Hello there, guys. I think the music's probably really loud. Oh. Are we here? Are we here? Are we here? Okay. Oh, that's probably really loud. Maybe. Dun dun dun. We're here in the jungle. That background music is vexing me now. Some somewhat ambient background music, but no, it's vexing. Am I too loud? Am I too loud? I don't know. I do not know. We're about to find out. Welcome to whoever has joined. I need to make a poll. Yes, guys, we're doing it. We're doing 100 integrals. I'm doing it, and I'm making sure that I finish by 6 p.m. Okay, it's 7 minutes past 3. I'm going to do integration until 6 p.m. Hopefully we can get through all of them. And yeah, I'm going to do 100 integrals. So welcome to whoever's joined. Hello. Let me make it so the chat actually appears on the screen. Boom. Feel free to let me know how you guys are. And I want to do a poll because I need to ask you guys, what is your favorite monkey? I need to know, what is your favorite monkey? Let's see. Adding a poll now, guys. Adding a poll now. Start a poll. Right, I'm going to go offline for 1 second while I write the poll. Okay, it's just been created, guys. The poll has just been created. So I'm asking everyone, what is their favorite monkey? So we've got Curious George, Kong, that's King Kong, Caesar from Planet of the Apes, or obviously Harambe. Please do vote, and we're very, very quickly going to get started today. We're doing 100 integrals in a row. 100 integral. Everyone's been, guys, listen. Everyone has been wondering, debating on the internet, a simple question. Who would win? Who would win? 100 men or one gorilla? It's an interesting question, but I have a better question. Who would win? One gorilla or 100 integrals? Yes, that's right. I'm coming at you live from the jungle. Curious George. Curious George is a low power gorilla. He's iconic, but he's a low power gorilla. But Nishane, I appreciate the Curious George love. You know, someone's got to be there for him. I just think he's always up to mischief. You know what I mean? I think he's always up to mischief, so I don't like him. Okay. And guys, we also have Bantu. If you guys know who Bantu is, Bantu the gorilla, but he didn't make the cut. He didn't fit on the poll, unfortunately. But don't you worry about that. So guys, I'm going to open up the document. I'm going to show you something. Okay. I'm going to show you what we've got here. Documents. Where is it? One gorilla versus 100 integrals. PDF. I made something, guys. Nishane says, I got to go work, but I subbed. Thank you. I appreciate that. My computer. Let's go. There it is. So, guys, I need to share something with you. I've made a PDF document. And yesterday, guys, I did these 100 integrals. I did them. I sat in Starbucks. It took me about 3 hours. I did the 100 integrals, so I know how to answer all of them. I made them myself, but I didn't really work the answers out. And some of them are quite difficult. You guys can see here. Can I make that bigger? Oh, yeah, several pages. So you guys can see. Here we go. I wish it was slightly... Can I... No, I can't really zoom in. Oh, I've just been Thanos'd. I'm back. Okay. Yeah, guys, unfortunately, I don't think that I can zoom in any further, but when I actually do the integrals, you'll see them in more detail. But just to show you how it starts, so we've got one gorilla versus 100 integral. I'm the gorilla in this context, though, guys. Obviously, I'm not actually a gorilla, but it's just for the analogy. Like, it's just, you need to go viral. You know, you need to, it's a bit of clickbait. No, it's not. You guys think a gorilla can actually solve an integral? Come on. Maybe he can do a derivative, but not an integral. Too difficult. You think a gorilla can comprehend the reverse chain rule? Maybe the chain rule, but not the reverse chain rule. Okay. So this is the idea. Integrals 1 to 24 are Curious George level. Okay. So Curious George could do it. Then 25 to 58. This is like kind of intermediate. This is Bantu territory. Bantu the gorilla. As you can see, we have some Bantu integrals. Okay. Next one, 59 to 83. That's King Kong level. Okay. We're going up the Empire State Building. 59 to 83. As you may be able to see, these are looking a bit tougher. And finally, and you guys can probably hear those birds because they know stuff's about to go down. Well, not finally, but 84 to 94, that's Caesar, guys. Caesar. And I'm not even talking about the salad, okay? I'm talking about straight up. I'm not even talking about Julius, guys. I'm talking about Caesar from Planet of the Apes. He's a high power gorilla. And finally, Harambe. Harambe is arguably the most powerful of all the gorillas. And coming straight at you from the jungle, I can tell you that these integrals, again, don't know how easy they are actually to see because I can't figure out how to zoom in, unfortunately. When we actually do them again, it's going to be a bit easier because I'm going to write them down. But these are going to be the most difficult integrals, okay? And I want you guys to join me on this adventure as I do 100 integrals. And I show you that I, the gorilla in this analogy, not a real gorilla, guys, can actually face these 100 integrals. One gorilla versus 100 integrals. I think we should get straight into it. I've got until 6 p.m. Can't go past 6 p.m. I've got tutoring, got some private tutoring to get done, guys. Make some bread. But we're going to go there. So we've got 2 hours 45. Let's see how many integrals we can do. And I might have a break in the middle. Okay, guys. Share the love. So, remove, add. I'm still figuring out how this website works. Okay. Straight up from the jungle. Okay. And I've, as I said earlier, I've actually done all 100 integrals yesterday. So they're pretty fresh in my mind, just so I know how to actually answer some of them, because the easy ones are easy, but the hard ones are hard. Okay. Let's go straight in. What did I get recommended? In search of name, I'm in search of your subscription. That's why. Crazy game. Thank you. I appreciate it. I'm in the jungle, guys. I am the gorilla. I am the gorilla in the analogy. I'm not a real gorilla. Okay. But guys, we're going to do some integration. 10 people have joined. Welcome. We've got the whole pack. What's a group of gorillas called? I don't know. Guys, we need more votes, please. Curious George does not have 75% of the votes. Who am I talking to right now? Who do you think you're talking to? There's no way, guys, there's no way that thank you, someone just voted. I can only see Curious George for some reason. I think the poll is broken for me. Maybe I'll check on my phone, and then we're going to get started, guys. We're going to have a start on these 100 integrals. Could a gorilla do 100 integrals? Let's find out. Who's voting, guys? Who's voting on the poll? Where even is the poll? I'm such a boomer. I can't even work out how to look at my own poll that I made. Maybe it's just not on the phone. I don't know. Curious George has only got 50%. Guys, if Harambe, I can't see the others, but if Harambe doesn't have the other 50%, I don't know what to say. Anyway, guys, let's just get started because we've got until 6 p.m. I'm doing integrals until 6 p.m. Can we get through all 100 of them? I sure hope so. Guys, please also let me know if there's any technical difficulties. If the screen goes blank, if I freeze, if you can't hear me well, if the music is too loud, just let me know. Please do. Please let me know. Okay. Moment of silence. Okay, and let's go. But please, guys, do let me know if there's any technical issues. So integral number 1, again, I don't know. Am I able to... Is there a way so you guys can like see the 100 integrals? Like, I don't know. I don't know if there's a way. Like, I wish that I could. So, I've got. Sorry to faff about a little bit here. Oh, hello. Oh, I'm moving around. 13 people have joined, guys. I clicked on float. Oh, good luck on the integrals. Thank you, Redicus. I can't read Redicus what you just wrote. To be honest with you, that's a me problem. Okay, so before we start, I just want to show you guys one more time. Here's the 100 integrals. Curious George level integrals to begin with. Okay. Bantu levels, guys. Bantu is a gorilla that got sedated when being transported to another zoo. And unfortunately, the anesthesiologist went a bit crazy and he didn't wake up. So he's iconic. King Kong, obviously. King Kong, what can we say? Caesar, as in from Planet of the Apes. And Harambe. Okay. These are what I'm going off of, but I wish that you guys could like actually see, but then it's so small. I don't know. Can I add? No, it's like there's a limit. Is there really a limit on how many things I can do? Why am I sharing the screen with? Oh no, I'm not. Guys, sorry, I'm just being such a boomer right now. Just bear with me. And I'm gonna remove that. Add that. Boom. Make it bigger. Yes. Boom, boom, boom. 5 big boom. Okay. Delete that. No, I'm gone again. No, that's not right. Sorry, guys. Let's get rid of that. Let's get rid of that. Where have I gone? Unbelievable. Okay. I think we're just going to get started. Yeah, let's do it. So guys, please do let me know if there's any technical issues. I'm sorry that you can't see the PDF. I'm going to try and make it so that you guys can access the PDF afterwards, so you can, like, you know, try them yourself or whatever. But yeah, let's just go. So number 1 is the integral of x squared. Okay, so this is very simple. It's just going to integrate to a third x cubed plus c. Lovely, lovely, lovely. Okay, number 2. Obviously, they get progressively harder, guys. At the moment, we're in Curious George level. The next one is the square root of x, the integral of the square root of x. So the first thing I would do is rewrite this as x to the power of a half. And then remember, you add 1 to the power, so that's going to be 3 over 2, and you divide by the new power, and then you do a plus c. And that's going to simplify to 2x to the 3 over 2 over 3 plus c. Lovely. Okay. Next one, the integral of 1 plus x cubed over x squared. And by the way, guys, if these integrals are looking a bit easy, come back in an hour, see what's happening. The equals the integral of, right, so it's 1 over x squared if we split this up, plus x. Just by splitting this up using index laws. And this is the integral of x to the minus 2 plus x. And that's equal to x to the minus 1 over minus 1 plus a half x squared plus c. And I might write this as a half x squared minus 1 over x plus c, just like that. Cool. Question 4 is the integral of 2, and making sure that I'm not in the way here, the integral of 2x to the minus 5 over 3. So again, we're going to just add 1 to the power. So minus 5 over 3 plus 1 is minus 2 over 3. And then we can just simplify this a little bit. So times the top and the bottom of the fraction by 3. It's going to give us minus 6x to the minus 2 over 3 over 2, which is minus 3x to the minus 2 over 3 plus c. That also needs a plus c. There we go. So the final answer for that one is minus 3x to the minus 2 over 3 plus c. Green Pudding says, hello. Hello, Green Pudding. How are you? We're doing 100 integrals. And we're seeing if I can do it by 6 p.m. It's currently 23 minutes past 3. Hopefully I can. I did faff about a bit at the beginning, but we're on a roll now. Number 5. And keep voting on the poll. I want to know who is the premier gorilla. Okay. Who is the most powerful? Curious George, currently at 45%. Okay. Make that lower. I'm a hater. Okay, 5. The integral of sine x. These are currently Curious George level integrals, guys. So again, if you think that they're too easy, then they are. Even Curious George could do them, and he doesn't know anything. That's why he's so curious. All right, sine. What does that integrate to? It's going to integrate to minus cos x plus c. Because if you differentiate cos, you get minus sine. So there's a minus there. We need a minus there so that it becomes a plus. All right. If you've got an integration exam coming up, this is perfect revision for you. The integral of cos x dx is actually just positive sine x. Standard integral, guys. Standard integral. Number 7, the integral of e to the x. Again, another standard one. Maybe the easiest integral of all time. It's just e to the x plus c. Lovely stuff. By the way, guys, please just stop me if there's anything that I say that doesn't make sense or if you're confused by that. Next one, the integral of 1 over x. We're still just doing some standard stuff right now. This is the natural log of the absolute value of x plus c. Don't forget that absolute value, guys. What's with the primate theme? Anselm, I'm just chasing clout because it was the 100 men versus 1 gorilla. So I'm just trying to be like a bit like, I'm just doing my little maths spin. You know, what if the gorilla, instead of fighting 100 men, what if he fought 100 integrals? You know what I'm saying? That's all it is, mate. And I'm in the, I really am in the jungle. This isn't a green screen. I really am in the jungle. Look, I can even touch the leaves. I won't do it though. I won't. I don't want to go all the way over there. I don't want to go all the way over to the leaves behind me that are 100% real. Okay. Maybe this is about to turn into one man versus 100 gorillas. I don't know. Because I'm really in the jungle. Okay. Next one, number 9, is the integral of cosine of 2x. Okay. So this is going to be using the reverse chain rule. You could do a u substitution. You could let u equal 2x. That's chill. But this is going to be sine of 2x plus c. And if you differentiate sine of 2x, you're going to get 2 cos of 2x. So we need to put a half here so that everything kind of just works out. That's number 9. Number 10, we're doing the integral of 2x plus 3 squared. Okay, so you can do this in 2 ways. You can expand it, which is what I'm going to do, or you can do it by a substitution, or actually a third way, you can use the reverse chain rule. But because we're on Curious George time, we're on Curious George mode right now, I'm going to expand it out. Don't worry guys, we're going to get to all the juicy chain rule, we're just doing Curious George stuff right now. So this is going to be 4 over 3 x cubed plus 6x squared plus 9x plus c. And I'm just checking my answers as I go. I did every single one of these questions yesterday, guys. So you can imagine how long it's taken me. All right, the next one is the integral of 6e to the x minus 5x plus 1 dx. Okay. So what do you guys think? That's a rhetorical question. I'm not going to ask for your opinion. Well, you guys can tell me what you think. I love you guys. So this is going to be 6e to the x minus 5 over 2x squared plus x plus c. Okay. Next one, number 12, the integral. This one's actually a little bit tricky, of the square root of kx dx. Okay, and here k is positive. Just to be clear. Okay, so how are we going to do this? Well, guys, what I would do is I'd rewrite the integral as the square root of k times the square root of x. And then I would do the square root of k times x to the half. And then I would maybe even take out the square root of k. Okay, just like that. And that's going to be the square root of k times x to the 3 over 2 over 3 over 2 using the standard stuff plus c. And we can simplify this to 2 root k over 3 times x to the 3 over 2 plus c. And that's going to be the answer for that one. Okay, hopefully everyone's having a good time. This integral is giving me tangerine vibes. The duck with a monocle, I have no idea what you're talking about, bro. But I kind of don't want you to elaborate because I love how mysterious that sentence was. Well, do you know what? If I did ask you to elaborate, I'd be a bit of a Curious George myself. And Curious George is an op, guys. These integrals, up to integral number, I will tell you, up to integral number 24 inclusive, these are Curious George level integrals. And then they get harder, okay? I always do integration by parts. And so by explicitly giving functions to plug into the chain rule or product rule, because I really cannot stand the abuse of notation. What? Wait, I always do integration by parts. And so by explicitly giving functions to plug into the chain rule or product rule. Anselm, please elaborate. Is this OneNote? This is Microsoft Whiteboard. But guys, if you know how I can share the document with you, because I have a PDF document about 5 pages that has all the integrals on it that I've made up, please let me know how I can make it so you guys can access it, because I don't know, I'm a boomer. Okay, that was question number 12. Let's go on to question 13. Question 13, we're doing the integral from 0 to the natural log of 2 of e to the x plus 1. The plus 1 is in the power. dx. Okay, so this is the first one where we have limits. So we're doing a definite integral. So here we're going to integrate e to the x plus 1, which is still going to be e to the x plus 1, but we're going to plug in our limits like this. So we're going to get e to the power of the natural log of 2 plus 1 minus e to the power of 0 plus 1. So this is e to the power of the natural log of 2 times e minus e. And e to the power of the natural log of 2 is just the e and the ln cancel. So it's 2e minus e, which is actually just e. So the answer to number 13 is actually just e. Anselm, you can just not write it that way. I'm not sure what your... wait, I don't like that you treat dx and du as real terms and manipulate them. To me, they're just syntax. So the normal way of writing u substitution is simply nonsense. Yeah, you're kind of right to an extent. Yeah, a lot of stuff in maths. Another one that is very much like abusive notation is when you solve a differential equation by separating the variables, like timesing both sides by dx. I imagine, Anselm, that you also have a problem with that. I don't know what your level is, so I don't know. I don't want to be condescending if you already know this, but it turns out that it is okay to do it, but you're right, it's an abusive notation, but it works out. Like, it's actually fine to do it. It's okay, but you're right, it's quite an abusive notation, I would say. The duck with the monocle says Google Drive or Mega Upload. Most convenient way would be the Google Drive. I'm just going to very quickly do that. How do I do that? I want you guys to be able to access the document. Go on Google Drive. Boom, boom, boom. Sign in. Give me 2 seconds here. So can I... Oh. Someone give me detailed instructions as to how to do this. Just because I'm so bad at technology. Okay. And Anselm says, yeah, I'm aware that it's fine, but I cannot be bothered to figure out why exactly. Yeah, no, fair enough, fair enough. Separation of variables, it's like a convenient thing. It kind of just works. U substitution is very complicated. So you would have to, really, you'd have to do quite a lot of, like, a maths degree kind of thing, real analysis, doing metric spaces, measure theory, studying integration in a lot of detail to be able to like fully understand it. You probably have you might have a problem with just integration generally speaking, because it is very mysterious, and it's like, what exactly does it mean to integrate something beyond finding the area under a curve? If you think about it in a bit more detail, it's, and there's lots of different ways or paradigms of actually doing an integral. You have Riemann integration, and you could do it by using what you call regulated functions, or Lebesgue integration. Like, there's a lot of it. It gets very in the weeds. But anyway, guys, this gorilla doesn't know about none of that. Let's go straight in. I'm calling myself a gorilla, by the way, not you, because I'm the gorilla, because I'm doing 100 integrals. Okay, that was question 13. Please do, because that's an interesting conversation. Please do let me know if you have any more thoughts on integration, because it's fascinating, actually. All right, next one is the integral from 0 to pi over 2 of sine 2x dx. Okay, so this one again, sine is going to integrate to minus a half cos 2x, and that's because if you differentiate this, the 2 comes out, cos differentiates to minus sine, the minus cancel, so that's definitely right. Put the limits in. Got minus a half cos of basically pi minus a half times cos of 0. Now cos of pi is -1, so this becomes positive a half, minus a half times -1, and cos of 0 is 1, so like minus a half, so a half plus a half is 1, so the answer to that one is actually just 1. Okay, number 15. This one's really interesting. So a lot of people have slight issues with an integral like this. The integral of 1 over, let's say, 3x with respect to x. And some says, I know way too little about proper maths, i.e. doing the nuts and bolts computation, so I kind of don't understand why it's not okay to just equate the integral with the antiderivative, or with an antiderivative. Well, you can, you can do that. You can. They are the same. But it's just more of like the idea of an integral on it. Like, I don't want to do too much of a detour into this, but like, Anselm, let me give you an example, right? So if I constructed a function, you normally call this like a pathological function because it's really nuts. But let's say that I have a function and I'll call it f of x. And I'll say that f of x has got two outputs. It gives you an output of 0 if x is a rational number, and it gives you an output of 1 if x is an irrational number. So for example, f of 1.5 would be 0 because it's a rational number, but f of root 2 would give you 1, or f of pi would give you 1, or f of the natural log of 2 would give you 1, because that's an irrational number. Now, you can't actually draw this function because it's like it. You can imagine, this is it. It would just go like, it would just do this basically. But the problem is it would have infinitely many oscillations. You can't actually draw it, because between any two peaks, there's infinitely many more peaks, because between any two rational numbers, there are infinitely many irrational numbers, and between any two irrational numbers, there are infinitely many rational numbers. So it's kind of impossible to draw. And the question is very simple. What is the integral of the function? Let's say between 0 and 1. What's the area underneath the graph? Well, you might say, what on earth? I don't know. It turns out that depending on the paradigm that you integrate under, you either can or cannot do this. Okay. So if you do what's called Riemann integration, this integral is completely meaningless. It's not equal to anything. It doesn't make sense as a question. However, that was Riemann. Years later, a fellow comes along called Lebesgue, who changes the paradigm of integration and says, well, I've got a way of doing this so that actually you can find this integral. And if you use this Lebesgue integration, actually you go from not having an answer to having an answer. And actually it turns out that the area would be 1, because there are far, far more irrational numbers than rational numbers. Okay, so the area is mostly 1, and so that's the idea. Now that's a real problem. So Anselm says, yes, I've heard about this Lebesgue integrable, but not Riemann integrable, if I remember correctly. But I don't understand why you can't just ask if any function has a derivative equal to this. I.e., it seems to me that one of the types of integration, Lebesgue or Riemann, would be unambiguously the correct one. You're saying surely one should be right and one should be wrong. Yeah. Well, the thing is that integration has different definitions depending on how you do it. So Riemann integration and Lebesgue integration, they're two of many ways. They're not the only, and it's just a completely different paradigm. I can't remember the phrase that's normally used for it, but it's like integration. Like if you can define integration to be the area underneath a curve, but it causes all sorts of problems because there are functions that kind of do have an area, but not like a trivial area, like the one that I've just given you there, the example there. I think that's called the Dirichlet function or Dirichlet function or whatever. But anyway, this is very complicated. But yeah, not to go on too much of a detour, but it's a hugely important concept in maths, in analysis, and like measure theory and stuff. and talking about the measure of different sets and stuff like that, like the measure of the irrational numbers versus that of the rationals. It's very complicated. It's very complicated. But yeah, neither of them are unambiguously the correct way of doing integration. What if we just say an integral of f is capital F if and only if the derivative of f is f? Well, in that case, there are some functions. So I'm only talking, integration is the same thing as anti-differentiation, you could say. But I'm only talking about the area under a graph, because there are plenty of functions that are not integrable. There are plenty of functions that are not integrable. There are plenty of functions that cannot be expressed in terms of elementary functions. Okay. Before I go back into the questions, let me just give you one. The integral of e to the power of sine x, I believe it was a French mathematician. I don't know how to pronounce his name. It's like Leoville. He proved that this integral is not expressible with elementary functions. The integral exists, but you just can't express it. So there's lots of issues with the idea of integration. And you could express a function in terms of an integral. You could say, well, the function that integrates to this is literally this. Symbolically, it's just the same thing, but with an integral or whatever. But it's very complicated. It's very complicated. Good questions, though, Anselm. Very good questions. Very good questions. Let me go back to the thing, because I don't want to spend too much time on it, but please do continue asking, because there's a great line of questioning. To be honest, I may not even be the best person to answer the question, to be honest with you. It's not my speciality. So if you come across anyone that studies things like measure theory, metric spaces and stuff, then they'll probably be able to give you a better answer than me. But that's the idea. Anyway, this integral is very interesting. So there's two ways of doing this, and you'll get different answers if you do either one of them. So the normal way, I guess, of doing this is to rewrite it as a third times the integral of 1 over x dx. And then this gives you a third times the natural log of the absolute value of x plus c. Boom, done and dusted. Now, that's not the only answer, because you could also do this by saying that it's the natural log of 3x over 3, like 1 over 3 times the natural log of 3x plus c. This is also a valid answer, because if you differentiate this, you would get 3 over 3x, and then there's still a 1/3 over here. Those 3's cancel. You get 1 over 3x, which is what you started with. So both of them are valid, but they're explicitly different functions. The reason why this works, though, is because they only differ by a constant. So the c's are just different numbers. So it's actually fine. I have a whole video about this, doing the same integral 4 different ways and getting 3 different answers, but they all only differ by a constant. Anyway, the natural log of 3x is the natural log of 3 plus the natural log of x. So you can see that you do get the same answer, but you just have this extra term, so it changes the value of c. So the c in the second version is a third times the natural log of 3 less than in the first version, but they're both completely correct. Anselm says, I think I'll stop asking about this or you'll never get back on topic. Very true, very true. But thank you very much for the questions. I do appreciate it. And if you have any more questions, feel free to answer or to ask. You can answer your own question if you want. Sometimes I do that. Okay, number 16, the integral from 0 to 1 of a times x to the a dx, where a is not -1. Okay, so for this one, we're just going to do our normal method. So because a isn't -1, we can just add 1 to the power and take 1 off the power. We don't need to worry about if it's x to the -1, we get a logarithm. That's not going to happen. So we've got a times x to the a plus 1 over a plus 1. And we're evaluating that between 0 and 1. So we're going to get a over a plus 1. And that's going to be the answer. Cool beans, cool beans. Okay, number 17. The integral of cos of x over 2 dx. Okay, so this one, similar to before, this is going to be 2 lots of sine x over 2 plus c, because if you differentiate sine of x over 2, you're going to get a half cos x over 2, and the 2 will cancel with the half to give you the 1 that you want. Number 18, the integral of e to the 4x minus e to the 2x over e to the x. So the way that I would do this is I would simplify. So I've got e to the 3x minus just e to the x. And that's going to give me a third e to the 3x minus e to the x plus c. Okay. For number 15, do any of the 2 solutions equal 0 at x equals 0 if you set c equal to 0? I can't see them anymore, so I can't check for myself. Let me just go back so you can look at it again. I've got to reread your question. I'm not 100% sure what you mean. So you're saying, let me just put you here. You're saying for number 15, do any of the solutions equal 0 at x equals 0 if you set c equal to 0? So if you set c equal to 0, then yeah, like when x is, well, not when x is 0. When x is 1, then it would give you 0. It's Lun. Oh, I'm not sure, Anselm. I'm not sure what you're... No, don't apologize. I wasn't sure what you were actually asking, but that's okay. Please keep asking away. Okay, that's 18. Number 19. We're almost through the Curious George questions, guys. It's going to ramp up. Next one is the integral of pi over x to the 4. Okay, so again, for this one, we're just going to rewrite it as pi x to the minus 4 dx. And that's going to be pi times x to the minus 3 over minus 3 plus c. So minus pi over 3 times x to the minus 3 plus c. Just like that. Or you could have, obviously, you could also have a minus pi over 3x cubed plus c. Obviously, they're the same thing. So you could have that too. That's all good. The natural log of 0, yes, the natural log of 0 is undefined. Undefined. Or it's kind of minus infinity. Like, it's kind of okay just to say it's minus infinity. It's not quite as bad as 1 over x at 0. That's actually undefined because depending on which side that you approach it from, you get different answers. As x approaches 0 from the positive direction, it's positive infinity. But as it approaches 0 from the negative direction, it's negative infinity. That's why when people say, well, technically, anything divided by 0 is infinity, it's like, actually, that's literally wrong. Because you could easily argue that anything divided by 0 is minus infinity, just as much as it's positive infinity. But the natural log, it doesn't work that way. Okay, number 20. The integral of cos of x plus pi over 3. So this is just going to be sine of x plus pi over 3. When we differentiate sine of x plus pi over 3, we're just going to get 1 times cos of x plus pi over 3. So we don't need any number on the front, but we do need a plus c. Okay. Question 21. We've got the integral of 1/3 x to the minus a half dx. Okay, so that's just going to be a third x to the half over a half plus c. So in other words, it's going to be 2/3 x to the half plus c, or 2/3 the square root of x. Cool. Question 22. The square, we're going to do the integral of the square root of the square root of x. So we have to realize that the square root is the same as x to the power of a half, and it's being raised to the power of a half twice. So this is x to the power of a quarter. Okay, so if we add 1 to the power, we're going to get 5/4 divided by 5/4. So we have got 4/5 x to the 5/4 plus c. Amazing, amazing, amazing. And of course, that's just when x is positive. I got to stop asking questions because I don't pay attention to the maths on screen when I'm typing. I love that. I love that. But you can ask questions, and if you want me to, elaborate on anything, then please do. All right, this one's really interesting. So the integral of arctan of the natural log of k plus 1 dx. And this is when k is bigger than -1. So I'd like to know if anyone has an idea for this. Maybe Anselm knows. It's kind of a trick question, but maybe that's giving it away. This is to catch all the curious Georges. Okay. We need higher level gorillas. Got the iced coffee. So the idea is that there's actually no x in it at all. Isn't that just a constant if k doesn't depend on x? You're absolutely right. It's just a constant. So it's kind of a trick question because this is actually just going to integrate to arctan of the natural log of k plus 1 times x plus c, because it's just constant. It's the same thing as if it was just like a. What's the integral of a with respect to x? Well, ax plus c. So same thing. Good spot. Okay, number 24. This is the last Curious George question. Number 24, we've got the integral from 1 to 2 of x e to the natural log of 2x. Okay, and of course this is, again, this when x is greater than 0 and all that business. Okay, so we're just going to simplify this. Now, e to the ln 2x is just 2x, so this is just 2x squared overall. Okay, and we're going to integrate this, and we're going to get 2x cubed over 3. So it's going to be 2 times 2 cubed, so 16 over 3 minus 2 over 3. That's 14 over 3. Okay, and that's the answer to that one. So we've finished the Curious George questions. And Anselm says, so it's just that times x. Absolutely. Yeah, plus c, of course, but yes, for the last one. Okay, guys, we've made it out of the Curious George situation. And now I'm going to start a new tab because that one was getting all slow. We're going to look at the Bantu level questions. Okay, I'm going to start labeling this. This is Bantu level questions. Again, Bantu, if you don't know who Bantu is, Bantu was a gorilla that was sedated, and the anesthesiologist that sedated Bantu gave him a little bit too much of the good stuff, you know, and he was dreaming about bananas, and then everything faded away. Unfortunately, Bantu never woke up from his slumber. They were transporting him to another zoo. So he's in the same vein as Harambe, but Harambe died an honorable death, and Bantu just, slipped away. So, okay. What's the time? Okay, we've got over 2 hours. Number 25, let's ramp this up. So again, these aren't going to be like crazy difficult, but they're going to be a little bit harder. Some of them are still quite easy, like that one. Number 26, e to the half x. That's going to be 2e to the 2x plus c. Number 27, we've got the integral from 0, that's a 0, 0 to 2 of e to the bx dx. This is going to be 1, oh, let me move because my head's probably in the way of that. 1 over b e to the bx, from 0 to 2. And of course, b can't be 0, guys. I should have written it, but b can't be 0. And so we've got 1 over b e to the 2b minus 1 over b, just e to the 0. So overall, 1 over b e to the 2b minus 1 over b, or 1 over b e to the 2b minus 1. Again, b is not able to be 0. By the time you send a question, you're already 2 integrals down the road. The chat delay is making this kind of hard. Yeah. So some of these, I mean, some of them will take a bit longer. Don't worry. These ones, I'm just blitzing them because they don't really require much, much thought really. But as they get harder, I'm going to, talk to you a bit more about it. Next one is cos squared. So this one, guys, is you can't just directly integrate it. You have to use an identity from trigonometry that says that cos of 2x is identical to, we can use 2 cos squared x minus 1. Okay, so just by rearranging this, this is the same thing as the integral of a half plus a half cos 2x. So instead of integrating cos squared, we can integrate this. So we're going to get a half x plus a quarter sine 2x plus c, okay? Because sine 2x differentiates to 2 cos 2x. 2 over 4 gives you the half that you want. All right. Question 29. We're doing the integral of sine squared x. Okay. So same idea, but there's also an identity that says cos 2x is 1 minus 2 sine squared x. Okay. That's just by using the Pythagorean trig formula on cos. Cos squared is 1 minus sine squared, and this just pops out kind of. So this is the integral of, if we just rearrange this, of 1/2 minus 1/2 cos 2x. So that's going to be a half x minus a quarter sine 2x plus c. Okay, hopefully everyone's chill with that. Okay, we're making good progress. Number 30. I do need to slightly speed it up. Okay. Okay, number 30. It's the integral, how could we leave it out, of tan squared x. Okay, tan squared x. So, tan squared, there's an identity here, because if we use the fact that sine squared plus cos squared equals 1, so sine squared x plus cos squared x is actually equal to 1. This is a well-known formula. If we divide everything by cos squared, then we get tan squared x plus 1 equals sec squared x. So what we can do, because tan cannot be directly integrated, we can replace tan squared with sec squared minus 1. And sec squared integrates to tan. So this is just tan x. Oh, it's just signed me out. Okay, give me 1 second, guys. It's somehow, for some reason, it's just signed me out here. I'm not sure why it's done that. Let's get back on it. Let me just sign in. Two-factor authentication. It's going to be the end of me. Okay. Lovely, lovely, lovely. And oh yeah, we're back. We're back. Okay, apologies for that. How loud is that? That's fine. Okay. All right. Anyone who's recently joined, we're doing 100 integrals. Okay. 1 gorilla versus 100 integrals. So anyway, as I was saying, sec squared integrates to tan. So we've got tan x minus x, because minus 1 integrates to minus x, plus c. That's number 30. On to number 31. The integral of x over the square root of x squared plus 1 dx. Okay. So I think this is the first one where I'm actually going to use the u substitution idea. So I'm going to let you don't have to do this, but I'm going to let u equal x squared plus 1, which means that du dx is 2x, which means that dx is du over 2x. So I can rewrite this integral as x over the square root of u times dx, which is du over 2x, and the x's cancel. And so I've basically got 1 over the square root of u, so that's u to the minus a half. And there's also this 2 here that, we can't forget. So I'm just going to put the 1/2 there, and it's du. And now we have a new integral that's easier. This is a Curious-George integral, not just a Bantu integral. This is a Curious-George integral. So we're going to add 1 to the power, so u to the half. There's still a half there anyway. And then divide by the new power. Look at all those halves. And they all cancel out, and we get the square root of u plus c there. That should also have a plus c. And we said that u was x squared plus 1. So we got the square root of x squared plus 1 plus c. That's the answer. That's the answer right there. Okay, hopefully everyone's happy with that. Right, that was number 31. Number 32 is the integral of x plus 1 times x squared plus 2x plus 3 to the power of 4. So again, I'll produce this by u substitution. So I'm going to let u equal x squared plus 2x plus 3, meaning that du dx is 2x plus 2, meaning that dx is du over 2x plus 2. So now my integral is x plus 1 times u to the 4 times du over 2x plus 2. I'm just going to write that as 2 times x plus 1 like that so that they can cancel. And then I've basically got the integral of a half times u to the 4 du. And that's going to be a half u to the 5 over 5 plus c, which is a 10th u to the 5 plus c, which is a 10th times x squared plus 2x plus 3 to the power of 4 plus c. Okay. Hopefully everyone is happy with that one as well. That's number 32. Cool. Right, on to number 33. So we've got the integral of cos x over 3 plus 2 sine x. So could look potentially quite difficult, but actually it's not really too bad. And actually there's a few integrals that we're going to be looking at that are kind of this form here. So we have to realize something. The derivative of the natural log of any function is equal to the derivative of the function divided by the function. Do you guys notice that the derivative of sine, or the derivative of 3 plus 2 sine x, is actually a multiple of cos x, because the derivative of the denominator of that fraction, 3 plus 2 sine x, is 2 cos x. So actually, we have an integral that's kind of this form. It's the integral of this, pretty much. And so that is just going to be the natural log of the denominator. And this is a really, really important concept that is used a lot in integration. So here we've got, basically, we just notice essentially that it's going to be the natural log of the absolute value of 3 plus 2 sine x plus c. And if you differentiate this, you will get the derivative of 3 plus 2 sine x, which is 2 cos x, over 3 plus 2 sine x, which is the same, but we don't want the 2 to be there, so we should have a 1/2 out here to cancel out with it, and that's going to be the answer. Hopefully that makes sense to everyone. Okay, number 34. We're still in Band 2 territory. There's quite a lot of Band 2 questions. We've got x over x squared plus 4 cubed dx. So, what are we thinking about this? Well, this is once again a reverse chain rule, substitution, whatever you want to call it. So I'm going to let u equal x squared plus 4. So du dx is 2x. So dx is du over 2x. And now I've got the integral of x over u cubed times du over 2x. And again, the x's cancel here. So we have the integral of a half u to the minus 3 du, which is going to be a half u to the minus 2 over minus 2 plus c, which is going to be minus a quarter u to the minus 2 plus c. So minus a quarter x squared plus 4 to the minus 2 plus c. And that's number 34. Amazing. Okay, on to number 35. We've got the integral from 0 to 1 of 1 over 1 plus x dx. Okay, so this one, again, it's just, we have to notice that the denominator differentiates to a multiple of the numerator. And because of that, the answer will be the natural log of the denominator plus c, and it might need to be multiplied by something, but it actually doesn't in this specific case, doesn't, because the derivative of the natural log of 1 plus x is only the number 1, which is what's up there. So no constant needed, but it is a definite integral, so actually we don't need the plus c. And that's from 0 to 1. So we've got the natural log of 1 plus 1 minus the natural log of 1 plus 0. The natural log of 1 is 0, so it's just the natural log of 2 is the answer. And that's the idea. That was question 35. Cool. Okay. Question 36. The integral of 3x squared plus 2x over x cubed plus x squared plus 7. Okay. Again, guys, notice that the numerator is exactly the derivative of the denominator. So this very simply is just going to be the natural log of x cubed plus x squared plus 7 plus c. Nice and simple. 37. The integral of the derivative of a function of x divided by a function of x. And f of anything can't be 0, because otherwise that would be dividing by 0. Okay, how are we going to... Well, we already know that this is going to be the natural log of the absolute value of f of x, but how are we going to show it? We can do it by a substitution. So we can say that u is f of x, meaning du dx is the derivative of f of x, meaning that du is the derivative of f of x dx. So now we can rewrite this as, well, the derivative of f of x times dx is just du. So basically it's just du over f of x, which is u. So it's just this. So it's the integral of 1 over u, du basically. And that's going to be the natural log of the absolute value of u plus c. And that's the natural log of the absolute value of f of x, because we said that u was f of x. And that's how you actually prove that. Hopefully everyone's happy with that one. Let's go back up here, because I think it's getting slow because I'm making the whiteboard really big. Okay, so that was number 37. On to number 38. the integral of cos x times sine to the 5x dx. So this one is also one that it trips up a lot of like A-level students, this one. So any ideas on how we can do this, guys? Well, what I would do here is I would realize, again, it is a case of realizing that the derivative of sine to the 6x is 6 cos x sine to the 5x, because when you use the chain rule, remember sine to the 6 means sine x and then to the 6. So 6 comes down, derivative of sine is cos, take 1 off the power. Notice that actually that's exactly what we want, but it's 6 times bigger. So this is going to be a 6th times sine to the 6x. Oh, no dx. Why have I written dx? Plus c. That's what I meant. Okay, cool. That was number 38. I'm also just going to make a new whiteboard because it looks like it gets slow quite quick here. So making a new whiteboard. Lovely. Still on the Bantu questions though, guys. Okay, next one is pretty interesting. So this is the integral of tan, that's a tan, of kx. And k is not 0. So how do we integrate tan? Well, we can notice that the integral of tan is the integral of sine of kx over cos of kx. Okay. And guys, cos differentiates to minus sine. So this is going to be another ln. It's going to be the natural log of cos of kx plus c. And the question is, what number goes out front? Well, if we differentiate cos of kx, we're going to get minus k sine of kx. We don't want that. We just want sine. So we've got to divide this by minus k, times it by minus 1 over k. Okay. Now, the way this is normally written is this minus ends up going inside of the ln. So you end up with positive 1 over k times the natural log of cos of kx to the minus 1. And remember, cos to the minus 1 is 1 over cos, which is sec. So normally it's written as 1 over k times the natural log of sec x. Okay. So that's the integral of tan kx. Oh, and sorry, that should be a k there as well. Sec kx. Okay. Please do let me know if I make any silly mistakes like that and I miss them. Okay. That was number 39. So by the exact same principle, number 40, which is the integral of cot of kx, is actually arguably simpler. So this is the integral of cot kx, sorry, of cos kx, cos of kx over sine of kx. And the reason why I say this is actually simpler is because sine directly differentiates to cos. There's no minus business. So this is going to be 1 over k times the natural log of sine of kx. Again, this is when k is not the number 0. And just convince yourself that that's right. If you differentiate the natural log of sine of kx, you're going to get k cos kx over sine kx. And then the 1 over k gets rid of the k on the numerator. Okay. All right. Question 41. The integral of cos x e to the sine x dx. Now, again, this question potentially might seem like it's not actually very easy, but actually it's not bad at all. So the idea here is that the derivative of e to the power of f of x is always the derivative of f of x times e to the power of f of x, like that. And actually notice, guys, that that's exactly what we've got with f of x being sine. So this is just going to be e to the power of sine x plus c, because e to the sine x would differentiate to cos x, e to the sine x. Okay. And welcome to anyone who's joined. We're doing 100 integrals. We're almost halfway there. Okay. Question 42. It's the integral of x times the square root of x plus, that's question 43. Sorry, this is I missed one out. Question 42 is we're doing the integral of the derivative of f of x times e to the power of f of x. So again, we're going to prove that this result gives us just e to the f of x. So again, we can let u equal f of x, meaning that du dx is the derivative of f of x, meaning that du is the derivative of f of x dx, meaning that dx on its own, dx is equal to du over the derivative of f of x. The chat might be in the way there, okay? And then, so that's going to be equal to the integral of the derivative of f of x times e to the u, and dx is du over the derivative of f of x. And you can see that they cancel. So you have the integral of e to the u du, which is just e to the u plus c. And we said that u was f of x. So it's e to the f of x plus c, just like that. Cool. Lovely. We're getting there. Guys, at question 50, I'm going to take a very short 5-minute break just to like refill my coffee and stuff. Question 43. How much time have we got? We're doing all right. We're doing all right. Got until 6 o'clock. 43. That's going to be the integral of x times the square root of x plus 5. So again, I'm just going to do a u substitution, let u equal x plus 5, because it can't be directly integrated. So that means that du dx is the number 1, so du is equal to dx. And we can rewrite this as x. X is u minus 5. And the square root of x plus 5, that's just u. And dx is du, so just du. And that's going to be the integral of u squared minus 5u du. And that's equal to a third u cubed minus 5 over 2u squared plus c. And that's a third times x plus 5 cubed minus 5 over 2 times x plus 5 squared plus c, just like that. Okay. That was question 43. Okay. Oh, wait, guys, that's actually wrong. This is me making a silly mistake. For some reason, I wrote u, not u to the half. So actually, let me just go back on this. Lucky I checked my... Again, I literally did all of these. I did all 100 of these questions yesterday. And I've written out the answers to all of them. So lucky that I'd done that and checked it, because I think I would have missed that, to be honest. That's not the answer. I'm just like Rag and Bone Man, because I'm only human after all. Don't put the blame on me. That's me right now. Okay, so yeah, it's u minus 5 and then u to the half. So actually, it's the integral of u to the 3 over 2 minus 5u to the 1 over 2 du, which is u to the 5 over 2 over 5 over 2 minus 5u to the 3 over 2 over 3 over 2 plus c. So 2/5 u to the 5 over 2 minus 10/3 u to the 3 over 2 plus c. And that's going to be 2/5 x plus 5 to the 5 over 2 minus 10/3 x plus 5 to the 3 over 2 plus c, like that. Okay, cool. And that is the answer after all. That's the one. Cool. All right, that was question 43. On to question 44. Question 44, we're doing the integral of x plus 3 over x plus 8 dx. So for this one, I think you could probably let u equal x plus 8, but I'm going to do it as, I'm going to write this as x plus 8 minus 5 over x plus 8. Or you could use polynomial long division another way. There's lots of ways to do this. The reason I've done that is because now I've got this as x plus 8 over x plus 8 minus 5 over x plus 8. And this is the integral of just 1 minus 5 over x plus 8. And that's going to be x minus, and we can see here, this is 5 times the natural log of x plus 8 plus c. So that's what number 44 is saying. Okay. Number 45. That's going to be the integral of 1 over the square root of 1 minus x squared. So this is a very, very well-known integral. It's like a standard integral, but it's a little bit higher level. Cosmin says, I like this trick. I know, right? It's pretty cool. You can technically do that any time that you use algebraic or polynomial long division. It technically works any time. And polynomial long division is just an algorithm that automatically does it, but that's all it is. So yeah, it's quite clever, right? It's quite clever. Now, if you don't know about this trick, you're going to be mind blown, but Cosmin, you might already know about this. So the integral of 1 over the square root of 1 minus x squared. So we're going to do a substitution, and you guys might already know it because it's quite well known, but still, if you don't know it, your mind's going to get blown. We're going to do a substitution to make this the integral easier. Okay. You might say, well, maybe u should be 1 minus x squared. Or maybe u should be just x squared. Or the square root of 1 minus x squared, or some variation of that. But actually, it turns out that none of those are very good. And actually, the best substitution that you can make, it's actually so good that it's going to turn the entire integral into just the integral of the number 1. The best substitution is to replace x with sine u. Okay? I know it's really random, but dx du becomes cos u. So dx is cos u du. So you've got the integral of 1 over the square root of 1 minus sine squared u. And dx is cos u du. Now the clever thing is that 1 minus sine squared is cos squared. And then you take the square root of it. So this is the integral of cos u over cos u. The denominator is just cos. Okay, and we're assuming that the inside of that square root is positive and all that stuff. And not only is the inside of the square root positive, but it is indeed positive. That's fine. And then so this is just the integral of the number 1, which is literally the best substitution that you can possibly do. Now, with respect to u, this integrates to u plus c. And finally, we just got to put x back. Now, we said that x was sine u. So that means that u on its own is inverse sine of x. So this integral is actually equal to arc sine, or inverse sine, if you prefer that notation, of x, like this. Okay, believe it or not. I know it's crazy if you guys have never seen that before. It's very cool. Okay. Now, in a very similar vein, we're going to do the same thing, but with another integral, and it may or may not involve another trig function. So we're going to do the integral of 1 over 1 plus x squared. Okay, and I'm just going to cut to the chase with this one, but we can actually let x equal tan u, so that dx du is equal to sec squared u, because that's the derivative of tan. So dx is sec squared u du. Okay, and this integral becomes the integral of 1 over 1 plus tan squared u times sec squared u du. And again, if you know your trig identities, you will be able to say that, wait a second, 1 plus tan squared is sec squared. 1 plus tan squared is sec squared. We actually used it earlier. So again, this becomes the integral of the number 1 du, which is u plus c. And u, remember we said that u was, that x was tan u. So that means if x is tan u, then u is arctan or inverse tan of x. So this integral, the integral of 1 over 1 plus x squared, which is a pretty basic standard integral, ends up being the same function as arctan x. What the hell? What the hell? I know, it's crazy. What's the count of integrals? Need to know how deep you are in the list. That was integral number 46. The duck with a monocle. That was integral number 46. We're still on band 2. We're still level 2 because there's quite a lot of level 2 questions. Okay, question 47, and we're taking a break after question 50. Only for a few minutes. All right, 0 to pi over 2. This is number 47. Of sine theta over 1 plus cos theta. D theta. Okay, we're using thetas, but that's okay. So guys, once again, cos differentiate, or 1 plus cos theta differentiates to minus sine theta. So we know this is going to be an ln 1 plus cos theta. And if you differentiate this, you're going to get minus sine. So we need another minus here to cancel it out. And we're going to go from 0 to pi over 2. And so this is going to be minus the natural log of 1 plus cos pi over 2 minus the natural log of 1 plus cos of 0. Okay. Now, cos of pi over 2 is 0. So this is minus the natural log of 1 plus the natural log, and cos of 0 is 1, so the natural log of 2. So the natural log of 1 is 0. So this is just the natural log of 2. That was question 47. Okay. In the jungle. All right. Question 48. Again, I think I keep having to like blitz through these whiteboard tabs because they just get slow really quick. Okay, number 48. We want to do the integral of e to the 2x over e to the 2x plus 1 cubed dx. Okay, so for this one, we're just going to let u equal e to the 2x plus 1. This is a pretty standard substitution. So du dx is 2e to the 2x. So du is 2e to the 2x dx. So dx is du over 2e to the 2x. Okay, so the integral is going to be the integral of, I'll leave e to the 2x there for a second, over u cubed. And again, dx is du over 2e to the 2x. So they cancel. And so we've got the integral of basically a half u to the minus 3 du, which is adding 1 to the power, it's a half u to the minus 2 divided by minus 2 plus c. So in other words, minus a quarter u to the minus 2 plus c, or minus a quarter times e to the 2x plus 1 to the minus 2 plus c. Hopefully everyone's kind of happy with that. Move that up so you guys can see it. Cool. All right, that was question 48. Now for question 49. We're doing the integral of x times sine x. This is the first one where we're going to use integration by parts. So we're going to let u equal x, and we're going to let dv dx be sine x. Okay, so du dx is the number 1, and v is minus cos x because we've integrated. So minus cos x is what differentiates to sine x. So that's how we've done that. And we're just going to use the formula. I'll write it down once and once only. The formula for the integral of u times, let me move down so you can see it better. U times dv dx with respect to x is equal to uv minus the integral of v times du dx. This is the formula for integration by parts, gang. Okay. So I'm just going to use the formula. So u times v, got minus x cos x, minus the integral of basically minus cos x. So because it's minus cos x here, I'm just going to make that a plus and put cos x there because it's way easier. And so I've got minus x cos x, and cos integrates to sine, so plus sine x plus c. Cool. All right, and then let's do question 50. Question 50, it's the integral of x e to the 3x. So again, let u equal x, let dv dx equal e to the 3x. So du dx is equal to 1, and v is a third e to the 3x. Okay, and this is going to be a third x e to the 3x minus the integral of a third e to the 3x dx. And that's going to be a third x e to the 3x minus a ninth e to the 3x plus c. Okay, cool. So guys, that was question number 50. The time is 4:30, so we've got an hour and a half to do 50 integrals. That's not looking great for us, but you know, let's see how we get on. I may be able to go over a little bit because it's not an actual lesson that I'm doing. I'm not actually tutoring someone. I'm just taking a free meeting with them, and I may be able to ask them if they'd be kind enough to move the thing back by just a little bit. So we'll see about that. We'll look into it. But guys, I'm just going to take a short break, and we will be back with another 50 integrals. This gorilla, I'm the gorilla in this analogy, okay? This gorilla is not done. We're not finished with our integrals, okay? So I'll see you guys very, very soon. Hello again, guys. I'm back. Oh, my hair's tweaking though. I look like that kid from Sam and Cat. I look like Harry Potter. If you guys know what I'm talking about, maybe you do, maybe you don't. Okay, cool. So. Oh, let me do something. I think I can make my Wi-Fi a bit better. I might go offline, but I'll be back. Hello? Have I made my Wi-Fi better? Have I made it worse? Who knows? We shall see. Right. Okay, guys. So, hopefully, yeah, I think my Wi-Fi, I feel like it's going to be better now. Yeah, it is. It is. I just realized I wasn't connected to my Wi-Fi repeater the whole time. Anyway, let's crack on with some more integrals, guys. We are back. So, number 55, or 50, I actually can't count. Number 51. Okay, number 51. We're still in Bantu territory, guys. So this is an interesting one. The natural log, the integral of the natural log of x. So you might say, oh, how do we do this? How do we do this? Well, guys, you actually have to use integration by parts. So you let u equal the natural log of x, and you let dv dx equal the number 1. And just see what happens. Okay, so you've got x ln x minus the integral of x times 1 over x, which is the integral of the number 1. And so you've got x ln x minus x plus c. Believe it or not. Very cool. Very cool. Okay, number 52. I think the last Bantu question is like 58. Yeah, 58 is the last Bantu question, I think. And then it goes on to King Kong. Okay. Right, next one is the integral of the natural log of x over x. Okay, so you can do this by substitution or by parts, but I'll do substitution. So you let u equal the natural log of x. I think this is how you do it. Yeah, that makes sense. U equals the natural log of x. And then du dx is 1 over x. So dx is x du. So then you've got your integral as u over x times x du, and they cancel out. So you've got the integral of u du, which is a half u squared plus c. So a half times the natural log of x squared plus c. Amazing. Amazing. Cool. And again, guys, please do just let me know if you've got any questions or anything like that. I think now is maybe a good time to see what that poll was saying, because I don't know what the poll was saying. Okay, guys, so we've got 23 votes on the poll, and it looks like Curious... Are you serious? Is Curious George... Is Curious George seriously the highest, guys? It better not be. I think Curious George is the highest. Oh, no, no, it is. No, it's Kong. It's Kong, actually. I'm going to end the poll. But I love that, guys. So we had Kong at 39%, Curious George at 34%, Harambe at only 26%, and no one said Caesar. That's poor. 23 people. Good turnout, but guys, Caesar is the GOAT, guys. Unbelievable. Okay, I'm just kidding. So next up, 53. Question 53. Oh, this is a cool one. So the integral of 2 to the power of x. So 2 to the power of x. what can we do? Well, guys, all we've got to do is think backwards. The derivative of a to the x, if a is positive, is a to the x times the natural log of a. So the derivative of 2 to the x would be 2 to the x times the natural log of 2. So that means that in order to find something that differentiates to just 2 to the x, this is going to be 2 to the x divided by the natural log of 2 plus c. Okay, because if you differentiate 2 to the x over the natural log of 2, you'll just get the natural log of 2 times 2 to the x over the natural log of 2. So it works. Bit random, but yeah. And you could probably do u equals 2 to the x. That'd probably work as well. All right, next one, 54. Oh, this is a really cool one, guys. So if I'm just on in the background, lock in for this one, because this is a really cool integral. I've got a video on this one, actually. I've got a YouTube video on this integral. So guys, oh, and I just realized I'm not actually full screen. There we go, makes it slightly bigger. So this one, you can just let u equal sine x plus 1, and I think it works. But there's a really cool way of doing this, which I love it. And so what we do is, maybe this is a little bit overboard, but it's the coolest way. We rewrite sine x using the double angle formulae, okay? So using the double angle formulae, sine x is the same thing as 2 sine x over 2 times cos x over 2. So I'm just going to, because normally it's like sine 2x equals 2 sine x cos x, but you can just halve everything, that's fine. And so you've got 2 sine x over 2 cos x over 2. And then the number 1, you can replace it with cos squared of x over 2 plus sine squared of x over 2. Because remember, cos squared plus sine squared is always the number 1. Okay, and you might say, oh, you've made this way worse. Look at what you've done. You've made it so much worse. Well, guess what? Inside of this square root lies a perfect square. Notice that the inside of this square root is actually cos of x over 2 plus sine of x over 2 squared. Okay, because if you expand it out, you're going to get cos squared plus 2 times cos x over 2 times sine x over 2 plus sine squared. And why is that nice? Well, because we're doing the square root of that. Okay. Now, technically, because we're squaring it and then square rooting it, it should be the absolute value of cos x over 2 plus sine x over 2 here, the modulus. But notice the integration limits 0 and pi over 2. Cos and sine are both positive in the region that we're integrating. So we don't need to worry about the absolute value sign. So they just cancel out. And don't you guys think that's kind of awesome? Because I do. Okay. And then we actually integrate. So cos is going to, or cos of x over 2 is going to integrate to 2 sine x over 2. And sine of x over 2 is going to be minus 2 cos of x over 2. Like this, from 0 to pi over 2. And then, from here it's pretty basic. So we've got 2 sine pi over 4 minus 2 cos pi over 4 minus 2 sine of 0 minus 2 cos of 0. So sine and cos of pi over 4 are the same number, okay? Sine of pi over 4 is root 2 over 2, and so is cos of pi over 4. So these cancel out. They're the same number. And then we've got sine of 0 is 0, and cos of 0 is 1. So it's minus 2. So the answer is just 2. So the integral of the square root of sine x plus 1 from 0 to pi over 2 is just, let me get rid of that, it's just the number 2, as you guys can see there. And don't you guys think that's awesome? Because I do. I think that's really cool. I'm a big fan of that. Okay, that was question 54. Let's go on to question 55. Question 55. the integral of x squared times the natural log of x. Okay, so again, this looks like an integration by parts. So we're going to go u equals, oh, not u equals x squared. We're going to go u equals ln x. And dv dx is going to be x squared. So we've got du dx is 1 over x, and v is a third x cubed. Okay, and again, using the formula, it's going to be a third x cubed times the natural log of x minus the integral of a third x squared, because it's x cubed, but then it's divided by x. So this is going to be a third x cubed times the natural log of x minus, and then this is going to be a ninth x cubed plus c. And that's the answer. Okay, hopefully everyone's nice and happy with everything so far. Again, I'm just going to make a new whiteboard because it's just getting slow. Again, okay, cool. That was question 55. On to question 56. This is another one that's kind of like superficially difficult. So 6x squared minus 4 cos 2x plus 4e to the 2x, all divided by x cubed minus sine of 2x plus e to the power of 2x. Okay, now why do I say this is like superficially difficult? It looks really difficult. It looks really complicated. But guys, notice that if I was to differentiate the denominator, I would get 3x squared minus 2 cos 2x plus 2e to the 2x. So the numerator is just double the derivative of the denominator, meaning that I know that I'm going to have the natural log of x cubed minus sine of 2x plus e to the power of 2x plus c. And again, if I do this, I'm going to get one lot of the derivative over the original. I don't want that. I want 2 lots. So I need to double it. There we go. And that is the answer to number 56. Cool. 57 next. 57. Okay, this one's cool. So the integral of sine x. Okay, this is hyperbolic sine. Hyperbolic sine. Okay, you might say, what is that? There's going to be a few of these. So if you've never heard of it, let me break it down for you. Sine x, so sine with an h, is the same thing as e to the x minus e to the minus x over 2. You might say, what's that got to do with trigonometry? It's related to the trig functions via complex numbers. It's a very interesting function, very useful. Turns out that sine actually just integrates to this thing called cosh. And before I show you that, I'm going to write down what cosh actually is. Cosh is defined as e to the x plus e to the minus x over 2. So let me prove to you that the integral of sine is cosh. This is the integral of e to the x minus e to the minus x over 2. So that's just e to the x plus e to the minus x over 2 plus c. And it's kind of really, I mean, that's it. And again, this is, we call it cosh x. So sine integrates to cosh, or hyperbolic cosine is what you might call it. Okay. That is number 57. 58, number 58, this is the last Bantu level difficulty. The one after this is going to be a step up. That's going to be King Kong level. Okay. So we've got the integral of cosh x. Now, what do you think cosh would integrate to? You might say, is it minus sine because of sine and cos? But actually, no, it's even better than that. So the integral of cosh x is the integral of e to the x minus e to the minus x, or plus, sorry, over 2. And guys, this is just going to be, e to the x minus e to the minus x over 2 plus c. And if we remind ourselves, that was sine x. Okay, just going back up, sine x is e to the x minus e to the minus x over 2. And that's actually what we've got here. So sine, hyperbolic sine, integrates to cos, or to hyperbolic cos, and hyperbolic cos integrates to hyperbolic sine. There's no pluses or minuses. And of course, the same works with differentiation as well. Hyperbolic sine differentiates to hyperbolic cos and vice versa. No minus signs. Pretty good. Okay, guys. Now we are on to the next level, which is King Kong level. Okay. So this is Kong. All right. So we're getting crazy with number 59. This is the integral of hyperbolic tan, okay, or sometimes called fan. Okay. Now, what is tan? Well, hyperbolic tangent is, as you may know, or you may guess, hyperbolic sine over hyperbolic cosine. That's a cosh. Okay, and remember that sine is e to the x minus e to the minus x over 2, and cosh is e to the x plus e to the minus x over 2. So the over 2's cancel, and if you just times everything by e to the x, you've got e to the 2x minus 1 over e to the 2x plus 1. So this is the definition of tan, okay? That's the definition of tan. But we don't want to use the hyperbolic version because it's just really crazy. So the exponential version, I mean. So we're just going to do this as sine over cosh. Oh, and that should have a dx. Okay. Now, again, cosh directly differentiates to sine. So we can see that this is the natural log of cosh x. And it turns out, although it's not immediately obvious, cosh is never negative. It's always greater than 0. So we can get rid of the absolute value sign. So this is the answer. Okay. So hyperbolic tangent integrates to the natural log of hyperbolic cosine. Green pudding is back. Welcome back. Do you know what? Let's add that. Green pudding. I see you. You literally are. You're a green pudding in the profile photo. Green pudding is back. Okay. Thank you. Welcome. Welcome. That sounded a little bit sarcastic. I didn't mean it to be sarcastic. Okay. Question number 60. We're on Kong levels, guys. Question number 60. This one is a bit of a pain in the bum, but we're doing the integral. Where are we? The integral of e to the x times sine x. This is a very famous one. If you do A-level maths or whatever, it's a pain to do. So you do it by parts. So you say u equals sine x, and dv dx is e to the x. So that means that du dx is cos x, and v is e to the x, and then you use the formula. So you've got e to the x sine x minus the integral of e to the x cos x. And then you go, oh no, I've got e to the x cos x. So what you then do is you use integration by parts on this. So you say u equals cos x, and dv dx is e to the x. So du dx is minus sine x, and v is e to the x. So this integral here is u times v, so e to the x cos x, minus the integral of e to the x sine x. And a lot of people at this point are going to go, oh no, I've got back to where I started. But actually, that's not a problem. So if I label e to the integral of e to the x sine x, if I just call it I, then basically I have that I equals e to the x sine x minus e to the x cos x plus oh sorry, and I've made a mistake because this should have a plus here because it's minus sine times e to the x, and there's already a minus in the formula. I was going to say, I was like, oh, I've got it wrong. And when you do that, Oh, ruler. When you do that, there's a minus I there. And the clever thing about this is that if you add I to both sides, you get 2I equals e to the x. I'll factor out the e to the x there. Sine x minus cos x. So I is a half e to the x times sine x minus cos x. And I'll put the plus c here. So it's kind of a cheat way of doing it. So the integral of e to the x sine x, like if you do by parts, you kind of come back to it and you get half e to the x times sine x minus cos x plus c. So a very weird question, definitely a Kong level question. Definitely a Kong level question, quite difficult. Where do you get these problems? I made them, green pudding. I have them on a, let me very quickly show you. I have them on a PDF document here. So it's one gorilla versus 100 integrals. I made them all myself. And actually yesterday, I did all 100 of them just in a Starbucks. Took me ages. And some of them I I made them up and they were kind of impossible, like way harder than I thought they would be. So like I just had to change them and stuff. But there we go. They're the Curious George ones. We've already done all of those. There's the Bantu questions. We've also already just done all of them. King Kong, these are the ones that we're currently on. And then the Caesar questions and the Harambe questions. Okay. But I don't know how, I wish that I can share this with you guys, but I don't know how to do it. Someone said a Google Doc, but I genuinely don't know how that works. I don't know how to do it. So if anyone knows, that would be what I call bless. But going back to this, just take a quick, I'm like so, my mouth is so dry. Oh, sorry for the ASMR, guys. Okay. Right. Okay. Where are we? That was question number 60. Question number 61. Okay, this one looks crazy, guys. This is a Kong level question. What can we say? So 61, we've got the integral of 1 over 2x times cos of the natural log of x dx. So again, looks pretty crazy indeed, but you know, that's how we roll. So how might we do this? Well, we can do a substitution. So we can say that u is equal to the natural log of x, meaning that du dx is 1 over x, which means that dx is equal to x du. So this integral becomes that of 1 over 2x times cos u times x du. And the x's cancel out. So you've basically got a half times the integral of cos u du. So a half times sine u plus c. Or a half times sine of the natural log of x plus c, like that. And yeah, so actually not as bad as it looks, to be honest. Looks very difficult, but really, is it that bad? Is it really a Kong? Who knows? Okay, question 62. Question number 62. Right, we've got the integral of 2 to the power of log base 4 of x. Okay, so the difficulty in this one is not really the actual integration. It's using logarithms and understanding rules of logarithms, because if you don't understand it, then obviously you're not going to get very far with this. So because we've got 2 and the base of the logarithm is 4, what I would do here is I'd rewrite the number 2 as 4 to the power of a half. Okay. And the reason I do this is because now I can rewrite this as 4 to the power of a half log base 4 of x. Okay, and now I can rewrite this as 4 to the power of log base 4 of x to the power of a half. So I'm just using a lot of rules of logarithms here. And 4 to the power of log base 4 of something is just the thing in brackets. So it's just x to the half. And x to the half, again, this is a Curious George, guys. Come on, we can do it. And so we get 2/3 x to the 3/2 plus c. Okay, and that's that one. So really, it's just the integral of the square root of x, but it's written in a funky, funky way. All right, on to question 63. 63, right. We're going crazy. The integral from 1 to infinity of 1 over x squared dx. So this is our first what you call improper integral. It's an improper integral because the limit of integration, one of them is infinity, okay? And I will do this as rigorously as possible. So this is equal to the limit as t approaches infinity of the integral from 1 to t of x to the minus 2 dx. And it's really important to write the limit every time, even though it's tempting not to. X to the minus 2 integrates to minus x to the minus 1. Okay. And this is how you do this if you have a, you replace it with a t, do the integral as you normally would, and then let t go to infinity. So we've got minus t to the minus 1 minus 1 to the minus 1, like that. Okay. This is the limit as t approaches infinity of, this is minus 1 over t. Now, just to be clear, this is like 1 to the minus 1 and then minus minus, okay, just to be clear. So that makes a plus 1 there. As t goes to infinity, minus 1 over t goes to 0, okay? So that means that this is equal to just the number 1, because number 1 stays and chills, whereas the minus 1 over t goes to 0. As t gets bigger and bigger, 1 over t goes to 0. Cool. That was question 63. Yeah, 63. On to question 64. And the last King Kong question is 83. So we've got quite a while. Okay. Question 64. We're doing the integral from 0 to infinity of 1 over 1 plus x squared with respect to x. Again, this is an improper integral because we've got infinity there. So this is the limit as t approaches infinity of the integral from 0 to t of 1 over 1 plus x squared dx. Now, guys, remember, we've actually done this integral earlier. The integral of 1 over 1 plus x squared is arctan x, believe it or not. So this is arctan x from 0 to t. Okay. So this is the limit as t goes to infinity of arctan t minus arctan of 0. Okay, now arctan of 0 is 0, verifiable via the calculator. You might say, what's the limit as t goes to infinity of arctan of t? Well, if you know that normal tan looks like this when t is positive, for example, where there's an asymptote here at pi over 2, arctan is the inverse function of tan. So arctan, the graph will look kind of like this, with an asymptote in the same place, but it's horizontal, pi over 2. So we can see for arctan that the larger that t gets, the closer the arctan t gets to pi over 2. Okay, so, and you could check that. You type in arctan of a really big number. Okay, really big number. What are you going to get? And it's probably a bit better if you do it in radians, because it should be in radians. You're going to get as close to pi over 2 as you can. So this is just pi over 2. So actually this integral is quite nice. The integral from 0 to infinity of 1 over 1 plus x squared, it's pi over 2. Lovely, delicious, delectable question. Cool. Okay. On to question 65. Question 65. The integral, this one's funny. Actually, I'm going to do this on a new whiteboard again, guys, because otherwise it just gets really slow. Question 65. The integral of sec of kx. And this is again where k is not 0. So the trick for this one, it kind of seems like you're pulling it out of nowhere, but it's actually to rewrite this as sec of kx, and you times it by, again, not very obvious, but you times it by sec of kx plus tan of kx divided by the same thing. So you're only multiplying it by the number 1. So you're not actually changing the value, but this is a very nice little trick to do this. And the reason why this works, you're about to see, is now you've got the integral of sec squared of kx plus sec kx times tan kx over sec of kx plus tan of kx dx. You might say, okay, great, what's the big deal? Like, I don't see what the, what's happened there. But sec kx differentiates to sec, or is related to sec on its own, differentiates to sec times tan. And tan on its own differentiates to sec squared. So the denominator differentiates to the numerator, or close enough. So again, this is going to be the natural log of the denominator okay, and you might say, okay, but what about the constant? If you differentiate sec of kx, you're going to get k times sec of kx tan kx. If you differentiate tan, and that should also have a k there, if you differentiate tan of kx, you're going to also get k times sec squared of kx. And there isn't a k up there, so we should have a 1 over k out here. So it's 1 over k times the natural log of the absolute value of sec of kx plus tan of kx plus c. Pretty crazy. Pretty crazy stuff for the jungle. And that was question number 65. Question 66. Making good progress. The integral of cosec of kx, okay? So again, a very, very similar trick where we rewrite it, timesing it by 1 in a very, you could say, a very elaborate way. So it turns out if we multiply the top and bottom by cosec kx minus cot of kx on the top and on the bottom, it's gonna be very good. And again, you will see why in just a moment. So it's going to be the integral of cosec squared of kx minus cot kx times cosec kx divided by cosec kx minus cot kx. Okay, cool. Lovely, lovely, lovely. Now, you might know that cosec differentiates to minus cosec times cot, or minus cot times cosec. So once again, that differentiates to that. You might also know that cot differentiates to minus cosec squared. So minus cot differentiates to positive cosec squared. So yet again, it's a case of having the natural log of the denominator. So it's going to be the natural log of cosec kx minus cot kx plus c. And again, you're going to get this k come out, so we need a 1 over k here. And also we have to be, do we have to be careful? No, I think that is just the answer. I'm just going to check my notes again. I literally did this whole thing the other day. No, that is just the answer. That's all it is. That's all it is. Okay, cool. Hopefully everyone is pretty happy with all of this so far. Okay, pushing on. Number 67. Number 67, we've got the integral from minus infinity to 1 of x squared e to the x cubed. So again, this is an improper integral. So we need to do the limit as t approaches infinity of the integral from minus t to 1 of x squared e to the x cubed. Okay. And then we need to think about how we're going to actually integrate it. Okay. Now I'm proposing that the integral here is going to be e to the x cubed, because if you differentiate e to the x cubed, you get 3x squared e to the x cubed. And we need to divide it by 3. So now when you differentiate this, the 3 and the 1/3 cancel, so you do just get 1 lot of x squared times e to the x cubed. And that's between minus t and 1. So we've got the limit as t approaches infinity of 1/3 e to the 1 minus 1/3 e to the minus t cubed, like this. Okay. And we can do one more step of simplifying this before we actually write down the answer. 1/3 e to the 1, that's just 1/3 e. And then minus t cubed is just like minus t cubed. So it's minus 1/3 e to the minus t cubed, like that. And guys, as t goes to infinity, e to the minus t cubed is going to go to 0 very quickly as well. So this is just going to be 1/3 e is the answer. Just 1/3 e, because again, as 1/3 e to the minus t cubed, sorry, as t goes to infinity, 1/3 e to the minus t cubed is going to go to 0, which is just going to delete that term. All right. Next one, question 68. Question 68. And I'm just gonna do a quick status check on the live stream. Yeah, it's all every now and then. I've just got to check it because sometimes it freezes and stuff. Okay, cool. All right, this one is the integral of 1 over the square root of 25 minus x squared. So we did do a very similar question, but it wasn't 25, it was the number 1. So the question is, what do you do now? So it's the same substitution, but not just x being equal to sine u. You want x to actually be 5 sine u, because when you rewrite it, you're then going to have 1 over the square root of 25 minus, and then when you square this, you're going to have 25 sine squared. And the clever reason behind why you want to do that is because they're the same number, so you still have a multiple of cos there. Otherwise, if it wasn't 25 minus 25, you wouldn't be able to pull out a cos. It would be a mess. And we already know that dx is going to be 5 cos u du. So we've got 5 cos u du there. And again, this is super nice because you've got 5 cos u, and then this whole thing here is 5 times the square root of 1 minus sine squared, if I take the 25 outside of the square root. And again, this thing here is just cos u. So it ends up just being the integral of, again, literally the number one. Super nice. And that's just obviously u plus c. And the only extra thing here is that trying to get u on its own. So just to be clear on this, to get u on its own, you would divide both sides by 5. So x over 5 is sine u. And then u is inverse sine of x over 5, or arc sine of x over 5. So the final answer to this is that we have arc sine of x over 5 plus c. Just to zoom out a little bit there so you can see that. That is our final answer. Hopefully everyone's happy. All right, the glorious 69. Okay. Question 69. This one's actually harder than it looks. So the integral of 1 over 3 plus 4x squared. Okay. Right. So it's difficult because the 3 and the 4 are not the same number. If they were the same number, it would be a lot easier. But unfortunately, they're not. So the question is, what do we do? Well, what I would do, there's several ways of exactly approaching this, but what I would do is I would factor out 1/4. So I've got 1 over 3 over 4 plus x squared. Okay, you could factor out a third. Maybe a third would maybe be better. And then I would say, well, remember, guys, remember the integral that we did earlier. Remember that the integral of 1 over 1 plus x squared is very much doable. That's arctan x. We know that. So I would do a substitution that turns my integral into that. Okay, so I would think about this a little bit, and I'd go, okay, well, I want to let something give me like 3 over 4. Like I want there to be 3 over 4 tan squared u where the x is. So I should let x be the square root of 3 over 2 times tan u. Okay, and again, you'll see why this works. So it's, zoom out a little bit. So it's going to give you 1/4 integral 1 over 3 over 4 plus, and then x squared is going to give you 3 over 4 tan squared u. Okay, that's the kind of clever part of this. And because the 3 over 4s are the same, we're very happy. Now, also remember that dx would be root 3 over 2 sec squared u du, because the derivative of tan is sec squared. Okay. And so just moving everything, let's do the root 3 over 2 on the outside. We've got root 3 over 8 times the integral. And I would also probably take out the 1 over 3 over 4. So like this is 4 over 3 times 1 over 1 plus tan squared u times sec squared u du. And then we've got 4 root 3 over 24 times the integral. And remember, guys, 1 plus tan squared is sec squared. So this is just the integral of 1 du. Okay, so it's 4 root 3 over 24 times u plus c. And 4 root 3 over 24 is just root 3 over 6. And u is a bit tricky to get. So let's work out what u is. Okay, so again, this is going to be, so we've got that 2x over root 3 is tan u. So u is inverse tan or arctan of 2x over root 3. You could rationalize the denominator if you really wanted to, but that's what we're going to get. Okay. And so if I just replace that, we've got root 3 over 6 times arctan of 2x over root 3 plus c. So yeah, very crazy stuff. But nonetheless, hopefully everyone is pretty happy with that. So again, it's a question that looks actually quite easy, but it's not. It's quite a difficult question. Okay, on to question number 70. Big 70. So this is going to be the integral of log base 10 of x. Okay, pretty cool, pretty interesting question. So this is the idea, okay? What I would do is I would do integration by parts, just like if I was doing the integral of the natural log of x. So I'd say that u should be log base 10 of x, and I would say that dv dx should be the number 1. So v is x. And then the question is, what is the derivative of log base 10? That's quite weird. You may well have gone through all of your maths education without even knowing that or even considering it. So let's just do this on the side here. Let's say that y was log base 10 of x. If we raise 10, or raise both sides to as a power of 10, we've got 10 to the y equals 10 to the log base 10 of x. So 10 to the y equals x. Using implicit differentiation, we can say that the derivative of the left-hand side is 10 to the y times the natural log of 10 times dy dx, and that's equal to 1. Then dy dx is equal to 1 over 10 to the y times the natural log of 10. Okay. Now, we don't really want y to be in this. We know that 10 to the y is just x. You know, it's written here. So this is equal to 1 over x ln 10. Okay. So that means that this is 1 over x times the natural log of 10. Okay, so our integral is going to be x times log base 10 of x minus the integral of basically just the number 1 over the natural log of 10 dx. And that is x times log base 10 of x minus x over the natural log of 10 plus c. That simple. Well, I say that simple. A very difficult question, all things considered. But hopefully that makes sense. All right, that was question 70. Let's go make a new whiteboard again and go straight into question 71. Hopefully everyone's enjoying the video. I know that it's quite crazy. 100 is actually a big number. So we're doing the integral of v plus 1 over v squared plus 1 dv. Again, it seems to be maybe quite an easy question. The problem with this is it's not going to be explicitly a natural log because the derivative of the denominator is just 2v, and there is a v in the numerator, but then there's the plus 1, which messes it all up. Okay. Sorry, I just need to clear my throat. It is it's very drying. It's a very drying experience to talk this long. So the clever thing that we can do here is we can split it up into v over v squared plus 1 over v squared plus 1 dv and do the integral separately. Now, the first integral, because we're on Kong level now, guys, I'm going to assume that everyone's pretty directly happy if I just actually say that this is going to be, the first one is a half the natural log of v squared plus 1. Because if you differentiate the natural log of v squared plus 1, you'll get 2v over v squared plus 1. So the 1/2 is there to cancel. And then 1 over v squared plus 1 directly integrates to arctan. There it is again, arctan of v plus c. So that would be the answer to that one. And obviously the v is just there to throw you off. Like instead of x's, it's just v's because like why not? Why not? Sometimes you just need a v to keep you going, you know? Okay. Number 72. The integral of 1 over the square root of a squared plus x squared dx. And this is where a is greater than 0. Okay. Interesting looking question. You might be thinking, maybe do I do a trig substitution? No, it won't really work. But there is something that's like trig adjacent that we've already looked at that might work. And that is that you should actually let x equal a sine u. Okay, we're going to use hyperbolic trig functions. Now, I'm not going to go into all the details as to like why exactly this works, but it's true that instead of cos, cos squared plus sine squared is 1, the hyperbolic version of that is cos squared minus sine squared is 1. So it's a minus. And the good thing about this is that it means that cos squared is 1 plus sine squared. And you can see that we basically have like something squared plus something squared. So that's why it kind of works. So we already know that sine differentiates to cos. So we've got a cos u du there. And so that integral is the integral of 1 over the square root of a squared plus a squared cos squared, it's not cos squared, a squared sine squared. I like your funny words, Magic Man. That's how I feel right now. I feel like I'm casting spells. And then dx is a cos u du. There we go. Okay, and that's going to be the integral of, so we've got a cos u du divided by, and then I'm going to take the a out here, so a times the square root of 1 plus sine squared u du. And the a's cancel. Okay, and remember guys, 1 plus sine squared is cos squared. So the square root of 1 plus sine squared is just cos. So again, it's cos over cos. So this is the integral of the number 1, which is just u plus c. And we said the x was a sine u. Okay, meaning that u on its own would be r. Let me try that again. R sine of x over a, and if you've not deduced it, r sine is the inverse function of sine. Okay, it's not arc sine, it's r sine. Okay, don't ask me why. I know, but don't ask because it will take ages. Absolutely ages to explain. Okay, right. So this integral, let's rewrite it for dramatic effect. The integral of 1 over a squared plus x squared dx is equal, believe it or not, to r sine x over a plus c. And r sine has a nice definition in terms of logarithms and stuff like that, but we won't go into the weeds on that one. Okay, that was question 72. We're still on Kong level, guys. We're still on Kong level. Question 73 is next. The problem is, as these questions get harder, they take longer, of course. And that's great, but I'm going to be here all night. But hey, can't complain. All right. Question 73. We want to do the integral of 1 over a squared minus x squared. Okay. And again, this is where a is greater than 0. Okay. So for this one, again, we're going to let x equals a than u. So another hyperbolic trig substitution, and it simply turns out that this works really well. So dx du is going to be a, and than differentiates to sec squared. So a times sec squared u. Okay, a times sec squared u. Okay, and I think, do you know what, with this one, I think I'll very quickly explain that. So than, the derivative of than, the derivative of this is basically sine over cosh, sine x over cosh x. Using the quotient rule to differentiate this, the quotient rule, it's u over v, and it's du dx times v, so cosh squared, minus dv dx times u, so minus sine squared, divided by the denominator squared, so divided by cosh to the 4, cosh to the 2, what am I on about, squared, losing my train of thought. And so this ends up being 1 minus than squared x. And again, out of nowhere, we've got this formula that cosh squared, we already know that cosh squared minus sine squared is 1. So if we divide everything by cosh, or divide everything by cosh squared, we've got 1 minus than squared is equal to sec squared. Sec is just sec is the reciprocal hyperbolic trig function for cosh. So sec is 1 over cosh. Okay, just to be clear. But I guess you can kind of gather that or deduce that. Anyway. Okay. Right. Then we've got the integral of 1 over a squared minus a squared than squared u. And again, dx is a sec squared u du. And again, like 1 minus than squared is sec squared. So this is the integral of, we've still got the 1 over a there. But other than that, that's it, because it's just sec squared divided by itself. But there's also the 1 over a. And so this is going to integrate to u over a plus c. And remember, we said that we said that x was a than u. So u is x is inverse than. So r than of x over a. Okay, so the final answer for this is that the integral of 1 over a squared minus x squared dx is 1 over a r than x over a plus c. Just to be clear with this one does not actually require this substitution, because you can do it with partial fractions, because a squared minus x squared, where a is positive, is always factorizable, because it's the difference of 2 squares. So it's a minus x times a plus x, and then you can do partial fractions. It turns out, because of the definition of r than, they both give you the exact same answer. Just to be clear, they both give you the exact same answer. All right, cool. Hopefully everyone's happy with number 73. On to number 74. And we're almost 3/4 of the way there, kind of. So number 74 says, this is the integral of arc sine x. Okay, so again, this one is an integration by parts. So we're going to let u equal arc sine x. We're back to normal trig functions. And dv dx is just going to be the number 1. So that du dx is 1 over the square root of 1 minus x squared. Remember, the integral of 1 over 1 minus the square root, the integral of 1 over the square root of 1 minus x squared is arcsine. So it makes sense that that would be the derivative. And so v is x. Okay, cool. And then just by using the formula for integration by parts here, we have got that it's x arcsine x minus the integral of x over the square root of 1 minus x squared dx. Okay, and that's going to be x arcsine x. And then this integral here, you can do it by a substitution. You can let u equal 1 minus x squared and it will work. But it's just going to be 1 minus x squared to the power of a half. And if you differentiated this, you get a half times minus 2x. So that's just minus x. So it works. So that just needs a plus and that just needs a plus. There we go. That's maybe the lazy way of doing it, but there we go. And, final answer for the integral of arcsine, just to write it nice, it's going to be x arcsine x plus the square root of 1 minus x squared plus c. There we go. So I kind of BS'd my way through the very last integral there, but you can do it by substitution. It's fine. All right, cool. That's 74. 75. 3/4 of the way there. This is the integral from 0 to 1 of arctan x. Okay. So what are we thinking about this? Well, again, we're going to do integration by parts. U is arctan x. And dv dx is just the number 1. So du dx is 1 over 1 plus x squared. Remember, the integral of 1 over 1 plus x squared is arctan. And v is x. And so this is just going to be x arctan x from 0 to 1 minus the integral from 0 to 1 of x over 1 plus x squared. And if we actually plug into the first thing, we've got x arctan x at 1, so 1 lot of arctan of 1, so arctan of 1, and then obviously minus, it's just minus 0. And then this integral, this is a half, I think we've done this one already, half the natural log of 1 plus x squared from 0 to 1. Arctan of 1, you could verify on your calculator. In radians, it's pi over 4. Minus, and then this thing here is a half the natural log of 2 minus a half the natural log of 1. So it's pi over 4 minus a half the natural log of 2, because the natural log of 1 is just 0. So it's a very nice answer, actually, the integral of arctan x from 0 to 1. It's pi over 4 minus a half the natural log of 2. Green Pudding says, is arcsine just sine to the minus 1? Yeah. So if you write like sine to minus 1, it means the same thing as arcsine. That's absolutely right. Yeah, 100%. Okay, that was question 75. Question 76. This one's fun. So we want the integral of sec cubed. So the trick here is to rewrite it as sec squared times sec one more time. Like that. So sec cubed is sec squared times sec. And then you do integration by parts, because sec squared has a nice integral and sec has a nice derivative. So u can be sec because it has a nice derivative. And dv dx can be sec squared because that's easy to integrate. So du dx, the derivative of sec is sec x tan x, and the integral of sec squared is just tan. Okay. Now, if we, where shall I do it? Okay. If we use the formula for integration by parts, we're going to have sec x tan x minus the integral of sec x tan squared x, like that. And you might say, ooh, that's not great, but this is sec x tan x minus, and then the interesting thing is that, remember guys, I'll write it down again, 1 plus tan squared, we've used this a few times now, is sec squared. So tan squared is sec squared minus 1. So this is sec x times sec squared minus 1. So we've got sec x tan x minus basically the integral of sec cubed again, and then minus the sec, but it's also minus, so like that's dx, plus, let me rewrite that because that's actually really bad, very, very gross, dx plus the integral of sec x. Okay, and we've just got that by expanding it out, because it's sec times minus 1, but there's already a minus in front of the entire integral. Okay, so just to write out what we've got here, again, if I label the integral of sec cubed, if I just call it I, just as a shorthand, we basically have that I, oh, let me put it in white, I is equal to sec x tan x minus I plus, and then the integral of sec, we've already done that one, it's the natural log of sec x plus tan x. And again, we've got this thing where like the integral is this like self-referential situation. So if I add I to both sides, I've got that 2i is sec x tan x plus the natural log of sec x plus tan x plus, and I'll do the plus c at the end actually, and then you just half both sides. So I is half sec x tan x plus half the natural log of sec x plus tan x, and then plus c on the end. I'm cool 123 says, I have a small understanding of what I'm looking at right now, but I do know some simple trig and calc. That's good. I mean, I'm cool. Because the whole thing here is like we're doing, the integrals are getting progressively more difficult. So, I mean, it's up to you, but I've been going for almost 3 hours. If you want, feel free to go back to the beginning of the video, because you'll maybe, if you're familiar with some calculus, you'll be happy with some of the beginning stuff. So the idea with this is like everyone can find their level and you can find a good sweet spot. I've organized the questions in terms of difficulty. I've like, as you can see here, I've put them in terms of 5 different monkeys. So you might be curious, George, that's the first 24. I don't know how easy it is to actually see those integrals that are written there, but they're quite easy. I've done all of these. Bantu was another gorilla, a real gorilla, like Harambe, slightly harder. King Kong, even harder. We're currently on King Kong actually. We're on we just did question 76. So we just did sec cubed, and we're still going, and the next difficulty level is going to be Caesar, and then it's going to be Harambe. So we're going. But that's the idea. So, but I really appreciate everyone watching. I really appreciate it. Okay. So that was the answer to that. Let me just make sure, just check my notes. As I say, I literally did this whole quest. I did all 100 questions yesterday in a Starbucks. It was tough. I mean, I'm doing it now as well, so it's tough now, but we're going, we're strong. Got my coffee. Guys, at 6 p.m. UK time, I'm going to have to go because I've got to take a free meeting with someone that I'm potentially going to be tutoring, but I'm going to be back. I'm not going to leave the live stream. I'm just going to mute my mic. It should only take 10 minutes maximum, and then I'll be back just to let you guys know, because I don't want to do a separate live stream, guys. We want to do this all in one go, even if it takes me 4 hours, which it very well could do. I don't care. Like, we're doing it. Okay, question 77, and I'm actually gonna again make a new whiteboard tab. The calculus major does not concern himself with basic arithmetic. Hell yeah. Hell yes. I love it. I love those lion memes. One of my YouTube thumbnails is the lion. I did sine of 15 degrees without a calculator, and I put on the thumbnail, the lion does not concern himself with a calculator. Am I a gorilla? Am I a lion in this scenario? Who knows? Who knows, guys? But what I do know, yeah, is I'm the king of the jungle, yeah. Sorry, that was a bit embarrassing. I said it ironically, so hopefully that's fine. Okay. Right. Yeah, question 77. So question 77. This is going to be the integral of the natural log of x squared, like this. So it's the natural log of x and then squared, using the trig notation, like sine, sine squared, like using the same notation, the natural log of x and then squared. So with this one, again, you just want to do a substitution. So you've got u equals the natural log of x. So du dx is 1 over x, meaning that dx is x du. Cool. So that means that we've got the integral of u squared times x du. Okay, and x in this scenario, if we just rearrange this, x would be e to the u. So we've got u squared times e to the u du. Now, slightly annoyingly, that means that we have to do integration by parts twice. But guys, I'm going to use, I was going to use the DI method, which is when you just basically run through it really quick. But no, I'm going to do it properly, actually. So, right, we're going to say that, and by the way, guys, I'm just going to do a trivial little substitution. I'm just going to say let t equal u, so that I can just rewrite the whole thing in terms of a different letter. Just because I'm about to do integration by parts, and I want to label it u and v. I don't really want to be labeling let u equal u and all that stuff. So I'm just going to turn it into t's. So now I can say, so now we're doing this integral here. I can say that u is t squared and dv dt is e to the t. Okay. Otherwise it'd be like let u equal u squared, and I just, no. Okay. Cool. So just using all of that. And then we've got, this is t squared e to the t minus the integral of 2t e to the t dt. And we need to do integration by parts on this. So let u equal 2t, let dv dt equal e to the t, du dt equals the number 2, v equals e to the t. So this, like the whole thing overall, is going to be t squared e to the t minus, and then in brackets, we've got 2t e to the t minus the integral of 2e to the t dt, like that. Okay, so this is t squared e to the t minus 2t e to the t, and then plus this integral. And this integral is 2e to the t plus c. And remember, we said that t was the same thing as u, and we said that u was the natural log of x. So the final answer, the integral of the natural log of x squared, is the natural log of x squared times e. Well, not the final answer. We'll simplify it even more in a second. Replacing all the t's with ln. Like this. Okay. And e to the ln x, guys, we all know it's just x. So this is going to be x times the natural log of x squared minus 2x ln x plus, and just plus 2x plus c. And that would be the final answer. And that was question number 77. And again, I'm just checking that I've not made a mistake. No, that's correct. That's correct. Blimey. You are the gorilla against the integrals. Yes. Thank you. Thank you. Thank you, Green Pudding. Okay, that was question 77. Question number 78. The integral of 1 over x squared plus x cubed. Okay. So guys, with this one, we want to use partial fractions. So we rewrite it as 1 over x squared times 1 plus x. Like this. Okay. Then let's work this out. So just what is this in terms of partial fractions? So we need to set it equal to, let's go a over 1 plus x plus b over x plus c over x squared. That's how this works. So if you have a repeated factor, you've got to include a bracket or a fraction for each power of that repeated factor. That's just the way that it works. Then we times everything, both sides, by x squared and by 1 plus x to get rid of all the fractions. So we get this. Okay. And now we need to work out what a, b, and c are. So I'm going to let x be the number 0 so that I get 1. So that's going to get rid of a and b. And I just get 1 equals c times 1. So c is the number 1. I'm also going to let x be equal to minus 1. And that's going to give me 1 equal, because that's going to get rid of the b and the c. So it's going to give me 1 equals a times minus 1 squared. So a is also equal to the number 1. And then there's nothing else that I can choose to like get rid of something. But what I can do is I can let x equal just a really simple number like the number positive 1. And then I've got the equation 1 equals 1a. So just 1. A is the number 1. Plus, and we don't know what b is yet, so plus b times 1 plus 1, so times 2 times 1. C is also the number 1, so just plus basically 2, because it's 1 plus 1, and then times 1. So 1 is equal to 3 plus 2b. So minus 2 is 2b, so b is minus 1. Okay. So now I can come back up here and I can rewrite my integral as we said that a was the number 1, so 1 over 1 plus x. B was the number minus 1, so minus 1 over x. And c was the number positive 1, so 1 over x squared. Okay, and then we can rewrite this as the natural log of the absolute value of 1 plus x minus the natural log of x. And then remember, this is x to the minus 2. So it integrates to minus x to the minus 1, like that. And then I'm going to combine the logs. So I'm going to write my final answer as the natural log of 1 plus x over x in absolute values minus 1 over x plus c, just like that. Okay, hopefully that makes sense to everyone. Who's your favorite mathematician? For me, it's Feynman because he taught himself calculus from scratch. That's a lot of dedication. I'm called 123. That's an amazing question. I've never actually thought about who my favorite mathematician is. I think I don't want to ruin your, by the way, I don't know if you know what Feynman's trick is, but later in this video, I think it's like integral number like 98 or like 96 or something. It has something called Feynman's trick. which you might know about. It's an integration method, actually. So coming up later in this live stream, we'll get to it in, I don't know, 45 minutes to an hour probably. I'm going to be doing Feynman's trick. So yeah, not to ruin your impression of Feynman. He was a pretty good mathematician, I think. He didn't do anything like ridiculously good as a mathematician. He was also a physicist, and he was a very good physicist. He had a weird habit, though, of sleeping with his students. I mean, none of them were underage, but he did sleep with his students quite a lot. That's a real thing. And he was probably a bit of a narcissist, but also, I mean, who's not? If you're like, I mean, he was probably a genius. Like, who wouldn't be, right? So I'm not going to diss Feynman. He's pretty good, and in physics, he's super influential. So, I mean, he has a Nobel Prize. He's a good physicist, I think, or he was. So yeah, where did you get this information? What like which part of it? Green pudding. The fact that he slept with his students, or like, I mean, it's just I don't know. I'm not sure where I got it. It's like fairly. No, I don't want to call it common knowledge, but I just know this stuff. I mean, I've read books and things, I guess. But yeah, he's pretty good. Who's my favorite mathematician? What I'll do, guys, is I'm going to answer this question, and then again, I'm going to go for about 10 to 15 minutes. We're going to take a break. The live stream will stay up, okay? But I've got to go and take a meeting with someone that I might be about to tutor. So I'm going to have a meeting with them in any minute now, and then I'll come back, okay? And we'll continue. So don't go anywhere. But yeah. So like I don't know if he was like morally the best guy, Feynman, but do you know what? He was pretty good. He also, this Feynman's trick, he didn't actually invent it. That was a very famous mathematician called Leibniz. Leibniz came up with it, but Feynman repopularized it. He says that he found it in like a not very mainstream textbook and like repopularized it. So that's pretty cool. Anyway, who's my favorite mathematician? I have several mathematicians that I really like. Do you want to know who I think is actually the best mathematician of all time, or who do I think is like? I'll tell you what. I'll answer all of them. I think Euler is probably the best mathematician of all time. Leonhard Euler. It's a pretty basic take, but I mean, this guy. He has his grubs on every single aspect of maths. Every area of maths. Leonhard Euler is the guy. Like, he's goated. He is goated. He's goated status for sure. Who do I think is underrated? I think Lagrange is an underrated mathematician and physicist. He's still very well known, don't get me wrong. Yeah, Joseph Louis Lagrange. He is incredibly influential in like mathematical mechanics and in physics, and in economics. Like, he's everywhere as well, Lagrange. But people don't really say him in the same breath as like Euler and Newton and stuff like that. So Lagrange is pretty underrated, I would say. And I'll give you one more person that I think is pretty. I'm trying to like juggle. I think there's quite a lot of people that are really, really good. I think no, I'm just going to rattle off a few. Archimedes. This guy lived in like the like 200 BC, and he got shockingly close to inventing calculus. And it took another almost 2,000 years for it to actually happen. But he was a few good ideas away from inventing calculus, about 2,000 years before it actually was. So Archimedes is definitely up there. And Archimedes was like, especially for his time, he was unbelievably good. And then one more mathematician that I think is really, really important. Not necessarily like the best of all time, but a really important mathematician is Cauchy. I think Cauchy, for like analysis and that kind of thing, is hugely important. He was a colossal step from mathematics and calculus being quite unrigorous to making it rigorous. the idea of a Cauchy sequence, the idea of like the epsilon delta definition of convergence, and all of that stuff, you could attribute it to Cauchy. Not only him, there's people that did huge legwork as well, like Weierstrass and Leoville. I'm trying to think of other people, but it was a huge team effort. Riemann as well, but there's a lot of people. Yeah. I saw this joke about Euler that we name a discovery in mathematics after the second mathematician. Yeah, I know. I already know what you're going to say, because it was always Euler who kept getting the discovery named after him. Well, the problem is that I don't even know how many mathematical theorems there are that are basically called Euler's theorem. There are so many Euler's theorems for every area of maths, because this guy just published, countless bits of mathematics for his entire life. And I might be wrong, but I'm pretty sure that people are still digging through all of it to figure out what he did. So Euler is, like, for me, he's the best mathematician of all time. He's number one. I really do think he's number one. Just no one else in all of like maths had the reach that he did. There are people that revolutionized their own field, like their own, people like Lagrange that revolutionized mechanics, and even Newton, like calculus. But Euler just did everything. He just did everything, and no one else really did. A bunch of mathematicians discovered Pythagoras' theorem before Pythagoras. Yeah, and Pythagoras isn't even necessarily a real person, and I don't consider Pythagoras to be a good mathematician, even if he was a real person. There's a rumor that it was actually a group of people. I don't consider him to be a good mathematician because, one, you're absolutely right, and two, Pythagoras was not in the game for his enthusiasm with maths. Pythagoras hated the idea, for example, of irrational numbers. He didn't believe in them. The story goes, as to whether it's true or not, the story goes that he killed someone because they proved that the square root of 2, which is a number that you can easily make with a Pythagorean triangle, 1, 1, root 2 on the hypotenuse, this guy Hippasus proved that the square root of 2 is irrational, and the story goes Pythagoras threw him off a boat and killed him. Are you pro or anti education, information, knowledge if you kill someone because they make a discovery? Like, I'm sorry, but you're not even, I don't even consider you to be a good mathematician, let alone one of the best. Yeah, he had no chill. Yeah, he allegedly he killed someone. But that's just me. Anyway, guys, I'm gonna go for about 10 minutes, and I'm gonna be back, and we're gonna finish this off. Okay, so I'll see you guys in about 10 minutes time. Okay, guys. Jump scare. I'm back. I'm cool 123 has left us, unfortunately, but that's okay. Welcome to myself, because I've just joined. Welcome to everyone else who's just joined the live stream. Nice to have you here. We are going through 100 integrals. In this situation, you can see the background. I'm in the real jungle. Hello, green pudding. I'm in the real jungle. I am the gorilla in this scenario. All right, because I'm facing 100 integrals. Excuse me. We were just debating who's the best mathematician of all time. Okay. And someone says, what's 18 plus 22? I don't know exactly what that means. I know that 9 plus 10 is 21. So I think that kid is maybe the best mathematician of all time. No, I'm just joking. I'm just kidding. So, I feel slightly energized. I feel energized. Let me just meditate. We can go back in. It's going to be a long one, guys. We've currently been going for 3.25 hours. I'm getting myself an Indian takeaway after this. I don't give a shit. Oh, shouldn't have sworn. Sorry, guys. Sorry. I genuinely was like shocked at myself. I try and keep it family friendly. Not that anyone actually cares. No one cares. Guys, you don't care. You don't care. But still, I don't like swearing. Not on here. Anyway. Oh, making funny noises. I swore in front of my mum by mistake the other week when I was visiting my family. I just casually dropped the most diabolical F-bomb. I like almost jumped out of my own seat because I live in the kind of family where it's like, it's just a bit like weird to like swear in front of my parents, kind of. So yeah. But anyway, they found it funny. All right. Anyway, guys, let's go back in. So we just finished question 78. So you know what that means. It's time for question 79. It's the only possible conclusion. Question 79 is a fun one. So question 79 it's going to be the integral from 0 to n of what you call the ceiling function. Oh, let me draw that properly. The ceiling function of x. And this is, just to be clear, this is where n is a natural number. Okay. Just to be clear on what the ceiling function actually is, the ceiling function just rounds x up to the nearest integer, okay? But it rounds it up every time, okay? So, for instance, the ceiling function of 0.1 would be the number 1. Okay, the ceiling function of 5.99 would be 6. The ceiling function of minus 2.1 would be minus 2. Like it's rounding it up to the nearest integer. Okay, that's the idea. And I don't know what it does actually. I think if the number is already an integer, it doesn't matter for this question, but if the number is already an integer, I don't know, like conventionally, I don't know what it does. It doesn't matter what it does when the number is an integer for the question, but just out of curiosity, just to explain it, I will have a look now. Let's have a look. So it will round. No, it just keeps the number how it is. So for instance, the ceiling function of like the number 2 is just 2. It looks like it doesn't round it up to 3. So it's just it rounds it up to the nearest integer. That makes sense that it would do that. Lovely. Now the question is, what's the integral? You might say, oh my god, because it's kind of a weird function. But actually it's not that difficult, because if I just draw a diagram of what's actually going on, Okay. Well, it's going to look like this. Okay. So 0, the ceiling of 0, the ceiling function of 0 is still 0. Okay. And then it's going to go along. There's 1, 2, 3, 4, 5, etc. And it's just going to do this. So, and let me do this. 1, 2, 3, 4, 5, etc. That's the x-axis. That's the y-axis. And so, yeah, it's just going to do this basically. Okay. And just to be clear, the filled in circle means that it's including that number. And when it's not filled in, it means that it is excluding that number. But actually, I think I might have drawn it a little bit wrong because let's see. No, so it's actually, they've done it the other way around, which is fine. Let's just make sure we get this right. Again, these endpoints don't actually matter, but it's more of a case of like, I just want it to look accurate for you guys, and I don't want to ever tell you guys anything incorrect. So just do this now. So these end values are filled in like this, and on the left hand side, it's like this. Okay. So what this means is when x, for example, is exactly an integer, yeah, that makes sense that it's that way around. It leaves it how it is. So it means that because it's doing these like instant, like these discrete like jumps up. When x is exactly the number 2, it stays at the number 2. It doesn't go up to the number 3, which is what we said earlier. But this is the idea. This is what the graph of the ceiling function would look like. If it's already an integer, then the ceiling /4 doesn't do anything. Thank you, Green Pudding. Thank you. I appreciate that. I appreciate that. Sorry, I know that you said that like 3 minutes ago, but I only just saw it. But you're absolutely right. Okay. Now, we can see, guys, that the area underneath the graph when x is the number 1 is 1. The area underneath the graph from 0 to 2 is 1 plus 2. When x is 3, from 0 to 3, it's 1 plus 2 plus 3. And then it's 1 plus 2 plus 3 plus 4. And then it's 1 plus 2 plus 3 plus 4 plus 5, etc. So up to n, it would just be that all the way up. So this integral is actually equal to the sum from r equals 1 to n of just r. Okay. So the integral is actually a sum. And we already know what this is, guys. This has a standard formula of n over 2 times n plus 1. Or, curiously, it's n choose 2. Kind of a coincidence, I guess. But it's equal to n choose 2. So, for example, if n was the number 10, it'd be 10 choose 2. If n was the number, I don't know, 4, it'd be 4 choose 2, etc. So the answer to this is it's n choose 2, or n over 2 times n plus 1, believe it or not. Fun. This is actually a very important concept in real analysis, because the floor function or the ceiling function are used to construct the idea of a regulated integral. And a regulated integral is basically a Riemann integral. It's a very important concept, using partitions and stuff like that. It's a step function. So what are you doing, step function? No, bad. It's a step function. So that's the idea. It's a step function, and any if I'm remembering right, any integral that's like Riemann integrable, can be like approximated with step functions or something like that, or like using regulated functions. I don't know. Anyway, this might sound like kind of a stupid question, but actually it's very important. Okay, that was question 79. That was question 79. Okay, question 80. Question 80. Right. We're doing the integral of 2 to the power of sine x times cos x, like this. So this one's very curious. We did the same integral earlier, but with e instead of 2. And so the idea is if we differentiated 2 to the power of sine x, we would get cos x times 2 to the power of sine x times the natural log of 2, okay, by the chain rule. If you wanted to do this like the proper way, you would let u equal sine x, and it would so happen, that's what you'd get. So again, we have what we want, but we have this extra ln2 that we didn't want. So it means that this integral is equal to 2 to the power of sine x divided by the natural log of 2 plus c. Okay, that's the idea. Cool, that was question 80. 20 more questions. Question 81. Question 80, and we've almost finished the King Kong questions, by the way, guys. Question 81, it's the integral. We've already done arctan, but this is going to be x arctan x. Okay? Right. So, once again, we're going to use integration by parts. So let u equal arctan x. And let dv dx equal x. So du dx is equal to 1 over 1 plus x squared, because that's what arctan x differentiates to, and v is a half x squared. Okay, and that means that this integral is going to be equal to a half x squared arctan x minus the integral of a half x squared over 1 plus x squared. Okay. Now we're going to use this this interesting little strategy that was used earlier that someone said that they liked. This is a half x squared arctan x. That bit's done. That's fine. And then the integral, I'm going to rewrite it. I might take the half out, actually. Take the half out. And I've got x squared over 1 plus x squared. So what I'm going to do is I'm going to rewrite x squared as 1 plus x squared minus 1. Okay, and again, you could just do long division on this, but that's lame. That's boring. So I've got half x squared arctan x minus a half, and then why have I done this? Well, 1 plus x squared over 1 plus x squared, that's just the number 1, minus 1 over 1 plus x squared. Okay. And this is very much a doable integral. So I've got x minus arctan x plus c. So a half x squared arctan x minus a half x plus a half arctan x plus c. So a bit of a mouthful, but that's okay. And that was, or am I tripping? Is that definitely correct? Wait, I've got a different, when I did this yesterday, I actually have a different answer. Let me just review what I've just done. The integral of x arctan x, it's okay. I think... No, I'm not sure what I've done. Half x squared arctan x minus a half, and then we've got a half x squared, yes, over 1 plus x squared. So a half x squared arctan x minus a half. Yeah, added 1, took away 1. Yep. That looks right to me. I don't see the issue. Someone says, finally, a mathematical live stream. Hell yeah. Look at that. That's the energy that we need today. Tanny's TI-84 Tolkien. Love it, mate. You're hyping me up now. That's crazy. You're hyping me up. We love a maths live stream, guys. We love it. Oh dear. Okay. I know that it's crazy, guys. I know that it's crazy. So, yeah, I don't know what's happened because this integral, like, I'm very sure that it's right, but I did it the other day, and for some reason, it's like the only question I've not done any working out for, which is great. Maybe I just asked Chat. I think this might have been the one that I just couldn't be bothered to do, so I just asked ChatGPT. Let's see what the chat is saying. Let's just check out ChatGPT for just a quick one. So I'm just going to tell it to integrate x arctan x. And we'll just see what it's saying. I think that ChatGPT was just wrong because I don't see... Does anyone, guys, anyone watching, does anyone see an issue if I just zoom out? Does anyone see an issue with any of my working out for this question, for question 81? Please let me know. Whilst ChatGPT thinks. For some reason, my ChatGPT is like super slow, so I don't really know. I feel like I've not made a mistake, but maybe I've just done something really stupid that I can't really see. Yeah, please do let me know, guys. I think it's fine. I think. I fear. Guys, sometimes crazy stuff happens in the jungle, which is where we currently are. Okay. Don't forget it. ChatGPT. Integrate x arctan x. And don't mess it up, bro. All right, it's thinking. Let's see what it's saying. No, I think I was right. It's a half x squared arctan x minus a half x plus a half arctan x plus c. It was right the whole time. I've written it down wrong, I think. Yeah, guys, I've written it down wrong. But that's what happens when you do a King Kong level integral. Didn't know ChatGPT could do math in a jungle. I'm going on my lunch break. Hey, all I'm saying is in the jungle, anything's possible, okay? And sometimes you need an AI, and there isn't one because it's a very coarse environment, like the jungle. And the jungle is very challenging. And sometimes you just need a grok in a hard place. And then I would drop the microphone, but I don't want to really drop it on top of my computer. Guys, come on. I'm literally the dad joke king. Grok in a hard place, bro. Let's go. Let's go. I hyped myself up again. All right. Question 81 was right. I didn't make a mistake. I made a mistake the other day when I did it. It looks like. All right. Next one. Okay. Question 82. Question 82. All right. What are we saying about 82? Okay. Question 82. We're doing the integral of x to the 7 times the square root of x to the power of 4 plus 1. Okay. Now, the trick for this one is that you should rewrite it as x to the power of 4 times x to the power of 3 times x to the power of 4 plus 1. Okay. The reason for this is because this is a reverse chain rule, and this is just chilling. And so you can use integration by parts. So you can let u equal x to the 4, and you can let dv dx equal x cubed times the square root of x to the 4 plus 1. Okay, that means that du dx is 4x cubed, and v, we have to think about it. So how are we going to do this? Well, all right, I think that it's going to be x to the 4 plus 1 to the power of 3 over 2, because this would differentiate to give me x to the 4 plus 1 to the half with a bunch of extra stuff too. If I differentiate this, then it's going to give me 3 over 2 times 4x cubed times x to the 4 plus 1 to the half, which is exactly what I had, but instead of just one lot of x cubed times the square root of x to the 4 plus 1, I've actually got 3 times, so I've got 6 lots of it. So actually this here is going to be 1/6 of x to the 4 plus 1 to the 3 over 2, because 1/6 times 3 over 2 would give you 3/12, so a quarter, and then timesing it by the derivative of the inside, x to the 4 plus 1, so that's going to be 4x cubed, the 4x cubed. It just does what it just does, okay? And then we can go ahead and rewrite the original thing as u times v, so a 6th x to the 4 times x to the 4 plus 1 to the 3 over 2 minus the integral of 4x cubed over 6, so that's like 2 over 3 x cubed to the power of x to the 4 plus 1 to the power of 3 over 2 dx. Okay, hopefully that makes sense. That's just du dx times v there, but I've written it as 2 over 3 rather than 4 over 6. Okay, all right. By the way, what's your opinion on the whole City Tutoring Math and Maths Sorcerer feud? Is there a feud? Wait a second. The ambient music is going crazy. Let me know, guys, if you want me to turn up or down the ambient music. I didn't know there was a feud because I know who both of those people are. Now, I think, okay, guys, let me give you my opinion. I'll keep it brief because maybe some people don't know who these people are. But the Math Sorcerer, they're both Americans. The Math Sorcerer makes YouTube videos about maths, believe it or not. I mean, actually, they both do. They're both maths YouTubers. They're both men in their 50s, probably 50s. And the Math Sorcerer seems to have pivoted to some like inspirational type videos, like very short videos. He'll do these ones where like he writes something on a whiteboard and then like holds it up to the screen as the thumbnail. And then like it just says like, be the best that you can, or like maths is hard, or like, I don't know, whatever. He holds it up and then he takes it away. The whole video is only like a few minutes long. And he's kind of all right. Like he's all right. But the Math Sorcerer gives me kind of like slight schizo vibes. I don't know if that's actually accurate or not. I don't really know. But yeah. But I feel like the Math Sorcerer is all right. Like he's actually got, I'm only joking when I say that he's got schizo, but like he seems like a pretty normal, nice dude. Yeah, like he seems pretty fine to me. Okay, that's the Math Sorcerer. City Tutoring, to be honest with you, I didn't actually know that he was like well known. I thought I was the only person that knew about him, because City Tutoring, that guy is freaky. Can I just say that? Can we all be honest with each other? That dude is freaky. Not to be rude or mean. Someone said, yeah, the duck with the monocle says maths is a not only for geniuses. Learn math to become a genius. Video. Yeah. He'll do that kind of thing. There's like 2 City Tutoring videos calling out the math sorcerer. I'm gonna go and check those out later. But that's really surprising to me that they like know each other. I guess the maths like YouTube world is like it's a pretty small world, I guess, but like still. But yeah. So the City Tutoring guy is a bit freaky. Like I really find him quite weird, if I can say that. He's just a bit like off-putting and weird. Like he has like the really posh guy demeanor, and it's very strange, and like his videos aren't that great, dare I say. City Tutoring made a blog broadly proclaiming make maths great again. Yeah, that guy, he's a Republican. I'm pretty sure that the City Tutoring guy is like, he's got some very I don't want to mischaracterize him. I may be wrong, but he's got some very traditional thoughts, or at least I get the idea of that from his videos. He's got some very he's an interesting guy, but he's kind of freaky. I don't like his vibe. I really don't like his vibe. He does have I've seen videos from the City Tutoring guy. In City Tutoring, like that's how he speaks. City Tutoring, maybe a slightly different voice, but that's my impression of like in City Tutoring. What kind of stuff does he say? I don't know. I first got introduced to him because I saw a video where he was like basically saying that, you know, 8th graders are like hopeless at maths, and like look at how easy their maths paper is, and like it was very conspiratorial. Thank you 199% voice. No, give me something. Give me the kind of thing that he would say. I'll say it. Like, what kind of thing does he say other than just that? It's so funny. Sorry, guys, I don't want to go on about it, because if people don't know who we're talking about, then that's a bit peak. But no, he does sound like that. But yeah, and he's also made but his videos are very like conspiratorial almost. Like they're very like the government has like done this, and you know, like kids these days just like look at there's like an implication in some of his videos that like how would you say it, like just that like maths is like going downhill, and like kids are like hopeless and they're getting dumber and like all that stuff. I don't really believe that. Oh, they don't teach calculus from Spivak anymore. Herder. I'm not gonna lie, I've never heard him say that. I do not know how he would actually say that, but yeah, I just feel like he would say like, and now wait, let me get into. And now we are going to look at a quadratic equation. Like that's probably the kind of at City Tutoring. Yeah, that's his voice basically. But no, I'm team. If this is like Captain America's Civil War, I'm team Math Sorcerer. You know what I mean? I feel like, you know, Math Sorcerer all the way. Anyway, that's great. I need to know about their beef. I need to know about their feud, because I really didn't think that they were like, I can't get enough of the voice. That's literally how he speaks. Like, honestly, yeah, it's crazy. Yeah. I'm not gonna keep doing it, but yeah, that's how he speaks. That is his voice. And I don't know what you think, but I think that he's kind of freaky. Like he's kind of weird. Like I don't want to say anything too bad about him, but I wouldn't take my kid to get tutored by him. I just think he's got weird vibes, to be honest with you. He's weird. Yeah. Don't know what to say. Just what a strange dude. What a strange dude. Yeah. Math Sorcerer started publishing AI generated maths books on Kindle Web Store. Mainly, it's been mocked on some of my math circles. Really? Wait, what are the do you know what the names of them are? I ran into an AI maths textbook. Maths Sorcerer AI textbook. What's the name? Oh wait, don't wait. It's low quality slob, didn't bother writing down the name. You know what? Let me just check something. This is a Reddit page. I've been a fan of the Math Sorcerer for a couple of years, and I even bought a signed book that he owned. He's been a great source of math information as well as a source of motivation. I think he genuinely does care about his audience and believes what he preaches. Wait, I won't read all of it out. I've clicked on his page. Oh my god. He's just going under his own name, I think. The Math Sorcerer. He's got 44 books. They've only got like one review each. They have AI covers. Let me show you guys. I want to if you search up his YouTube, might find it in the description. I think I found it. Let me just. I want everyone to be able to see this. I don't want to go on like too much of a tangent, but actually, this is. Oh no, it's fairly important. Welcome back, Green Pudding. Lunch break is over. I love how you stopped watching the video for your lunch break, but you're back at work. I love it. Maybe you're just listening to my voice. I don't know. Anyway, we're currently looking at the feud. What number are you on? I just finished number 82. We've got one more question. Hello, Green Pudding. We slightly went on a tangent. We have done that. We've got one more question of King Kong level, okay, and then we move on to Caesar level from Planet of the Apes, and then after that it's Harambe level. 62. Did I say 62? Sorry, 82. Did I say 62? Oh, I don't know. I don't know what I said, but 82 is what I meant if I said 62. Anyway, we're currently looking. I don't know if you know who the Math Sorcerer is or City Tutoring. Anyway, they both are kind of weird. But do you know what? If he's making AI textbooks, then maybe I will switch. Maybe I'm gonna, maybe I'm gonna be like kind of like Spider-Man in Civil War to you. Like maybe I'm gonna switch teams. Maybe I'm gonna switch teams. He's basically it's this guy like the Math Sorcerer. He has a bunch of seemingly AI textbooks. Let's read a sample. Look at this. I mean. How to eat books and digest knowledge. Okay. Well, obviously the poster, the cover is AI. Is the book AI? Let's see. I think we'll be able to tell very quickly. Oh no, I can't actually read much of it. It's difficult because he may have written like the the introduction. I can't really tell based off of just this, but what's people saying? No, there's one rating. Someone's bought his book. I think that just to put a bookend on this, I think it's very low to make an AI textbook. I'll be honest with you guys. I do want to show you something. I'm a bit of an idiot with AI, to be honest with you, right? I am the kind of person that just doesn't realize that some stuff is AI. Like, I don't know if you guys saw the video of the kangaroo that wasn't allowed onto a plane. You might know what I'm talking about. I genuinely didn't know that was AI. And I think it actually fooled quite a lot of people, to be fair. And I found out the other week that it was an AI video. And when you see it, it's like, okay, it's kind of obvious that it's AI. But like in the moment, you're not thinking about it. Anyway, a few months ago, I bought 3 textbooks that looked like absolutely perfect. Like it was exactly what I needed. It was textbooks for maths, full of questions, exactly what I needed. The covers were AI. I was like, oh, that's a bit low, but whatever. And then I was reading it, and I was like, I think that. Oh, I don't know if you guys could actually see what I was just looking at there, but like this is the book. Not this isn't the book. I'm going to show you the book that I got. It was by someone called Jamie Flux, who I don't think is real. And anyway, I'm reading this book by Jamie Flux. I'll show you the ones that I've bought. Maybe have they kicked him off? Wait, they might have deleted it. They might have deleted his account. Oh wow. Okay, they might have. I don't think it's on Amazon anymore. I've got it. I've still got the book. Wait. I'll show you guys, and then we'll go back to the integrals. But this is super interesting. Might I suggest Anna's Archive for books? Wait, I'm going to write that down. Thank you. Anna's Archive. Okay, I've opened the page. I'll look at that. Thank you for that. So let me show you something, guys. So just to cap this conversation off, as I say, the other like a few months ago, really, I bought 3 books off of Amazon for about £20 each. I buy a lot of books off of Amazon, and I was like, wow, this is exactly what I need. Like a book on, I was doing like Markov chains and differential equations and all that stuff. And like I bought a book on Markov chains, I bought a book on differential equations, and I think I bought one on stochastic processes. And these are like somewhat specific things that I needed to look at. So I was like, wow, someone's got a book. Someone's written a book on all 3 of these things. Brilliant. You have an amazing bookshelf. Oh, thank you. Can you see it? Oh, did it like bookshelf? Did it like reveal? Oh god, I hope it didn't reveal my room. It's really messy. Oh dear, didn't notice that. Well, anyway, yeah. So these books, they were like 20 quid each. It was exactly what I needed. And again, the cover is obviously AI. I knew that, and I thought it's one thing having book reveal. You guys are going to see. You're going to see. It's one thing having a cover that's AI, and it's another thing to write the entire book in AI, right? No, I meant those slightly larger leaves in the back. Oh, I was really worried that it like revealed my room when I walked backwards. It's so messy. Oh dearie me. Yeah. But yeah, no, thank you. Yeah. I just leaf everything all over the place. Might drop again. No, guys. Let me lock onto this. So, I buy these books. They're super specific. They're exactly what I need. I start reading one of them, and I just get, like when something awful happens, and like you just have like your gut just like drops. You guys know what I'm saying? And I was just like, this is AI. Like this is an AI book, and I spent like 60 quid on these 3 books. And I'll show you what it looks like. So it's by Jamie Flux. And then I was like really embarrassed by it. I was like, oh my God, I just wasted so much money. And like the books had loads of mistakes in them and all that stuff. It was just terrible. And then someone that I was tutoring told me about this whole thing and said, oh, yeah. There's this author. Watch out. If you see a book on Amazon, there's this guy, Jamie Flux. he's not real. It's an AI. It's someone selling AI books. And again, my heart just like, because then it was like the nail in the coffin. I was like, oh, this is definitely AI, because I couldn't find anything on the internet at the time. Looks like the whole thing was really like quick, you know. It looks like he was on Amazon. I promptly bought the books, and now it looks like they've taken him off Amazon now. But I'm going to show you the book. Again, the cover is clearly AI. This is what it looks. Oh no, can you? That's the cover. Oh, there we go. This is on differential equations. Okay. Someone says, oh, well, the Duckwood and Monica. I don't know why I said someone. There's only like 3 of us in this thing. Oh, and if you have a taste for digital copies of rare books / hard to find books, I'd also suggest My Anonymous Mouse. Okay, I'll have that too. Oh, the Pancake Flip Flop Sensation. The Duck with the Monocle. You've lost me again, but it's okay. Look, so here's the book. No, anyway, you've seen it already. It's clearly an AI. There we go. It's an AI cover, clearly, right? Math Magicians, the Math Sorcerer. No, not really. When you said the Math Sorcerer, I really thought like maybe this was him, because Math Magician. I don't know, but yeah, Jamie Flux. And then in the book, it looks pretty good. Like it's it's very high quality. And again, I don't know how easy it's for you to read it. You're not gonna be able to read it because the stream is only in 720p anyway. But you can see here that like there's, roughly speaking, like it's a book. It's a book, and it's full of questions and all sorts of different things. And I was like, wow, this is great. And yeah, again, I'm reading it, and I'm just, when you just have a sense of something. I was like, oh. And then I started flicking through it and just reading it, and I was like, this whole thing is AI. It's so gross, And not to go on another tangent, but you guys have probably heard about what happened recently with Spotify. Someone's discovered an AI band on Spotify. I don't know if you guys have heard this. It's a band that does not exist. It's not a real band. All of the music is AI. All of their photos are AI. They're not real. And Spotify have obviously made them, or someone's made them to make money, but I wouldn't be surprised if Spotify made them so that they could pay themselves the ad revenue. They don't have to pay artists. They're called the Velvet Sundown. They're not real. And you can tell. They sound soulless. But it's really worrying. Anyway, I thought I'd tell you about that. I've still got the book. I don't read it. I don't even like it being in this room, to be honest. I've just been reminded of its existence. Gross. Anyway, that's an AI textbook that I fell for. And I'm a young guy. Like, in theory, I should be the least likely to fall for this kind of thing, right? I can only imagine how many people, like older generations, just eat it up, AI textbooks, AI music. I mean, it's a revolutionary tool, but it's just like, I hate the way that some people are using it. I mean, it's just disgusting. It feels like it's invading every single avenue of creativity. It's just the ultimate corner cutter. It's a shame. And you know what? If the Math Sorcerer really did write a bunch of AI books, give a prompt that just wrote a book, it's unbelievably low, especially if he's selling them. All this stuff, the Math Sorcerer, about how, all the motivational, like, maths is hard. No one said it was going to be easy. And then this guy goes and writes an AI book. Like, I just think it's grim. Anyway, that's my thought on that. Let's go back. Oh, blimey. My bass guitar has just fallen. It's fine. It's chilling there. It's chilling. Oh, okay, guys. Let's go back to this before I inevitably get distracted once again. I'm terrible with this kind of thing. But that's super interesting. I'm going to find out all about the beef between the Math Sorcerer and City Tutoring. Maybe I judged City Tutoring a bit too harshly. Maybe. Probably not. He's still a weirdo. He's still a weirdo, but like, at least he likes maths, you know. I always got the impression that City Tutoring, that guy, like, wasn't even that good at maths. I don't know. Maybe I'm just like completely mistaken. I'm pretty sure he's only got a bachelor's degree. But like, I mean, that's basically what I've got. You know, pretty much. So I'm not saying that it's nothing, but it's like, I don't know, bro. Like, don't you guys think that City Tutoring, considering, I think, if I'm wrong, then I'm wrong, but considering he only has a bachelor's, which a lot of people have a bachelor's in maths, why is this guy acting so like, you're not Einstein, bro? Like, you don't need to dress like that, talk like that, have this like slightly a sense of hubris, you know, to you. Like, bro, you're not that guy. Like, you're not that guy. Maybe he is that guy. I actually don't know enough about him, but I thought he only had a bachelor's because I think I actually looked into it like ages ago, though. Anyway, guys, I'm distracting myself. It's crazy. Let's go back in. Okay, that was question. Oh, we're still not finished with question 82. I've just realized. So we've got this integral here. Make sure that you guys can still see it. No, you can't. That's lucky. Lucky that I spotted that. Share my screen. Okay, we're back. We're back. Okay, so we're up here. We've got this integral. So this is equal to a sixth times x to the 4 times x to the 4 plus 1 to the power of 3 over 2 minus, and then what's going on here? So again, this is a case of the reverse chain rule. You could let u equal x to the 4 plus 1 and see what happens, but I'm not going to do that. I'm just going to do a quick aside here, and I'm going to say, well, I think that it's going to be x to the 4 plus 1 to the power of 5 over 2. And if I differentiate that, I'm going to get 5 over 2 times 4x cubed times x to the 4 plus 1 to the 3 over 2. And that's going to be 5 times 4 is 20 divided by 2. It's 10. So 10x cubed times x to the 4 plus 1 to the power of 3 over 2. Now, I don't have 10x cubed times x to the 4 plus 1 to the power of 3 over 2. I've got 2/3 that I'm trying to get. So I need to make this thing quite a lot smaller. So I need to do is it 2 over 30? Yeah, 2 over 30. So 1 over 15. 1 over 15, and we'll check it in a second. 1 over 15 times x to the 4 plus 1 to the power of 5 over 2 plus c. And again, the reason, let me just explain that, is if I differentiate this second term here, I'm going to have the 5 over 2 come down. So 5 over 2 times 15 is 5 over 30. So a sixth. And then I'm going to times it by 4x cubed because that's the derivative of the inside. So I'm going to have 4/6, which is 2/3. So that's right. Cool. And that's the final answer to that one. And again, I've got it written down. Let's check. Or maybe no, that's right. Yeah, I've got it. Cool. So that's the answer there. A sixth x to the 4 times x to the 4 plus 1 to the power of 3 over 2 minus a 15th x to the 4 plus 1 to the 5 over 2 plus c. And the duck with the monocle says, oh, so it turns out City Tutoring has a master's in maths from Imperial College. Okay. All right. Fair enough. I was wrong. Did do a Bachelor of Arts and then applied sciences. Don't want to distract with drama, but I'll send LinkedIn page. Yeah, please do. Please do. Yeah. Okay. He has a master's in maths. I can't really hate on him, to be fair. I don't know why. I don't know why I thought that. I thought I looked into it and it said that he only had a bachelor's, but I don't know. Yeah, please do send the LinkedIn page. I'm curious about this guy. But don't you think that he's just a bit perplexing of an individual? He's just a very like cartoonish guy. Like he gives. I don't know if are you British? I actually don't know. He kind of gives Jacob Rees-Mogg, you know. He has a bro. His bachelor's is from Cornell. Cornell is like a good uni, right? Maybe he is that guy, guys. He might be that guy. Maybe I'm not that guy, but he is. Maybe the tables have turned. But he does give Jacob Rees-Mogg. Not that Jacob Rees-Mogg is a very relevant guy these days, but he's giving Jacob Rees-Mogg through and through. Just absolutely unbelievable stuff. He's absolutely mogging it, bro. And there's no doubt about it. But yeah, maybe you guys don't know who that is. I don't know who's from the UK, who's not. Really compared him to a member of parliament in saying, yeah, but not a member of my parliament. You know what I'm saying? He really, but he gives parliamentary. He gives parliamentary, like he's a parliamentarian. I don't know what I'm talking about. He's just, I don't know. He has the same level of like slight, hubris to him. Slight, very strong hubris that Jacob Rees-Mogg has, But maybe, no, I like him better than that. Why am I hating on this guy? Like, he actually seems chill as hell. And you know what? Like, he being an absolute geek is clearly in his DNA. But you know what? There's nothing wrong with it. Like, he wears it on his sleeve. I just think his like accent is kind of funny. Like, it seems like he's really like channeling the deep voice, like he's really like, he talks kind of like, what's that actor? Who am I thinking of? He talks like an actor. He doesn't have the same voice, but he has the same cadence as, who am I thinking of? Oh, I'm thinking of, okay. This is the most random comparison. This is really niche, actually. I don't know if you've ever seen 100 Integrals Left Undefeated after Curious George distracted by other mathematicians. I know. Okay, I will get to it in a second, but I don't know, okay, because this is very niche. I don't know if you've ever seen the show Daredevil. The first iteration, the 2015 one, or Daredevil Born Again. Kingpin from Daredevil. Wilson Fisk, right? Vincent D'Onofrio, the actor. The way that guy talks is like the way that City Tutoring talks, guys. I swear to God. No, I can't. I have to show you now. Kingpin. It's not the same voice, but it's the cadence. Okay? I'm gonna show you guys. Make sure that I'm not showing a really violent scene. Okay. I just want you guys to see something. Just trust me. All right. Let me share my screen. Wait, Vincent played Edgar from Men in Black. Yeah, I think so. Yeah. All right. Just watch this. Wait. Can you tell me if you can hear this? Let me turn it down a bit. Tell me if you can hear this. Can anyone hear? Oh, wait, hold on. Guys, tell me if you can hear this. Wait.
This city isn't a caterpillar. It doesn't spin a cocoon and wake up a butterfly. A city crumbles and fades. needs to die before it can be reborn.
Could be a problem.
Problems. Just opportunities that haven't presented themselves.
Can you guys hear this?
Tell that to the people you've hurt.
Young man,
Can you hear it?
life is not a fairy tale. Not everyone deserves a happy ending.
I'm just the guy that got fed up with men like you, and I decided to do something about it.
I don't know if you can hear that. Could you hear it? Do you know what I'm saying? Like this guy speaks like City Tutoring. Okay, and I'm standing on that. One more.
And steal, but you merely present the prisoner with a challenge. Any truly determined man will find a way out. Love is the perfect.
And calculus. Today we're going to do algebra. I see what you're talking about, but he doesn't sound like that. No, but it's his cadence, bro. It's the way that he is getting the words out. Like they both sound like they're forcing it out of their like diaphragm. The way that he like it sounds like he's the way he's like straining. I'm not talking about his. Oh, he does sound like Hugh Laurie. Actually, I get that. I do get that. But I'm saying like their cadence, dude. They sound the same. Like City Tutoring is Kingpin. Maybe Matt Sorcerer is Daredevil. I don't know. Daredevil would never make an AI book. Partly because he's blind. Okay. Hopefully you guys follow me. But anyway, let's get back into it. But I actually do. No, I do see Hugh Laurie. I do see Hugh Laurie. Okay. Share screen. All right. Question 83. Question 83. We've got the integral of 1 over x squared minus 8x, and this is the last King Kong question, plus 20 dx. Okay. Oh, and I just realized you guys can't see it. There we go. Question 83. The integral of 1 over x squared minus 8x plus 20. Yeah, sorry about that. I just realized you can't see the whiteboard, but you can now, hopefully. It's only my 4th live stream ever, guys. Cut me a little bit of slack here. Cut me a little bit of slack. Okay. All right. So, any thoughts on this one? Well, I don't know. I keep saying that, but it's a rhetorical question because I'm not going to wait for everyone to reply, although I'd like to, but it would take too long. Who am I to say how long this takes? How long have we been going? 4 hours? 4 hours, 12 minutes. It's going to be 5. It's going to be at least 5 hours long. Okay, that's fine. That's fine. So what do we do? Well, guys, we can complete the square. So we can go 1 over x minus 4 squared plus 4. Okay, so we just completed the square on the denominator. Why have we done that? Well, guys, let's think about this. This is a really random substitution, but if we replace x minus 4, let x minus 4, if we replace that with 2 tan u, okay, then we're going to get 1 over 4 tan squared plus 4, which is really good. Okay, lovely. So what does that mean? Well, it means that we could say, let x, that means that if we want to do it a bit neater, x is 2 tan u plus 4. So dx du is 2 sec squared u. Okay, if we want to do it like that. So the integral is 1 over, and again, we're replacing x minus 4 with 2 tan u. So we're going to have 4 tan squared u plus 4, and dx is 2 sec squared u du. Okay. Now, what's good about this is that this is then going to equal, let's take the 1/2 to the outside. Okay, and the 1/2 is from the 2 over 4. The 2 and the 4 is kind of cancelling a little bit. Remember, guys, tan squared plus 1 is sec squared. So once again, it's sec squared over sec squared. So it's 1 du. So this is going to be 1/2 u plus c. But what did we say that u actually was? Well, we said that u, if we do a bit of rearranging of this, okay, tan u is x minus 4 over 2. So u is inverse tan or arctan of x minus 4 over 2. So the answer is that the integral of 1 over x squared minus 8x plus 20 is 1/2 arctan x minus 4 over 2 plus c. Look at that. And you guys can see it's a good case, right? Because these inverse trig functions appear like all the time in these integrals. Oh, and Nishane is back. Welcome back. Welcome back. We've been going so long that you've probably, I don't know what country you're in at the moment. We've got a lot of people from all over the place, but maybe you've gone to bed and woken up. We've been going for so long. Back on the break. Okay, love it, love it. Okay. Oh no, guys, I bought a PS5 the other day. You're in Texas. Oh. Got rappers, guys. Look at this. How have I got this in the jungle then? Right? This is global war. This is not good enough. Actually, that's what this is. Can't believe that. How are you going to get PS5 in the jungle, mate? Crazy. Absolutely crazy. So, yeah, I got PS5. That's the box for the PS5, guys. I've been playing Fortnite. Tell me if you got any good games, by the way. I got PlayStation Plus Pro, whatever, I don't know. The one where you get the free games. And Jurassic World Evolution 2. Let's go. That's like Sims for boys. Boys. Okay, guys, let's log back in now. We're getting silly. Okay, that was question 83. We're so close. Okay, question 83 complete. Question 84. Question number, let me zoom in a bit more. Question number 84, gang. Actually, it's being a bit laggy. New whiteboard. Are you with or against trees? That's funny, bro. I love it. No, I actually love that. No, you made me laugh. That's good. That's made my day, bro. Okay, guys. Question 84. The integral of 1 over 1 plus 3 cos x. I've also got a YouTube video on this exact integral on my channel. Just look for the video with John Pork in the thumbnail. That'll be the one. So the way that we're going to do this, there's definitely other ways, but we're going to use what you call, we mentioned him earlier, the Weierstrass substitution. Okay, this isn't even like top 10 things that he did, by the way, but you know, well, it probably is actually, but Weierstrass substitution. So just to break this down very quickly, essentially, if you let some letter t be equal to tan of, let's say, x over 2. I will not go through the whole. I've actually got a YouTube video on this, so you can check it out genuinely. But it turns out that cos of x can be written as 1 minus t squared over 1 plus t squared. And also, I'll just say it for the sake of it, sine x is 2t over 1 plus t squared. And tan x is 2t over 1 minus t squared. Okay, so what you can do, and also, by the way, when you do this, you get that dx becomes 2 over 1 plus t squared dt if you take the equation t equals tan x over 2. So this is called the Weierstrass substitution. It's super useful for integrating what you would call rational trig functions. So a rational trig function is just a trig function that is like a fraction, basically. So a bunch of like sine and coses and tans divided by a bunch of sine and coses and tans. So that's what we have. And so it's really good at that. Okay, and that's how I'm going to do it. You don't happen to watch K-theory by any chance, do you? No, I don't even know what it is. I've heard of that, but I don't know. Is that a YouTube channel? I think I've heard of that, but I don't know what it is. But feel free to enlighten me. Okay. So, oh no, is K-theory is it a K-drama? Is it a K-drama, bro? Because if it does, then I know someone that watches it. If it is, not if it does. Anyway, we'll get to that. We'll work it out in due time. Okay, so this is what we do, guys. We just simply use the substitution. So we're going to rewrite this as the integral of 1 over 1 plus 3 lots of, and remember, and by the way, we're saying that t is tan x over 2. We get that we've got cos is 1 minus t squared, 1 minus t squared over 1 plus t squared. And remember, dx, you can replace it with 2 over 1 plus t squared dt. So you've got 2 over 1 plus t squared dt. So this looks really messy, but actually we can make it nicer. So we've got 2 over, and then I'm just going to expand out this denominator with the 1 plus t squared over here. So we've got 1 plus t squared, and then we've got 3 times 1 minus t squared times, or divided by 1 plus t squared times 1 plus t squared. So this just becomes 3 minus 3t squared dt. And it's not the greatest integral in the world, but it's doable. So 1 plus 3 is 4. And then we've got t squared minus 3t squared. So that's minus 2t squared dt. Cool. Now we can also just divide everything by 2. So we've got 1 over 2 minus t squared dt. It's a maths YouTuber. He's doing a bit of his master's research on live stream. Oh, really? It's okay, Duck with a monocle. You can cheat on me. You can cheat on me, bro. Double checked. He's doing his PhD research. Lovely. I think now that you say that, I think I do know who he is, actually. Sometimes I do get mathematicians muddled up with K-dramas. It's happened at least 3 times. I'm being so silly. Okay, lock in. No, for real though. That actually sounds really interesting. It's like the time that, I don't know if you know who Bison Maths is. It's like the time that I accidentally did a live stream at the same time as Bison Maths. Crazy stuff. Crazy stuff. Okay, so we have the integral of 1 over 2 minus t squared. Now, guys, if we remember, if we take ourselves back in time, to which question? God, I've not written it down. So annoying. There was a question. Let's find which number it was, where we have an integral of this form. Okay. Let's work it out. Which one actually was it? Oh yeah, and by the way, we're now in the second Caesar question. Oh, I've just realized I've missed out a question, but that's okay. I think I missed 83, didn't I? Oh yeah, okay. I think I missed out at question 83. Or did I miss? No, I'll tell you what I did. I didn't miss it, but I've numbered them a bit wrong. I'm just going to make up a new question. Well, not make up, but I do have another. Basically, it's because in the Harambe section that we haven't got to yet, there was one integral that turned out to be way harder than I thought it was, so I deleted it, and I added another integral earlier on, and we haven't actually done the integral yet, so it's messed up all the numbers. But it doesn't matter. It doesn't matter. We can fix it. It's actually not messed up anything. It's only messed up the past like 1 or 2 questions. So if I do manage to get the PDF document out, you can still get the question numbers right. That's not an issue. But I do apologize for that. We'll do that in a second. Anyway, there is a question. We did it somewhere. Oh yes, question 73. Let's remind ourselves of question 73. So, guys, recall that the integral of 1 over a squared minus x squared dx is equal to, if I go back to question 73, where are we? Question 73. This is equal to 1 over a times r tan of x over a plus c. But, and I'm just take my word for this, guys, please. But that is the same thing. Okay, it is the same thing as 1 over 2a. Just take my word for this, of the natural log of x plus a over x minus a. Okay, just take my word for that. You probably can't even see it. There we go. Okay, just trust me. And if you don't trust me, that's okay. But I'm not going to explain it. This integral itself, like the integral of 1 over 2 minus t squared, is not even that bad because you can just do partial fractions. Just rewrite it as root 2 minus t times root 2 plus t on the denominator and you're fine. So it's actually not a big deal. But I just want to use like a previous thing that we did. So I'm going to use this. And we can see that like a in the integral that we're actually doing is the square root of 2 because like this is 2 on its own, so it's like the square root of 2 squared to match the form of this integral. So this is equal to 1 over 2 root 2. And by the way, again, I do have the full version in a YouTube video already. It's the John Pork video. 1 over 2 root 2 times the natural log of, and again, this in terms of t, so t plus root 2 over t minus root 2 plus c. And remember, we said that t was tan of x over 2. So the final answer for this one is 1 over 2 root 2 times the natural log of the absolute value of tan of x over 2 plus root 2 over tan of x over 2 minus root 2 plus c. Okay. That's the final answer for that one. We're getting there. We're getting there. Hopefully everyone's kind of happy with that one. Bit of an unconventional one because we use the Weierstrass substitution. Now, to do question 84, I am going to do it again. So question 80, or 85, I mean. 84 we just did. So question 85 is going to be the integral of 1 over sine x plus tan x. I also have a video on this one. So again, we're just going to use the same substitution. We want to let t equal tan of x over 2. And that means that we can rewrite this integral as that of 1 over 2t over 1 plus t squared plus 2t over 1 minus t squared, and dt is always the same because it's the same substitution. It's 2 over 1 plus t squared dt. Okay, and then we can expand this. So we've got 2 all over, and then times everything by on the denominator by 1 plus t squared. So we've got 2t, and then we've got 2t over 1 minus t squared times 1 plus t squared dt. Right? And then I think I'm going to times everything by 1 minus t squared. So this is equal to 2 minus 2t squared, all divided by 2t times 1 minus t squared plus 2t times 1 plus t squared dt. And I'm going to cancel out all the 2's. So I've got 1 minus t squared over t times 1 minus t squared plus t times 1 plus t squared dt. And I'm just going to keep expanding and simplifying. So 1 minus t squared over t minus t cubed plus t cubed. But wait, that's wrong. T minus t cubed plus t cubed. Oh no, that's not wrong. I thought everything just cancelled out there, but it doesn't. Good. Okay. And that's the integral of 1 minus t squared over, and then the t cubes do cancel, and with t plus t, that's 2t. And all of a sudden, this is a pretty straightforward integral. So this is an integral of 1 over 2t minus, and it's like t over 2t. So 1 over just t over 2, or half t. Okay. And I think that it doesn't matter, but I think I will also take out the 1/2. So 1/2, and then we've got 1 over t minus t dt, like that. And hopefully everyone's pretty happy with that so far. So I've got a half, and then actually doing the integral, I've got the natural log of t minus a half t squared plus c. And that's going to be a half times the natural log. Again, t is tan over 2. So the natural log of tan, well, it's not tan over 2, tan of x over 2, minus a quarter t squared plus c. And that is the final answer. So that was the integral of 1 over sine x plus tan x. Turns out to be a half the natural log of tan x over 2 minus a quarter t squared plus c. Fascinating. Absolutely fascinating. Oh, and I've just realized, why have I left t squared how it is? That's just me being a bit silly. Obviously, t is tan x over 2, so minus a quarter tan x over 2 squared, so tan squared x over 2 plus c, like that. And yeah, that's the answer. Cool. Okay. We're making good progress, to be honest. Next one. The integral This is question number... Oh, actually, before we do this, I'm going to do this extra question. I'm going to call this question 85. And question 85 is going to be... Where's it gone? There's a question somewhere that has not actually been done. 83. Oh, yeah. So it's the integral of x cosh squared x squared. This is technically a King Kong question again, but it's quite good. So the integral of x cosh squared x squared dx. That's the question. Okay. So, oh, excuse me. Okay. So we're just going to let u equal x squared. So du dx is 2x. And then we can rewrite this as the integral of x times cosh squared of u. And then dx, we can see dx is du over 2x. So times du over 2x, the 2's cancel, oh, sorry, not the 2's, the x's cancel out. And so this leaves us with the integral of a half, and again, cosh is hyperbolic cosine, half cosh squared du. Now, you might say, okay, well, how do you integrate cosh squared? Well, of course, don't be silly. We can use the double angle formulae for hyperbolic trigonometric function. Don't be so silly, of course. Right. So remember that cos of, let's use u again, cos of 2u is 2 cos squared u minus 1. That means that cosh of 2u is 2 cosh squared u minus 1. Because, and I've not actually said this, but just to be clear, any trig function maps directly onto any, any trigonometric identity maps directly onto any hyperbolic identity, with the exception of what you call Osborne's rule, which is that if there is a sine squared term, if there is a sine term multiplied by another sine term, you need to change the sign of it from positive to negative or negative to positive. There is no sine squared term here, or shine squared, so it's the exact same. That's how all of the identities work. The reason for that is because of complex numbers and stuff. Okay, and so that means that we can rewrite this as the integral, and cosh squared, we can see, cosh squared, I'm going to take the 1/2 out. Cosh squared is a half cosh 2u plus a half. So here we've got a half, and actually let's take the half out as well. So a quarter, and then we've got cosh 2u plus 1 du. Remember that cosh integrates to shine. So this is going to be a half, put it here, a half shine 2u plus u plus c, okay? And that's going to give us an 1/8 shine 2u plus u over 4 plus c. And remember, we said that u was x squared. So the final answer to this one is an 1/8 shine 2x squared plus x squared over 4 plus c. Okay. Hopefully everyone is kind of chilling and happy with that. And I'm just checking, an 1/8 shine 2x squared plus x squared over 4 plus c. Yeah, good. Just got to check my answers, because sometimes I'm a bit of a silly guy and I make silly mistakes, you know. We all do. Right. So that was the integral of x cosh squared x squared. All right, on to question number 86. We're slowly but surely getting there, guys. We're slowly but surely getting there. All right, question 86. The integral, the return of the hyperbolic functions, we've got the integral of r sine x. Okay, the integral of r sine x. Let me write that down. So r sine, again, it's the inverse of hyperbolic sine. And just as a reminder, if anyone wasn't here or they weren't sure, sine on its own, the original function, actually, I'm going to open another whiteboard because it's buffering. Okay, so just to be really clear, sine x is by definition e to the x minus e to the minus x over 2. And we're looking for the integral of r sine x dx. So this is the inverse function of this. So what can we do? Well, we can use integration by parts. Okay, normally it's pretty, if there's an inverse function, it's sometimes a good shout, I would say, to use integration by parts. So let's let u equal r sine x, and let's let dv dx be the number 1. So that means du dx is going to be the derivative of r sine x. Now you might say, wait, what is the derivative of r sine x? Well, it's going to be 1 over the square root of x squared plus 1. Okay, and that means that v is just x though. But before we go on, because I think I've just pulled that out of thin air, so let's actually explain this. Let's say, let's be rigorous, or as much as possible here. So I'm going to say I want to differentiate r sine just to show you what it is. So I'm going to say that y is r sine x. Okay. You could also do it by literally finding what r sine is in terms of logarithms and stuff. Like, you can do that, that's fine. But let's do it directly. If we apply sine to both sides, then we have sine y equals x. So that means that using implicit differentiation, cosh y dy dx is 1, which means that dy dx is 1 over cosh y. Remember, where shall I do it? I'll do it over here. Remember that cosh squared x minus sine squared x is 1, not plus. So that means that cosh can be replaced by the square root of sine squared x plus 1. Okay. Green pudding is going... please just use OneNote at this point. Is OneNote better? I don't know. I don't use it. I don't know. Is it still good for you guys? Or is it just more like out of concern for me from it buffering and stuff? And green pudding is going on another lunch break. Okay, have a nice time. We will still be here. It's so much better. Okay, well, I'll use it next time. There'll be another. Should I do like 100 different derivatives? I could do so many things. 100 differential equations. That would take ages. 100 Laplace transforms. It would take ages. It's part of the game though. It's fun. Okay. Anyway, we know that y, or x, sorry, is sine y. Okay. So in our derivative here, we have that dy dx is 1 over the square root of sine squared x plus 1. and shine squared, oh, sorry, not x, that's a y, shine squared y. We know that shine squared, or we know that shine y is x. So this gives you 1 over the square root of x squared plus 1, like so. That's how you know that that's the derivative. Okay, and then moving back into actually integrating it, the integral of r shine x dx is going to be u times v, so x r shine x, minus the integral of x over the square root of x squared plus 1 dx. Okay. Although I did pirate the 2024 version. Oh, do you have to OneNote? I don't know. Do you have to pay for it? OneNote. I feel like I should know this. I'm such a boomer. I'm such a boomer. I don't know. Do you have to pay for it? I don't know. I don't know. I'll pay for it, maybe. Okay. Now, this integral here, x over the square root of x squared plus 1. We've got x r shine x. And then what's going on with this this guy here? Let's do it in a different color to make it distinct. So this is x times, actually that's going to be in the way. This is x times x squared plus 1 to the minus a half, right? So if I think about x squared plus 1 to the power of positive a half, and I differentiate it, I will get 1/2 times 2x times x squared plus 1 to the power of minus a half. These cancel, and I do indeed get what I wanted, which means that I know that the integral of x over the square root of x squared plus 1 is just going to be the square root of x squared plus 1. Okay, and then plus c. So the integral of r shine x is x r shine x minus the square root of x squared plus 1. Get a load of this guy. Imagine not pirating software with hostile companions. Inexorable the type of guy to pay the cancellation fees to Adobe subscription. No, I would never. I wouldn't. I heard about that because it was like the PewDiePie thing. Wasn't it like they asked him to pay $60 or £60 to cancel his own subscription? That's unbelievable. No, I wouldn't pay that. Of course not. I don't know if I don't even know if OneNote costs money to like. I wouldn't necessarily pay for it if I didn't have to, but like I don't even know if it costs money. Like that's what I mean. Like, is it free? I literally don't know. Yeah. Who knows? Okay, but anyway, that's the answer to that one. So that was question number 80. Was that 86? 86. It's supposed to be 86, but I've kind of I've ever so slightly messed up the ordering here. Not exactly, but kind of. I think it was right. That was question. Yes, that was question 86. Somehow. I'm not sure how it was 86 because I feel like we're missing. Are we still missing a question? I really don't know. What was the last question? Well, the last question looks like it was 85. Yeah. Okay. I'm not 100% sure what's happened, but you know. Paulo Rodriguez says, why? Seriously, why? What do you mean? What do you mean? The funny thing is there's literally so many things that you could be validly, genuinely asking that question for on this live stream. Why would you pay for Adobe? Or why would you pay for OneNote? Or maybe why are you pretending that you're in the jungle? Or why are you doing 100 integrals? Paulo, come join us. You know, we're almost done. But I have somehow we've lost a question somewhere. Like it seems to. I don't know. Like I've lost count. I don't know, but we'll work it out. We'll work it out. So we've got R shine. Okay. The next few questions are fascinating. So the next one, I'm going to treat that as question 86. Okay, let's figure out whether it's going to, work later. Now it's time for question 87, and this is the integral of R cosh x. Okay, and again, R cosh is the inverse function of cosh. And just to be clear, cosh x, as a matter of definition, is e to the x plus e to the minus x over 2. That's what cosh is, and this is the inverse function of that. Okay, so again, using integration by parts, we should say that u is r cosh x, and dv dx is 1, meaning that du dx is the derivative of r cosh of x. And again, I'm not going to actually prove this one, but it's 1 over the square root of x squared minus 1. Just take my word for it, gang. Just take my word for it. And v is x. Okay. Cool. I think this is question 86, you say. Want me to go back in the live stream? Well, I actually did go back in the live stream. I've got it on another tab. I think if I've ordered them slightly wrong, it doesn't matter, but I think that this is question 87 now. I don't think it's question 86. I think it's question 87. But if it turns out that it's all wrong and messed up, then it doesn't matter. It doesn't matter. It should be question 80. It might be question 88. I don't know how, but we'll see. We'll work it out. We'll work it out. If I get to the last question and that was only question 99, then you're right. Which could happen, but then I'll just make up another one. Okay. Right, so anyway, we continue with this. So again, not going to show you why that differentiates to that. It's a very similar concept. It's going to take ages. So we have then got that it's the integral of r cosh x is going to be x r cosh x minus the integral of x over the square root of x squared minus 1 dx. That's going to be x r cosh x minus, and then again, guys, we can think about what this is going to be. I think this is just going to be the square root of x squared minus 1. And just to check that that's definitely right, it would be to the power of a half. So when you differentiate, you get the minus a half, which is good. Half comes down, half times 2x. That's correct. Okay, so that was basically a new method that I've just made up called integration by guessing. Integration by magic. I've not actually made that up, of course. People have been doing that for a very long time, I'm sure. Just checking the answer. Boom, 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 boom. Yep, that's right. Lovely. Okay, so I think that was question 87. On to question 88. Question 88, we're doing the integral, believe it or not, of the inverse function of than, r than x. Again, than is shine over cosh. There's a crap load of latency between the chat for me and the stream. So when I did post that you were attempting question 86, this is question 87, like you said. Oh, okay. Okay, I've got you. I've got you. That's a shame that there's so much latency. That's crazy. Yeah, it makes sense, to be fair. It makes sense. Okay, but thank you. So I believe this is question 88. It's 88 in my document. But as I say, I've kind of confused myself because I added one in after, and then I did it yesterday, and I'm reading it off, not the document, but all of my working out from doing all of these questions yesterday. So by the time we get to the end of this, I will have done 200 integrals in the last 48, actually in the last, yeah, pretty much less than 48 hours. And just the same 100 twice. So it's going to be crazy. Okay, Rthan. So again, this is the inverse function of shine over cosh, and it's the same method as before. So we say that u is Rthan x, and dv dx is x. It is 1. So du dx is the derivative of r than, which is 1 over 1 minus x squared. And v is just x. So this is equal to x r than x minus the integral of x over 1 minus x squared dx. Okay. Hopefully that makes sense. And then that's going to be equal to x r than x. And then let's, and this is quite an easy one because it's just a logarithm question. So again, it's going to be like the natural log of 1 minus x squared. If you differentiate this, you're going to get minus 2x over 1 minus x squared. Now you do want the minus because there's a minus there as well, but you don't want the 2, so plus 1/2 plus c. And it looks like that's the answer. So it's, x r than x plus 1/2 the natural log of 1 minus x squared plus c. And for this one, hopefully it's clear to see that the absolute value of x needs to be less than 1. Otherwise, the natural log, we're going to be doing the natural log of a negative number. Okay. And I believe I think I'm right in saying that r than is actually only defined between -1 and 1, so it's kind of irrelevant to say that. I've not been stating the domain for any of these functions when they clearly have them, because normally, or pretty much all the time, the domain of the integrated function is just the same as the domain of the original. So it's kind of a bit boring to keep saying it, but still important. Okay. Cool. So that's the integral of r than, the inverse function of sine over cosh. Okay, on to question 89. Question 89. This is an interesting one. So the integral from 0 to 1 of the natural log of 1 plus x over 1 minus x. Okay. Now, this is an improper integral because we can see that when x is the number 1, we've got the natural log of like infinity. The denominator for that fraction is infinity. So we need to be a bit careful. So what I'm going to do is I'm going to split this up. Say it's the integral from 0 to 1 of the natural log of 1 plus x minus the natural log of 1 minus x, just by using that rule of logarithms. Then the first integral is rather doable. It's rather doable just on its own by doing a substitution, and then just remembering what the integral of the natural log of x is. So I'm just going to say let u equal 1 plus x. Okay. And before I do that, I'm going to split them up into 2 separate integrals because I only want to do the substitution on the first one. So I'm going to rewrite this one more time as the integral from 0 to 1 of the natural log of 1 plus x dx minus the integral from 0 to 1 of the natural log of 1 minus x dx. And we're coming up on 5 hours on the live stream. 5 hours. 5 hours. Okay. So for the first one, I'm going to let u equal 1 plus x. Okay. So that means that we can see du dx would be the number 1. And when I've got my integral here, I'm just making sure that's still visible. Yes, it is. When I do my integral, I've got the integral from this time, it's when x is 0, when x is 1, 1 to 2 of the natural log of just u du. And we can actually just use a standard result. We actually did this integral earlier, the integral of the natural log of u, or the natural log of x, so that's fine. And then I'm just going to rewrite this other integral but I'm going to go minus the limit as t goes to 0, or as t approaches 1 actually, because 0 is not the problem, of the integral from 0 to t of the natural log of 1 minus x dx. Okay, cool. Cool. Yeah, that's fine. All right, now we know from a previous question, because we actually did the integral of the natural log earlier today, we know that the natural log of u is going to integrate to u times the natural log of u minus u. That's the integral of the natural log of x ln x minus x. Okay, and then plugging in 1 and 2, and we'll come back for that in a second. Then I've got the limit as t approaches 1 of this integral, and I think the best thing to do here is to also use a substitution. So I'm going to let v equal 1 minus x. I think that's the best way of doing it. So then I've got that this term here is going to be 1, and this is going to be 1 minus t, and then I've got the natural log of just v. And remember, dv dx this time is going to be minus 1. So dv is minus dx. So I can put a dv here as long as I put the plus out there, and that should be fine. Cool. Cool. Right, next thing's next. So let's actually do this first integral. So u times the natural log of u. So this is going to be 2 times the natural log of 2 minus 2 minus 1 times the natural, that's a bit confusing. Yeah, 1 times the natural log of 1 minus 1 plus, and then I'm going to replace the t. I'm going to say the limit as, maybe we can say as y approaches as y, because as t approaches 1, do you see that the upper limit is actually just 0 because it's 1 minus 1? So let's say the limit as y approaches 0 of the integral from 1 to 0, or from 1 to y of the natural log of v dv. Okay. And it doesn't matter, by the way, that the order of those terms is like the wrong way around, right? Because it's like 1 and then up to 0. That doesn't matter. Okay, so then we've got 2 times the natural log of 2 minus 2. The natural log of 1 is 0. And then we've got like minus 1, so plus 1. And then we've got plus the limit as y approaches 0. And then again, the natural log of v is v times the natural log of v minus v. Well, the integral of it is at least. And then we've got 2 times the natural log of 2. Minus 2 plus 1 is minus 1. Plus the limit as y approaches 0 of, and then we've got y times the natural log of y minus y minus 1 times the natural log of 1 minus 1. Okay, so we've got 2 times the natural log of 2 minus 1 plus the limit as y approaches 0 of y ln y minus y. Again, the natural log of 1 is 0. And then we've got like a minus 1, so plus 1, like that. Okay? Now, we need to work out what's going to happen as y goes to 0. Okay, because at the moment the y ln y is actually not very obvious. This is maybe one of the harder parts of the question. What is 0 times the natural log of 0? Well, yeah. What is 0 times the natural log of 0? Or what's the limit as we approach it? Well, 0 is 0, and the natural log of 0 is minus infinity. So it's like 0 multiplied by infinity. What is that? Well, let's see. So I've got 2 times the natural log of 2 minus 1. And then the clever trick here is that if you rewrite it as the natural log of y over 1 over y, then you have the natural log of 0, which is minus infinity, divided by 1 over 0. So minus infinity divided by infinity. And the reason why you do that is because it allows you to use L'Hopital's rule. Because L'Hopital's rule only works for 0 divided by 0 or infinity divided by infinity. Okay, so L'Hopital's rule says that if you're struggling to evaluate a limit that's in the form 0 divided by 0 or infinity divided by infinity, you can simply differentiate the numerator, differentiate the denominator, and try again. So the derivative of the natural log of y is 1 over y, and the derivative of 1 over y, which is y to the minus 1, is minus y to the minus 2. Okay, and then the minus y, I'm just going to leave it, that's fine. And then plus 1 is also fine. Okay, and we're almost done. Now we can actually try to evaluate the limit here, or maybe let's do one more step of simplifying. If I multiply the top and the bottom of this fraction by y squared, then I get y divided by minus 1. And as y goes to 0, that goes to 0. So 2 ln 2 minus 1 plus, and then this term we now know that's going to just be 0, so plus 0, minus y, that's also 0, and then plus 1. Okay, so the minus 1 and the plus 1 cancel. The final answer is that the integral from 0 to 1 of the natural log of 1 plus x over 1 minus x is 2 times the natural log of 2. Or you could also have, if you want, the natural log of 4. Just bringing the 2 up there. Cool. Hopefully everyone's kind of happy and chilling with that. We're almost at the Harambe level here. Not quite, but almost. So that was question 88, 89. Okay, so now we're at question 90. This is where it gets interesting, to say the least. Make a new whiteboard, though, because it's getting a bit crazy out here. Okay, so question 90, not quite at Harambe level, but still, we're really getting there. The integral from 0 to infinity of x to the 5 times e to the minus x to the 4 dx. So it's a pretty crazy one, okay? And it relies on a very interesting result that's actually a question later on. It's a Harambe question. So I'm just going to do, this may not seem that satisfying because I'm going to tell you the value of an integral, but we will work out the integral. We'll kind of like prove it later, okay? So take my word for it for now. So first thing we do is we just do a substitution. It will make sense in a second, but we're going to say u equals x squared. Okay, that means that du dx is 2x, meaning that dx is du over 2x. So now we're going to do the integral from, and again, like changing the limits into u's, it's still going to be from 0 to infinity. That doesn't change anything. Of x to the 5. So x to the 5 is x squared times x squared again times x. So I can say that this is u squared, that's x to the 4, and then times another x. I've got e to the minus u squared du over 2x. And that x cancel. So now I have the integral from 0 to infinity of, take the 1/2 to the outside, 1/2 u squared e to the minus u squared du, just like that. Okay. Now, the clever bit here is to split the integral up again and use integration by parts. Okay. So again, I'm just going to do like a trivial substitution. I'm just going to say let t, no, I'm not going to use t actually because I'm going to probably use it later. Let's let, we'll come up with a letter. Let's do lambda. Let's be a bit crazy. Let's just let lambda be equal to mu so that I can rewrite this because I'm going to do integration by parts and I want to be able to use the letter u. So that's my integral. Lambda and mu are the same. Oh, and sorry, that should be a d lambda. Cool. And the reason I'm doing this is because now I can let u, and actually I'm going to do one more step to make something very clear here. I've got 1/2 the integral from 0 to infinity of, and I'm going to write this as lambda times lambda e to the minus lambda squared d lambda. So I'm treating this as two functions here. U is going to be just lambda, and dv dx is going to be lambda e to the minus lambda squared. So that means that, oh, and so that's dv d lambda. And so du d lambda is 1, and v, we have to actually integrate lambda e to the minus lambda squared. That's going to be e to the minus lambda squared. And then if we differentiated this, it would give us minus 2 lambda e to the minus lambda squared. So I should put a minus 1/2 there so that it cancels out. Okay, tell me if that makes sense, guys, or not. Hopefully it does. Hopefully. You don't actually have to tell me, but hopefully it does. All right. Then we can say that this integral is 1/2 big brackets u times v, so minus 1/2 lambda e to the minus lambda squared, and again that's 0 to infinity. I should probably be putting lim, but I'll do that in a second. Minus the integral from 0 to infinity of minus 1/2, so plus 1/2 e to the minus lambda squared d lambda close bracket. Okay, and the eagle-eyed ones of you might notice that the last integral is very, very curious indeed. So this is equal to, I'm now going to start writing it, 1/2 times the limit as t approaches infinity of minus 1/2 lambda e to the minus lambda squared from 0 to t, plus the integral from 0 to t, and I'm going to put the half on the outside there, 1/2 e to the minus lambda squared d lambda. Okay, and this is equal to 1/2 times the limit as t approaches infinity of, and what have I got here? So I've got minus 1/2 t e to the minus t squared minus basically 0, because it's minus 1/2 times 0 times something, plus 1/2 times this integral. And this integral has a value that I'll get to in a second. Okay, now the integral here, we can also use L'Hopital's rule to do it, because it's currently in indeterminate form, because as t goes to infinity, we've got infinity times 0, because e to the minus infinity is 0. So again, what I'm going to do is I'm going to say this is minus 1/2 times t over e to the t squared. So now it's infinity divided by infinity. Plus, again, 1/2 the integral from 0 to t, e to the minus lambda squared d lambda, like that. And this is 1/2 the limit as t goes to infinity of. Now, if I, again, use L'Hopital's rule, differentiate the top, differentiate the bottom, I'm going to have 1 over 2t e to the t squared. And very clearly, as t goes to infinity, this clearly is going to go to 0 over a 1 over that, because the denominator goes to infinity, so it's 1 divided by that. Okay. So what I'm saying is that if we actually take the limit, then we've got 1/2 open bracket, this is 0, so just 0, plus 1/2, and then I'm going to put the infinity sign back up here for this one, because this integral is very famous. So maybe some people might know what this is equal to, but the integral from 0 to infinity of e to the minus lambda squared d lambda is actually equal to the square root of pi over 2. So the answer for this question is the square root of pi over 8, because there's like 3 lots of 2 there. Okay, so I'm just going to make a note of this because we're actually going to do this integral later. The integral from 0 to infinity of e to the minus x squared dx is the square root of pi over 2. This is called the Gaussian integral, named after Gauss, another elite tier mathematician, if you ask me. But we'll get to that. So anyway, the integral that we just did, the integral from 0 to infinity of where have we gone? Of x to the 5 times e to the minus x to the 4, turns out it's actually equal to the square root of pi over 8. How satisfying. That was question 90. Let's do question 91. Hopefully everyone's having a good time. Hope so, hope so. Question 91. We're doing the integral of sine to the 4 theta d theta. Okay, so there's plenty ways of doing this. Okay, you can just use integration by parts if you want. It's probably the easiest way of doing it, but I'm going to do it in a crazy way on purpose because it's just fun. So I'm going to notice, or I'm going to tell you that if I say that z, I'm going to use complex numbers. If I say that z is a complex number, then I can write it as, oh, and I probably don't want to use, do I want to use theta? Yeah, I'll keep using theta. If I say that z is cos theta plus I sine theta, that's just a general complex number. Then that means that, and I'm not going to explain this in too much detail, but z to the power of minus 1, which is all of this to the power of minus 1, by something called De Moivre's theorem, z to the minus 1, if you know complex numbers, then you'll be happy with this. If you don't, then you won't, is cos theta minus I sine theta. Okay. Now that means that z minus z to the minus 1 is 2I sine theta, where I is the square root of minus 1, of course. Okay. It also means that z, well, it means that that's the important thing. One important thing. One thing I'll also say in general is that z to the n, again by De Moivre's theorem, is cos n theta plus I sine n theta. So by all the same logic, I'm also going to tell you that z to the n plus z to the minus n is actually 2 cos n theta for any value of n that you want. Actually, believe it or not, we're very close to looking at those hyperbolic trig functions, because we have this relationship between exponentiation and the trig functions, and we're actually very close to being able to look at those, but we won't do it now. That's for another live stream. That's for another YouTube video. Okay, so it's a bunch of complex numbers stuff. Again, you're either happy with it or you're maybe not happy with it, but I'll just say, we're happy. I know it's a bit of a different topic, bit of a change up. If you're not happy with it, it's okay. There's always question 92. Okay. Sometimes you don't know every animal in the jungle, and that's okay. Put the old laptop on charge here. This laptop is so hot. I guess it's quite intensive to a live stream this long. I don't know. 5 hours, 18 minutes. Okay. This, again, I'm just going to do some random complex numbers business. Hopefully you guys can forgive me for that. But what I'm going to say here is I'm going to consider doing z minus z to the minus 1 to the power of 4. Okay, and that's because z minus z to the minus 1 to the power of 4 has two things that it can be. One, we already said that z minus z to the minus 1 is 2i sine theta. So it's 2i sine theta to the power of 4. So 16 I to the 4 sine to the 4 theta. That's why I've chosen to do it, because we're trying to integrate sine to the 4 theta. That's why that's there. But also, you can expand this out in the typical way, or at least using the binomial expansion. So it's also equal to z to the 4 minus 4z squared plus 6 minus 4z to the minus 2 plus 6, no, not plus 6, plus 1 lot of z to the minus 4. Okay, I've done that very quickly, but that's the binomial expansion. And so the cool thing about this is that we can set them equal. I to the 4 is 1, so 16 sine to the 4 is actually going to be equal to all of this stuff, these powers of z. Now you might say, okay, what's going on? What's going on? Remember, guys, I've written this. This is very important. Okay. What I'm going to do is I'm going to group up all of the values that only differ by a negative sign. So I'm going to rewrite this as z to the 4 plus z to the minus 4 minus 4 lots of z squared plus z to the minus 2 plus 6. Okay, you'll see where this is going. So now I can say that 16 sine to the 4 theta is actually equal to cos 4 theta times 2. So two lots of it. And that's using, again, that's using this thing here. Z to the 4 plus z to the minus 4 is 2 cos 4 theta. Same thing. I've got minus 4, and then z squared plus z to the minus 2 is 2 cos 2 theta, and then plus 6. And all I've got to do now is divide everything by 16, and I've worked out what you might call the quadruple angle formula or something like that. I've got an expression for sine to the power of 4, which is difficult to integrate, in terms of cos of n thetas, which are very, very simple and easier to integrate. So everything divided by 16, this is going to be 1/8 cos to the 4 theta. 4 times 2 divided by 16, that's a half, so minus a half cos 2 theta. And then 6 divided by 16 is 3/8. Cool. So now I actually have an expression for sine to the 4 in terms of causes. And you can see that the right-hand side is a lot easier to integrate. So I've kind of done what I want. So that means that the integral of sine to the 4 theta is the integral of 1/8 cos 4 theta minus a half cos 2 theta plus 3/8 d theta. And so this is going to be minus 1/32. No, not minus. Plus 1/32 sine 4 theta, because the 4 would come down at 4 times 1/32 is 1/8. Plus, minus a quarter sine 2 theta plus 3/8 theta plus c. And that's the answer. So a quick trip into the complex world. But yeah, it's quite cool. It's quite cool. And I'm just checking, and yes, that's what I got yesterday. Lovely stuff. Lovely stuff. Okay, cool. So we've done everything. We've done a bit of complex numbers. We're having fun. Can we do this in under 6 hours? Let's see. I'm still ordering that Indian takeaway, guys. If you've been following me since the Indian takeaway, it's happening. But I can't order it yet because I don't know how long I'm going to be going for. Okay. That was question 91. I believe. Let's check. I think it was, right? Yes, it was. All right, now it's time for question 92. I remember back in the day, guys, back at the beginning of this 5 hours, I used to just be like rattling them off while I was talking, but now they take a bit of time. All right, question 92. We want to do the integral of the natural log of x divided by x times the natural log of x. Obviously, a lot of ln's. So this one's not actually that bad because we're just going to let u equal ln x. So du dx is 1 over x. That's an x. So du is 1 over x dx. So dx is x du. So now we have the integral of the natural log of u over x times u times x du. And the x's cancel out. And we have the integral of the natural log of u over u du. Now, this integral requires integration by parts twice, annoyingly, I think. Maybe? I think. No, it doesn't require it twice. I don't know. But the point is, we've already done the integral. We did this integral earlier on. We actually did it. It's question 52. Question 52, it's literally this integral. So I'm just going to quote my own working out. This is a half the natural log squared of u plus c. Okay, this was question 52. And so this is a half the natural log squared of the natural log of x, because u is the natural log of x. Okay, so that was question 92. Bit quicker, bit quicker. All right. Guys, let me know how it's going in there. If you guys are still listening, I love it. Thank you so much for sticking along with me. All right, number 93. This is one of the last Caesars. I think we're almost... Okay, that's enough questions. Look at this rad jazz player. I don't know what that means. Is there there's no jazz in the jungle, bro. But I don't want to look and find out because I'm not curious, George. This is the last one. Number 94. Well, I feel like I have missed out a question because apparently that's 94. What question am I possibly missing? Who knows? I really have no idea. I've really confused myself. I've really confused myself. But who knows? Okay, we won't worry too much about that. Did I maybe miss? No, I've done them. I'm so perplexed. Anyway, it doesn't matter. It doesn't matter. Oh, YouTube, nice one. Oh, YouTube censors links. That's Google. I don't know. Cool jazz. Yeah. It's a bit like from the B movie, I think. You like jazz. Okay, right. I'm going delirious. So, we're almost there, guys. We're almost there. Question number 93, allegedly number 93. I thought it was 94, but, you know, it does appear to be, yeah, something like that. Okay, 93. So, we're doing the integral of sec x. Okay. Now, sec x, again, sec is 1 over cosh. So if you want, the definition of sec is it's 2 over e to the x plus e to the minus x. That's basically what we're trying to integrate. Basically. Kind of. So this one is a bit interesting. Yeah, I'm just looking at my own working out actually, and like I'm not quite sure what I've done. It looks like I've scribbled out a bunch of stuff. Why have I done that? Who knows? I think I was going delirious in the Starbucks yesterday, it seems, because I've just scribbled out a bunch of stuff that I don't think I should have. Oh, you know, whatever. So anyway, interestingly, for this one, if you let u equal shine x, not cosh, something cool will happen. So du dx is cosh x. So du is cosh x dx. And so the idea is that dx is du over cosh x, and this is going to be super important. Okay, so this integral, boom, boom, boom. This is the integral of, I'm going to rewrite sech as 1 over cosh, so 1 over cosh x. And dx is du over cosh x. So there's like 2 lots of that. So this is equal to 1 over cosh squared x du. Okay. And then that's equal to the integral of, and guys, remember that, where shall I write it? I'll do it over here. Remember that cosh squared minus sine squared is 1, okay? So cosh squared is 1 plus sine squared. So this is 1 over 1 plus sine squared x dx. And the idea is we said that u was sine x. So we've got the integral of 1 over 1 plus... Oh, and sorry, why have I said dx? It's a du, not dx. So we've got 1 plus sine squared, which is u squared. du. And again, guys, this is arctan. We've done this a million times. This is arctan u plus c. But we said that u was sine x. Okay? So that means that the integral of sech x dx is actually going to be arctan, so normal, of sine, so hyperbolic, of x plus c. So how interesting is that? We're doing an inverse normal trig function of a hyperbolic trig function. Amazing stuff. Okay. The duck with a monocle says the insanity is set in. You're absolutely right. I'm seeing these messages like 3 minutes later anyway. The delay isn't actually this bad. We're never getting Silk Song at this rate. I high key don't know what that is. I'm sorry. I don't know these things. I feel every day more and more like a boomer. Maybe it's not a boomer thing. Maybe I'm actually being a Gen Zer right now and I don't know about something that I should. Yeah, for real. Hell yeah. Okay, cool. So that's awesome. And yeah, that was question 93. Let's go on to question 94. Guys, we've officially begun. All right. We've officially begun the Harambe questions. So these are the most difficult questions that I've got. Or at least the most like mathematically interesting, okay? So question 94. The integral from 0 to infinity of, x to the n e to the minus x. Okay. And I'm just going to say for simplicity, this is when n is a natural number. Okay. But it doesn't necessarily have to be for what I'm about to say to be true. So does anyone know what this is? This is a very special function in mathematics. It's a function of n, not of x. X is like a dummy variable. It disappears when you actually evaluate the integral. This is called the gamma function, or it's very closely related to the gamma function. Technically, the gamma function, there's like an n minus 1 there, but it literally makes no difference. You might call this the pi function, the twin sister of the gamma function. Anyway, it doesn't need a name. This is a super interesting function. So if anyone hasn't seen this before, you're in for a treat because it's quite cool. So I'm just going to tell you what this is equal to, and then I'm going to talk about it a little bit. It turns out that for any value of n, let's say that n is a natural number, so 1, 2, 3, 4, 5, etc., or 0, it would work. This is actually equal to n factorial. I mean, again, if you're not 100% sure what a factorial is, it just means multiply the number by every whole number decreasing until you get to 1. So for example, 4 factorial would be 4 times 3 times 2 times 1, which is 24. This integral for any whole number value of n, will just give you n factorial. So if you, for example, the integral from 0 to infinity of, let's say, x to the 5 times e to the minus x dx, that would just give you 5 factorial, which is 120. Okay, so that's really cool. Now, we were talking about Euler earlier, and Euler is an interesting case here because this function, the gamma function, which is basically what this is, believe it or not, take your best guess of who developed it, it was Leonhard Euler. So this is yet another discovery, invention, development of Euler. So yeah, another reason why he's probably the GOAT. Now, why is this actually true, and why does this work? And who cares? Why would you want to do an integral when you can just do n factorial? What this lets you do is it lets you find factorials of non-whole numbers. So now, if you can do the integral, you can work out what 1/2 factorial is, or you could work out what pi factorial is, or whatever. And it's some of the stuff is really cool. We won't actually do that now. I'm just going to explain why it gives you the factorials. Okay, the idea is if you use integration by parts, so you let u equal x to the n and dv dx equal e to the minus x, then you get du dx equals nx to the n minus 1, and v is minus e to the minus x. So this integral becomes minus e to the minus x times x to the n from 0 to infinity, minus the integral from 0 to infinity of minus e to the minus x times nx to the n minus 1. So I put a plus there, n x to the n minus 1 e to the minus x dx. And I'm not going to do the whole limit and all that stuff because it's just long and boring. But take my word for it, if you plug infinity into this or 0, you're just going to get 0 both ways. So that term there is ignorable. And so what you get is that this thing just equals n times the integral from 0 to infinity of x to the n minus 1 times e to the minus x dx. So this is a function. Let's say that I do call it gamma. This is the Greek letter gamma. Let's say that I say gamma of n was this. Again, technically speaking, that's not exactly the gamma function, but I'm just going to call it that for a second. Gamma of n has this property that it's equal to n times gamma of n minus 1. Okay. Now, what else has this property, right? What else has this property? Factorials. Okay. Because n factorial is equal to n times n minus 1 factorial. And so that's enough actually to prove that this is this is a way to what you would call analytically extend the idea of the factorial. There is actually a proof, I don't remember what it's called, that this is that the gamma function is the only what you call logarithmically convex function that has this property. So basically, in layman's terms, this specific function is the only nice function that has this property. Okay, so it's unique. It's not just like, oh well, this is one way of doing it. No, this is the way of doing it. So it's pretty cool. It's pretty badass, and that's why it happens. And again, that's kind of called the gamma function. Technically, guys, because I keep saying it's kind of, but it's not. Just to be clear, the gamma function is defined like this. It's the same integral, but it's to the power of n minus 1 instead of n. So you put n in and you get n minus 1 out. So it's really super annoying, but gamma of n is not n factorial, it's n minus 1 factorial, which is just like, I don't understand why. I don't know why that's better. There's probably a reason, but I don't know. I don't know it. Anyway, I'm probably going to make a video on this at some point, but that's that. Cool. So that's just a little investigation, I suppose, of allegedly number 94, but I still feel like it's number 95. All right. Now, number 95 is a very super duper interesting one. And this is one that we did earlier. So it's the integral from 0 to infinity of e to the minus x squared dx. This is potentially one of the most important integrals of all time because it appears in many areas of maths. It actually is required in order to have the probability density function of the normal distribution. This appears in probability and statistics, as well as tons of other stuff. Okay, so it's super important. Now I'm going to tell you what this is equal to, and then I'm going to actually show you why. I'm going to remind you because I did say it earlier. This is equal to pi, or the square root of pi, over 2. Question is, why? Why pi over 2? Let me show you. This one's going to be quite tough. I did say to myself on this video, I do not want to do any crazy integrals. I don't want to do any vector integrals. I don't want to do any line integrals. I don't want to do any contour integrals. That's no residue theorem, Cauchy's theorem. I don't want to do any of that. And I didn't want to do double integrals either, or triple integrals, which do exist, guys, if you don't know. I didn't want to do that. We are going to do a double integral now. So if you've never seen a double integral, hold on tight. So I'm going to say that I've got this integral from 0 to infinity of e to the minus x squared dx. I'm going to give this the name I, and I want to work out what I is. I'm going to square I. So I'm going to times the integral by itself. Now, I'm not just going to times it by itself in any old way. I'm going to have this integral, and then I'm going to times it by an equivalent integral. They are the same, but I'm just going to change the letter of the alphabet. So I'll just use y instead of x, like this. They're the same. They're both the same. I'm still timesing it by itself because x and y, they're dummy variables. They're irrelevant. But for simplicity, I do want them to be different numbers. Okay, but this is, you're allowed to do this. This is fine. Now, this is where the double integral comes in. I'm going to say that x and y are independent from each other. So with respect to each other, they're both constants. So with respect to x, y is a constant and vice versa, which means that I can treat this entire integral as one big constant, and I can bring it inside of this integral. So I can go, this is the integral from 0 to infinity of the integral from 0 to infinity of e to the minus y squared dy times e to the minus x squared dx. Okay, so all I've done here is I've taken this integral and I've put it inside another integral, which I think is metal. I think that is absolutely metal. All right, now I'm going to use the same logic to put the other integral inside of the other one. So with respect, so again, this is an integral inside of an integral, and what I'm going to do is I'm just going to move the terms around a little bit, and I'm just going to move the e to the minus x squared. And I'm going to put it I'm going to put it inside of this, because with respect to y, x is a constant as well. Okay, so I'm going to rewrite this as the integral from 0 to infinity of the integral from 0 to infinity of e to the minus x squared times e to the minus y squared dy dx. So I've put a constant with respect to y inside of that integral. And now I have what you call a double integral. It's a double integral because there's two integrals. That's the idea. Now, why is this important? Well, because look at what I can do, right? So I've got boom, boom, boom. I'm just going to do some laws of indices to rewrite this as one big thing. And then I'm going to do one more. So the integral from 0 to infinity, the integral from 0 to infinity of e to the minus, I've got x squared plus y squared here, dy dx. And what I'm now going to do is I'm going to do a substitution. It might seem like a really weird one, but it's very common because I'm basically going to turn the integral into polar coordinates. Okay, so I'm going to say let x equal r cos theta and let y equal r sine theta. Okay, and I'm not going to go into the weeds of exactly why this works and all that stuff. But if I do that, then please just take my word for it, guys. Please take my word for it. When I do this, I've got my double integral. I've got e to the minus, now x squared plus y squared. If you square r cos theta and r sine theta and you add them together, you just get r squared cos squared plus r squared sine squared. That's just r squared by the Pythagorean identity. dy and dx, again, it's really complicated, so I'm not going to actually go into detail here, but dy dx becomes, for not very simple to explain reasons, r dr d theta. Okay, so the inside integral is with respect to r, and if we're going from 0 to infinity, that still goes from 0 to infinity. And with respect to theta, because I'm going from because my region in the y direction is 0 to infinity, in the x direction is 0 to infinity. So my region, my angle theta, starting from the positive x-axis and then going anti-clockwise around, it's going to be from 0 to pi over 2. Again, just some of this stuff probably doesn't make that much sense. It's very difficult to explain all the details if you've not seen this before, but I just want to do it vibes based. Okay. Now, the important thing here is that in doing this transformation, the thing inside of the integrand is actually integrable now because it's e to the minus r squared times r, which is doable. This is the important thing. So it's the integral from 0 to pi over 2 of, now, it's going to be e to the minus r squared. And again, if you differentiate e to the minus r squared with respect to r, you're going to get minus 2r e to the minus r squared. So I need a minus a half here so that I get just 1r, because there's an r there, lest you forget. And that's from 0 to infinity. And again, I really should have that limit sign, but I'm not going to do it because I'm a bit lazy. Okay. And hopefully you guys can see that if I did plug in infinity, I would get 0 for the first thing. And then I would get minus, so minus, and then minus a half for the second thing, d theta. So this is the integral from 0 to pi over 2 of just a half d theta. Okay. And then I'm going to get theta over 2 from 0 to pi over 2. That's going to be pi over 4. So I found out that that integral is pi over 4, but that's not the original integral. Remember, at the very beginning, we actually squared it. So this is I squared. Okay. So what I'm saying is I squared is pi over 4. So that means that I, which remember that this is the integral from 0 to infinity of e to the minus x squared dx, this is the square root of pi over 4, which is the square root of pi divided by 2, just like that. So again, it's kind of vibe based. You know, we're in the jungle, guys. It's vibes based in the jungle. That's the idea. Okay. So the idea is you're turning the integral into a double integral in terms of polar coordinates. You have to use this thing called the Jacobian, which we just did when you transform dx dy into r dr d theta. All that good stuff. It's a bit crazy. But that's the concept. That's the idea. That was question 95. That was question 95. I don't think I didn't say that it was question 95, but it is. It was. We're getting there, guys. Question 96. Question 96 is the integral from 0 to pi of sine to the nx dx, where again n is a natural number. Okay? N is a natural number. So this is a super important integral because there's something, again, I've got a video on this as well. Yeah, thank you, mate. I need the hype up. Ken lover, mate. You're a Ken lover, bro. I'm a Ken lover. I was going to say I'm a Barbie lover, but like, you're not a Barbie, you're a Ken, bro. Well, maybe, I don't know. Actually, why am I assuming your gender? Why am I doing that? Why am I doing that? But anyway, we're getting there, guys. This is question 96. Let's actually start numbering them again. I'm going to eat an Indian takeaway, play Fortnite, and just crash. That's my plan. Because, guys, have you ever tried to talk for almost 6 hours? And by the way, guys, before I did this, I did 2 hours of tutoring. The number of words that have come out of my mouth is unbelievable, mate. A dry mouth. And I don't want to drink my coffee anymore because it has milk in it. And I've realized that I've had it for far too long. So I don't want to drink it. Because I didn't finish it and then I refilled it. And then I didn't finish it again and then I refilled it. And now it's been like 3 hours since I last refilled it. So some of the milk in there is like literally about 8 hours old. So I do not want to touch that. And it's warm. Ugh. Can you guys tell that I've been drinking coffee? Okay. So this is a really important integral or interesting integral because, and I have a video on this, there is something called the Wallis product, which uses this. And if you want to know how it is used, you can see the video. But it turns out that pi over 2 can be written as the product. This is the product notation from r equals 1 to infinity of 4r squared over 4r squared minus 1. That means you guys probably know sigma notation when you add up all of the terms. With this one, you're actually multiplying all the terms together. Turns out if you do this, you get pi over 2. It's a terrible way of approximating pi over 2 because it takes ages to actually look like it, but it's equal to pi over 2, which is really cool. And I have a video on this. But the first half of the video is doing this integral, okay? And that's what we're going to do now. So it's kind of an interesting, you might call this a Wallis integral. If you look up Wallis integral on Wikipedia, you get an integral of this form. Or it could be whether the top limit is pi over 2, not pi, but it doesn't actually matter. You can do it either way. Anyway, I'm just yapping, so let's actually go into it. So the way that we do this is we do integration by parts. We go u equals, oh, and actually what I should first do just to make it clear is I'm going to rewrite sine to the nx as sine squared x. No, I'm not. I'm going to write it as sine x times sine to the n minus 1 of x. And you'll see why that's good. All right, and then I'm going to say that u is sine to the n minus 1 of x, and I'm going to say dv dx is just sine x. So it's a kind of another little cheat way to use integration by parts. That means that du dx is going to be n minus 1 times cos x times sine to the n minus 2 of x. And v is minus cos x. Okay. So using integration by parts here, we have that this is equal to the integral from 0 to pi. Oh, actually, I should do this. This is equal to a big box, and then u times v, so minus cos x times sine to the n minus 1 of x from 0 to pi minus the integral from 0 to pi of n minus 1 times minus cos x. So I'm just going to make it a plus and put a plus there. Cos x times cos x, so cos squared x, times sine to the n minus 2 of x dx. Okay. Hopefully we're chilling. Then we can evaluate at least the first term. So the first term, it's minus cos of pi. That's fine. And then sine of pi is 0. And also sine of 0 is 0. So this whole term here is just 0 minus 0. And then this is the interesting bit. So I'm going to take out the n minus 1, integral from 0 to pi, and I'm going to rewrite cos squared as 1 minus sine squared. You might say, why? Why are you doing that? Well, guys, we're once again, and again, if I name the integral from 0 to pi of sine to the nx, if I just name this I, all right, then what I've got is that I is equal to n minus 1 times, and then look at this, integral from 0 to pi of sine to the n minus 2 of x minus sine to the n of x dx. So I've got this, write it all out, just the busy work here. And then that's going to be minus dx minus n minus 1 times the integral from 0 to pi of sine to the nx dx. And guys, this is I as well. So basically I is equal to n minus 1 times this integral sine to the n minus 2 of x minus I times n minus, well, I'm going to write it like n minus 1 times I. Okay. Now, also, what I probably should have done notationally is I'm not actually going to call that I. I'm going to call it I of n. Okay. I of n. So just by slightly adjusting my notation, I of n, I can then say that it's n minus 1 times, and then this integral is, do you see that it's actually I of n minus 2? So times I of n minus 2 minus n minus 1 times I of n. Rearranging everything, if I add n minus 1 lots of in to both sides, I've got I of n plus n minus 1 times I of n equals n minus 1 times I of n minus 2. Which means, because I've got I of n plus n times I of n minus I of n, so just n times I of n is equal to n minus 1 times I of n minus 2. So that means that I of n is n minus 1 over n times I of n minus 2. What a mouthful. Absolute mouthful that is. Okay. So what we have is we have what's called a, what do you actually call it? I mean, it's like a recurrence relation. It's got a name actually. It's called a reduction formula. Okay. This is in A-level further maths, further pure 2, the module. It's very well known, like it's well known, but slightly uncommon. And so what it is it's a way of writing an integral in terms of n, in terms of the same integral, but with a lower value of n. And what you can do is recursively use this. So for example, I of n, okay, it's equal to n minus 1 over n times I of n minus 2. But I of n minus 2 is the same thing, but replacing the n's with n minus 2s. And you could just like go all the way down, times them all together until you get to like a really, really trivial and simple result. So one thing that we did at the beginning of this is we split sine to the n of x into sine times sine to the n minus 1. And then we actually further, when we differentiated it, we ended up getting like sine to the n minus 2. So n, in order for this whole formula to work, or for this recurrence relation, reduction formula, whatever, this requires n to be bigger than or equal to 2. Okay. So you might say, well, okay, what if n is 0 or 1? Well, let's work it out. So let's look at this and say, well, when n is the number 1, I of 1, let's do 1 first. That's the integral from 0 to pi of just sine x. And this is a very simple integral, so we can just work it out directly. So sine integrates to minus cos. And then we've got minus cos of pi minus cos of 0. So cos of pi is already minus 1, so this is 1 plus 1, so this is 2. So I of 1 is 2. I of 0 is even easier. Let's do it over here. I of 0 is the integral from 0 to pi of sine to the 0, so just of the number 1 dx. And we can see that this is just going to be x between 0 and pi, so just pi. So I of 0 is pi, so I'm going to write these down. This is really important. I of 0 is pi. and I of 1 is 2. And then what we can do is, it depends whether n is even or odd as well, right? Because, for example, if n is an even number, you can use this formula and you're going to get all the way down and you're going to have to stop at I of 0. But if n is an odd number, you're going to have to stop at I of 1. So let's say that n is equal to 2k, where k is a natural number in and of itself. So let's basically say that n is even. Then we have I of 2k. That's going to be 2k minus 1 over 2k times I of 2k minus 2. And just to be clear on what's going on here, I of 2k minus 2 is just 2k minus 2 minus 1, so minus 3, over, and all I'm doing is I'm looking at this again, but with n equals 2k minus 2, over 2k minus 2, and that would be multiplied by I of 2k minus 4. But instead of doing that, I'm just going to actually rewrite, and you can actually already see what the pattern is. The next term would be 2k minus 5 over 2k minus 4, and this is going to go all the way down and down and down and down and down and down until you get all the way to when k is the number 1 and we're doing I of 2. So we're going to stop when k is the number 1, and we've got when k is the number 1, what would we have? That would be I of 2. So 2 minus 1, again I'm just using n equals the number 2 here because that's when k is number 1. So we've got 1 over 2 times I of 0, because obviously 2 minus 2 is 0, and I of 0 is pi. Okay, so this is going to be pi here. So if n is even, then the integral, basically the integral of sine of 2k of x from 0 to pi, what I'm saying is it's pi times the product from r equals 1 to k of 2r minus 1 over 2r. Okay, so hopefully that kind of makes sense. It's obviously very complicated, guys. We're doing Harambe level integrals. Okay, they had to kill him because he was too good at integration. Okay. If k is odd, so also if n is odd, then we have n equals 2k plus 1. Then we have that the integral from 0 to pi of sine to the power of 2k plus 1 is going to be the following. Okay. So, again, just using this thing up here, we're going to have, using the number 2k plus 1, I of 2k plus 1, we've got 2k plus 1 minus 1 over 2k plus 1 times the same thing, but replacing the k's with k minus 2's. Yeah, replacing the 2k plus 1's with 2k minus 1's, I guess you could say, yeah. Taking 2 off of everything. So 2k minus 2 over 2k minus 1, 2k minus 4 over 2k minus 3, etc. all the way down until we get to the last possible odd number that we can do here is 3, because we can't have 1 because that doesn't apply. Remember, n has to be bigger than or equal to 2. So the last number we can use is when n is 3, which means k is the number 1. So it's going to be is that right? When k is the number 1, you get n equals 3. Yep. So 2k plus 1 minus 1. So 2k, or what am I saying? When k is the number 1, then, oh yeah, so times 2 over 3. Yeah, that's right. Okay. And then the final term is 2 less than that. So I of 1, which we know is just the number 2. Okay, so that means I'm going to write these both out. The answer to this one is that the integral from 0 to pi of sine to the 2k of x is equal to pi times the product from r equals 1 to infinity of 2r minus 1 over 2r, and the integral from 0 to pi of sine to the power of 2k plus 1, so that's basically when the power is odd, is 2 times the product, and this is what we just did, from r equals 1 to infinity. Oh, not to infinity, sorry. Why have I written infinity? I think I'm thinking about my Wallace product video, which you do use infinity, but sorry if that was confusing. Not infinity. To the power of k in both cases, k. And this one, we can see the general pattern is it's 2r over 2r plus 1. And the idea, by the way, for the Wallace product formula is you basically take the ratio of these two, and the ratio ends up basically being, I mean, you can literally see that, look, pi and 2, pi over 2. You take the ratio and stuff happens. You take the limit as k goes to infinity, and it all just works out. It's really cool. It's actually genuinely, I'm not even just being funny, like it's actually really sick. So yeah, that's the idea. Cool. Whew. So that was question number 96. How's everyone feeling again? Hopefully everyone's good. Hopefully I'm not in the vacuum, in the void on my own. We're almost there. Question 97, because that was question 96, wasn't it? Yes, it was. Question 97. So this one's going to use Feynman's trick. So this is the integral from 0 to 1 of x to the a minus 1 over the natural log of x. And this is when a is greater than 0. Okay. So someone, I think they've probably gone to bed ages ago, but someone did mention Feynman being their favorite mathematician. I don't think they're here anymore, but we're going to use Feynman's trick to do this. So the idea behind Feynman's trick is you consider this to be a function of the variable a. Okay, so you just say f of a is this thing here. I'm just going to say, because it's not a function of x, because x is a dummy variable. When you actually compute the integral, there's no more x's. Okay, and then what I'm going to do, the clever thing here, is I'm going to differentiate it, not with respect to x, but with respect to a. And it's very hand wavy because there's actually a lot going on here mathematically, the dominated convergence theorem and all that stuff. There's actually a lot going on, but I'm just going to gloss over all of it because it's incredibly complicated, to be quite frank. The derivative of x to the a, not with respect to x, but with respect to a, is x to the a times the natural log of x. Okay, 1 just disappears, and this is still over the natural log of x. And the clever thing is that obviously they cancel. So all you have to do is actually the integral of just x to the a dx. And we've said that a is positive. We don't need to worry about a being minus 1 or anything. So here we've just got x to the a plus 1 divided by a plus 1 between 0 and 1. And this is just going to be 1 over a plus 1. Now, that's not the answer, because that was the derivative of the integral as a function that we're thinking of. So we need the original because we want f of a, not the derivative. So f of a is just the integral of 1 over a plus 1 with respect to a, dA. And we also need to, we're going to get a plus c, so we need to work that out. So we're going to get the natural log of a plus 1. Don't need the modulus function, the absolute value function, because we already know everything's positive. But the tricky thing is that we have the plus c. Okay. Now, what I'm basically saying is the integral from 0 to 1 of x to the a minus 1 over the natural log of x dx is definitely the natural log of a plus 1, but there's a constant, and we need to work out what the constant is. But guys, do you see that if a is equal to 1, then the integral becomes the integral from 0 to 1 of x to the if a is exactly equal to 0. And what I'm going to do, because there's technically no reason not to, is I think that actually a should be greater than or equal to 0 here, so it's allowed to be 0. It's technically not even a problem if it's not allowed to be 0. It still works, but it makes the maths way more complicated, so I just won't bother. If a is equal to not 1 but 0, the integral just kind of like just vanishes basically. So if a is 0, we have the integral of just x to the 0, which is 1, minus 1 over the natural log of x. So it's just the integral of the number 0 between 0 and 1, which is 0. Okay, and on the right hand side, when a is 0, we have the natural log of 1 plus c. So what I'm saying is 0 needs to be the natural log of 1 plus c, which is nice and easy because the natural log of 1 is also 0, so c is just 0. So that means that the final answer here is that the integral from 0 to 1 of x to the a minus 1 over the natural log of x dx, if a is greater than 0, is equal to the natural log of a plus 1 for any value of a greater than 0. Pretty nifty. So it's called Feynman's trick, differentiating inside of the integral sign. It's pretty cool. Pretty cool. Okay, we've officially been going longer than 6 hours. Jeez. Jesus. Okay. We can do it. I think we can do it by 6.5. I think we're really near the end now. That was question number 97. Now it's time for question number 98. The integral from 0 to infinity of sine t times e to the minus 3t. Now, this integral isn't actually Harambe level, okay? But I'm going to do it in a method that is Harambe level. I'm going to do this by using what you call a Laplace transform. Okay, so just to be very clear, I'm just making a little note of this. The Laplace transform of a function of x, or I'll use t just because t is in the question. It's a function that turns a function into another function, basically. That's why it's called a transform. Okay, so what it does is it integrates the function from 0 to infinity, but it's also multiplied by e to the minus st, where s is a new number. Okay, so you're basically turning it, and by the way, sometimes we call this f, capital F of s. We're turning a function of t into a function of some other variable s. I've got a bunch of videos on this already. The principal concept or reason why you might want to do this is because it lets you actually turn differential equations into algebraic equations. So in a sense, it's very powerful. Despite being named after Pierre-Simon Laplace, the mathematician, it was actually Leonhard Euler that did this. Leonhard Euler strikes again. So Laplace transform, it's named after Laplace. Actually, someone said it. There's a joke where they name stuff after the secondary mathematician, because why would you name the 100th thing after Euler? It's just confusing. So the Laplace transform, I mean, Laplace is like in some way associated with it. You could read up on it on Wikipedia, but Leonhard Euler is the guy that actually developed this properly, believe it or not. So really cool. Really, really cool stuff. All right, now why am I mentioning this? Well, because do you see that this integral here looks like the Laplace transform of sine of t, and then evaluated when s is the number 3. So all we have to do is know what the Laplace transform of sine of t is. And I'm just going to tell you what it is. Okay. The way that you would prove it is by directly doing it, which is boring. So the Laplace transform of sine of omega t, okay, is omega over omega squared plus s squared. Okay. Now in this question, omega is the number 1. So the Laplace transform of sine of just t on its own is just 1 over 1 plus s squared. Okay. Cool. And by the way, this is going to come up again later. So make sure you're happy with that. So this is equal to the Laplace transform of sine of t. So it's equal to 1 over 1 plus s squared. But it's a value, we can see that it's not s, it's the number 3. So this is evaluated when s is the number 3. So it's equal to 1 over 1 plus 3 squared, or in other words, 1/10. So that means that this integral, we can very simply say it's 1/10 here. Fairly cool way of doing it. All right, that was question number 98, guys. We're so close. Question number 99. The integral. And again, I've got a video on this. The integral from 0 to infinity of sine x over x dx. So this has a name. This is called the Dirichlet integral. It's named after I believe he's French or maybe German, a mathematician called Dirichlet. He's pretty well known, pretty famous mathematician. I don't know his nationality though. I think he's German. Anyway, it doesn't matter. This integral can be done in lots of ways, and actually, in the video that I've got on this, I actually use Feynman's trick. So that's interesting. But what I'm going to do is I'm going to use again the Laplace transform. Okay, I'm going to do it. I'm going to do it. Now, again, some of this, it might not seem like particularly that satisfying because I'm just going to tell you a bunch of stuff about Laplace transforms that it's not really immediately obvious. But it turns out, and again, I'm just going to remind you what a Laplace transform actually is. The Laplace transform of a function of t or x, whatever, it doesn't actually matter, is the integral from 0 to infinity of the function times e to the minus st, where s is just like some made up new variable. Okay, so you're turning it into a function of another variable. And we sometimes call that capital F of S. Now, an interesting theorem or result from Laplace transforms is that the Laplace transform of a function divided by t, like sine t divided by t, for example, and I believe the way that you prove this is actually by doing another double integral, so I'm not even going to go there. But this actually is equal to the integral from s to infinity of the Laplace transformed function, but I'm just going to use u like as a dummy variable. But capital F of u is the Laplace transform of just f of t on its own. Okay, so it's just the Laplace transformed function of just f of t on its own. And I'm just looking at my wall because I've actually got this on my wall, I think, somewhere. Oh, maybe I don't. I thought I did. I thought I had this written on my wall, but I don't think I do now. Anyway, it doesn't matter. Okay. So what I'm saying here is that this can once again be treated kind of as a Laplace transform. So bear with me for a second, and let's just consider a new function that I'm going to say it's the integral from 0 to infinity of sine of t over t times e to the minus st dt. Okay, so it's not the same, it's not the exact same, but it's quite similar, and that's an S, not 5. I can say that this is the Laplace transform of sine of t. Let me just make sure my head's not in the way. Sine of t divided by t. Okay. And again, by using this formula, this is equal to the integral from s to infinity of the Laplace transformed function in and of itself. And guys, remember that the Laplace transform of sine of t is 1 over 1 plus s squared. Okay. Now we're treating it as a function of u, not s, but it's the same thing. It doesn't actually matter what letter of the alphabet that you use. And this is equal to the integral from s to infinity of just that 1 over 1 plus, and we're going to use u squared du. It's just a dummy variable. It doesn't matter what it is. And guys, look at this. Once again, we have this 1 over 1 plus u squared business. 1 over 1 plus u squared integrates to arc tan u from s to infinity here. And again, I really should be doing the whole limit thing, but I can't be bothered, to be honest with you. I should be doing the limit as t approaches infinity. But as I said earlier, arctan of infinity, or the limit as t approaches infinity of arctan of t, whatever, it's pi over 2. And then I've still got minus arctan of s. Okay? So I'm saying that the integral from 0 to infinity of sine t over t times e to the minus st dt is pi over 2 minus arctan of s. But you can see that if I just let s be the number 0, then I'm going to get my integral. The integral from 0 to infinity of just sine t over t times e to the 0, because I'm saying s is 0, is going to be pi over 2 minus arctan of 0. And arctan of 0 is 0. So this Dirichlet integral, the integral from 0 to infinity of sine x over x, is just pi over 2. Super important, super famous, actually, result. Very well known. That's one of many ways of doing it. You can also do this Feynman's technique. It's quite similar. Me and my friend, actually, in first year of university, we did this integration project thing. It's pretty much just for fun, nothing serious. And we each had a chapter in the book where we solved the same integral, this integral, the Dirichlet function or Dirichlet integral, using different methods. He used Feynman's trick, I used the Laplace transform. They're very similar. They're mathematically almost the same thing. But it's cool nonetheless. That was number 99. Now, guys, I have miscounted because I really don't know what happened. I feel like I've done one too many. I think I've already done 100 integrals, but I've miscounted. I don't know. I'm not going to copy it out though, guys. I've run out of integrals because that was integral number 100 in the book. So I don't know where the rest went. I'm not going to finish this off without doing the 100th integral. So I'm just going to make up a silly one. This is not Harambe level. This is the final integral. All right. It's a formality, guys. It's a formality. Okay. And I want everyone to say right now what their favorite integral was in the video, please. If you have a favorite, maybe you don't have a favorite. Maybe they're like your children. I don't know. Please do let me know if you have a favorite integral before we finish this thing off at just under 6.5 hours. Unbelievable. Okay. This is equal to 3x from 0 to 1. That's going to be 3 times 1 minus 3 times 0. It's going to be the number 3. Low-key, the pressure was actually on for that one because I was like, oh my God, if I mess this one up, then what's going on? Number 69 was a big win. I know that 69 is a funny number. I actually don't remember what number 69 actually was, though. Number 69 was I know you're making a joke. I know you're making a joke, but and that is funny. I'll agree with you, Ken Lover. But the integral of 1 over 3 plus 4x squared was pretty strong, actually. I think you're actually, if you're not joking, that's genuinely a very good choice, because that was it's quite a difficult integral. Anyone else have a favorite integral? We're done. We're done. We're done. We're done. We're finished. We're finished. Celebrate. King of the jungle, mate. King of the jungle, mate. King of the jungle. King of the jungle, mate. King of the jungle. King of the jungle. I've lost my mind. I'm ordering the Indian takeaway, guys. I've deserved it. Ken Lover, congratulations. Thank you, mate. Thank you. Title is wild tough. It's tough. It's tough, isn't it? It's tough, bro. I'm in the jungle, coming at you live from the jungle. Don't ask me why the lighting hasn't changed for 6.5 hours and why I haven't been eaten by a tiger. I am in the jungle. Okay. And yes, there is 4G/5G in the jungle. I rode a 5G horse to get here. It's a horse made out of 5G. I haven't eaten anything in 6.5 hours, and I have an appetite. I'm going to... Well, this is a Christian space. Well, not a Christian space, but this is a religious space, guys. I'm going to do unholy things to my Indian takeaway tonight. Okay? I'm going to do unholy things. I'm going to eat it with maximum delicacy. I'm going to eat it with maximum delicacy. And that's verified. Straight up. Okay, guys. I think that's it. Stay tuned. Stay tuned. Stay tuned for the next video. The next I'm literally delirious. I'm literally delirious. Stay tuned for the next live stream, guys. Please do leave some comments. You don't have to answer right now, but leave some comments on my videos. And let me know what you want to do. Should I do 100 derivatives? Should I do 100 differential equations? Should I do 100 Laplace transforms? Okay, I know it's very black pen, red pen, guys, because he does that a lot. But let me know what I should do. And I will do them. I will do them. Crazy. I'm genuinely quite proud of myself because I was like, am I going to do this today? I've been putting it off, guys. I've really been putting it off because I was meant to do this the other day. And I was like, oh, I can't. And today I was really having second thoughts, but I was like, should I really do it? Should I really do it? And I was like, yeah, let's do it. I genuinely thought I could do it in 2.5 hours. Like, if you start the live stream from the beginning, you'll see that I say it's currently 2:30. I need to be done by 6 p.m. So 3.5 hours, not 2.5. I mean, that's unbelievable. Like, obviously that was never going to happen. I can't believe it. I was kidding myself. I mean, I know that if I really, really focused, then maybe, but I would have blitzed it, and I wanted to go at a chill pace and answer questions and have chats and stuff. Why am I thumbs upping? Like, why has it done that? It's got, like, on Mac, it does this weird thing where, like, if you give a thumbs up, there we go, look. It's giving me a thumbs up in my head. I didn't ask for that. I'm in the jungle, mate. I'm a celebrity. I'm in the jungle. No, I'm not. I'm just joking. I'm getting delirious. Thank you, everyone, for joining. I genuinely appreciate it so much. Okay, I'm in the jungle. My room is actually getting dark right now. My background is not getting dark because I'm underneath some leaves. So that's just how that works. When I said my room, I actually meant my jungle. My jungle. And I think we'll leave it there because otherwise I'm going to go insane. More insane. thank you guys as always so much for watching. I do genuinely appreciate you guys sticking along with me for this long. It makes me really happy. I'm being serious. I've got a big smile on my face. This is genuine. I'm really, really happy. So thank you guys so much. It's like I've got runners high now. I've got runners high. I've got jungle high. I've got jungle high. Okay. I will see you guys in the next epic and extra maths video. Thank you so much for watching. I appreciate it as always. Love, kisses, not kisses. Well, like kisses in a platonic way, guys. It's not weird. Love and generosity and goodwill to every single person that has joined the live stream. Love you guys. And genuinely, thank you so much for watching. I mean, I really appreciate that. So, yeah, I'll see you guys in the next one.